outfit is just super cute, and the color wave is amazing.
There we go. And then doing my best at worst case scenario.
No worries.
Bring up
We are
Chip
live.
Studio to color over where I think you may have seen things.
We are broadcasting. I'm going to let our attendees in and see what we get today.
Yep.
Let's get this started. So I'm just going to let attendees come in. We've got already, no, it's just the three of us. Woohoo! Ooh, nobody wants to get up at early o'clock on Saturday morning. Oh, they probably thought, oh, you were supposed to start 2 minutes ago. What happened? This is all being live streamed.
Watching. Yeah.
This is all being live streamed on YouTube, by the way. Hello. Good morning. Thanks for joining us. Oh, good. We've got one guest joining us. Good morning.
Good morning.
So we're just gonna give it 10 minutes or so and let the attendees start coming in. Hello, I Lucinda Offer here from the Royal Astronomical Society. So just get yourself comfortable. If you haven't gotten a cup of tea yet, maybe you can get that sorted, or a little breakfast burrito perhaps. And we're just working on things in the background and getting things sorted. And we'll be with you in about 5 to 10 minutes.
Thank you for your patience with us, everyone. I'm Emma Thomas. I'm the astronomer today. We are just at the moment getting things set up at IRTF, starting our very boring side of astronomy, where we're doing our data. Well, we're taking in data from stars and from what we know as flat fields and dark fields, which are essentially just our baselines, so that we have everything ready for looking at Uranus.
That is not boring. This is so awesome. This is so awesome what you're doing. And it's, yeah, they wouldn't be here probably if they thought it was boring. All of it.
But it is needed. I can't say that it's something that we shouldn't do. It's something we definitely have to do to get the data, the data that we need for. But it's a bit of waiting around, not seeing much whilst we do it.
Yeah, they're seeing you, and kind of it is sort of like a passing the baton. Just like we were talking to 2 schools yesterday, and all those. I said, how many of you want to be astronomers? Just from listening to you and Henrik, do you see all those hands go up? And that's exactly what this is.
Yeah.
Because some people don't start this career path young. Some people get inspired later in life as well.
Yeah.
And change careers. And it's just from hearing about, seeing, learning, and following, the people who do something that they have an interest in, and they get inspired to take it on themselves.
Exactly. I mean, I have great respect for people who, decide at age 30, 40, 50, 60, even 70, who go, you know what, actually, I want to go off and I want to go do space. Because that's a large step to do, to go, okay, actually for part of my life I dedicated towards this area, now I'm going off to do an entirely new area. But I feel in some regards it's useful to know, I say useful, it's kind of comforting to know, like, it's not, if you've, like, I guess from an early age from school, you're always told, okay, you've got this one thing you have to do and that's what you're going to do forever and ever and ever. And that's it. Whilst these days, actually, you can do what you want. If you want to go off and do space science, you can. If you want to go off and do engineering, you can. If you want to go off and invest with, more into the business side of things, you can. If you want to do web coding, you can. There's so many different things that you can just decide to go and have a look at and be like, actually, yeah, I'm kind of interested in this. I'd like to see if I can dabble.
Yeah, or see how far you can go. I know I teach GCSE astronomy at the Royal Astronomical Society. We do this for free, by the way. Every 2 years, we open enrollment. So I have my students in their second year, and a good percentage of them are adults who want to take GCSE astronomy just to, get that foundation in case they do want to take it further, or they just want to learn a little bit that the GCSE covers, the basics. So Yeah, I only have a graduate degree, so I don't have a PhD yet, and I possibly might get one. I've never had the time to devote, as a geologist, my time and skills, if I still have them, because I haven't used them very much. But to learn more about Mars geology, I'd love to kind of specialize in something. And the UK is really great at specialists, creating specialists. It's a PhD machine, as far as I can tell, and it looks like that's, you have a lot of PhD and a lot of specialists in this country, which I think is really fantastic. And I love the idea of reinventing yourself at any age.
Exactly. Yeah, it gives me a lot of hope for for everyone that it's not. Well, so I think it's something that we really do need to encourage more, for people to not feel that that's it, they're locked in. You have a lot.
At any age, keeping your brain, learning new things helps develop your brain, or keep it as youthful as you can as we get older. So learning is helpful. I wanted to ask you what you think about this. I've always had turned off the chat before, but yesterday we had the chat open to all our attendees, and what do you think about that? I enjoyed the interaction with them. What do you think?
Yeah, no, I enjoyed the interaction. I don't find much of a reason to not, unless, well, I say this more as somebody who's watched Twitch streaming and whatnot, unless there's lots of spamming, or unfortunately somebody gets spam raided, and that one's equally not fun. So yeah, we're hoping that
okay, great. I will get that. I will keep it open. And good morning, Kevin from Thailand, who said he joined a few times, or they joined a few times yesterday and loved it. So looking forward to today's. Thanks for joining us again.
Thank you.
And I don't know who we have on. We have 33 people on YouTube. So the video from yesterday, day one, we already have over 2.8 thousand views just from yesterday when we finished.
Yeah.
We finished kind of late as well, after 5 o'clock. We went all day, which we're going to do again today, just setting things up and letting people come in and join us. I think I'll go ahead and do a start, if that's all right with you.
Yeah, perfectly fine.
Okay, good. Where am I? I'm trying to find there we are. And what else do I need? Normally don't work on the weekends. So sometimes we do at the RAS. But today, or this year, really, it's been feeling a bit tough working on the weekends even. It's been harder, actually. This whole online thing has been exhausting and difficult and hard. So bear with me as I get my own bearings straight. Here we go. Let's get this started. Just want to say hello and welcome to the weird and wonderful world of Uranus 3-day live stream. My name is Lucinda Offer, and I am the Education, Outreach, and Events Officer for the Royal Astronomical Society. And we're here on day 2. See if I can get my slide changing there. Somewhere around day 2, there we go, of the live stream of Uranus. And this is all about, like, if you ever wondered what a professional astronomer does. Well, this is exactly what we're going to be showing today. We have astronomer Emma Thomas with us, and I'll introduce her in a little bit. But what you're going to find out, well, we're going to be remotely observing Uranus from NASA's Infrared Telescope Facility, the IRTF. And I think I showed a picture of that earlier, so I'm going to go back to that again. Here we go. Got my slides a bit out of order. This facility is a NASA telescope facility that's atop Mauna Kea, Hawaii, to watch astronomer that we have Emma Thomas, who's currently connecting now with Dr. Tom Stollard. I don't think he's with us yet, but he will be joining us in a bit. And also other participants of the H3 Plus team and their work that they're going to do in supporting Emma in collecting her data. We're going to see what discoveries might be made, and we'll have another visit from our librarian, Dr. Sean Prosser, who will visit us. I don't think she'll be at the Royal Astronomical Society library today. I think she might be visiting us from home, but we're happy to have her back and have a chat with her about Herschel. She'll be sharing the search for Uranus, the connection between William Herschel and the RAS. Charles Draper has said he'd also join us again. He was with us yesterday, visited us, and had a chat about the Herschel Museum and its history, and a lot of information about William John and Caroline Herschel, and took us about the museum to look at the lots of different, the 7-foot telescope, the replication of the 7-foot telescope that Herschel used to discover Uranus. But in this, this is the place in Bath where William Herschel first discovered the planet with his own homemade telescope 240 years ago in 1781. So we will also have special guest appearances by scientists who will join us throughout the live stream, sharing insights about the weird and wonderful world of Uranus. And I was just going to show you, let's see if I can get, I should say that we, this was yesterday's program. You don't want to see that. Let's hope I have today's. Here we go. Today is Saturday, the 9th of October. We're going to be here from 9 a.m. to almost 5 p.m. Yesterday we ran a little late, and that's okay. We had a great Q&A session with Westminster School GCSE astronomy students. Today we don't have any classes or any school rooms joining us because it's Saturday, and they don't go to school on the weekend. So we're just setting up here. So again, taking our time, getting started this morning. Emma will please share with us about the science and probably give us an update of how things went yesterday. We'll get a telescope view, hopefully by 10 a.m. And then 10:30, Dr. Prosser will join us for a chat about the history of Uranus and Herschel. We'll be going back to the telescope to get updates on what we're collecting data. And then we'll have Ophelia Wibisono. Emma, I wanted to know, is Ophelia a PhD student?
Yes, so
okay.
She's a PhD student at the same facility as Will done yesterday,
okay.
So at UCL, MSSL.
MSSL, right. I just want to make sure I didn't need to be calling her Dr. Ophelia Wibisono, but I figured you would have told me if I needed to. A Q&A with the H3 Plus team, which is always fun at 12:15. And then I'm only hosting this morning, because it's kind of fun this time. I'm definitely handing over the baton to hosting. We're going to have Dr. James O'Donoghue host the PM session today. So if you're a big fan of James, who has a huge following, I think he said 134,000 followers on Twitter. He's going to be doing the second half of the hosting day. So I'm really excited to that. I'm going to have a chat with him at 12:45 actually, because he starts at 1. And I just wanted to pick his brain a bit and say, what is it? How did you get this? How did this come about? His interest. He does these great animations, graphic animations that Emma has been showing since yesterday. Really fantastic ways to help us visually understand Uranus and its tilt and its magnetosphere. Very fantastic things. And he just whipped up those videos overnight for Emma. It's fantastic. And then Professor Steve Miller from UCL, he is going to visit us, and I'm so looking forward to this. I work with Professor Miller on a weekly basis. He's on our council at the Royal Astronomical Society, and he's been helping us with the RAS 200 projects, and I have been working closely with him on that in this last year. So I get to it feels like I talk to him every day. He's a lovely person to chat with. But also, he's the guy who discovered H3 Plus. Is that okay to say, Emma?
He's been one of the leading members with H3 Plus.
Yeah,
it's a bit all over the place with H3 Plus because there's laboratory H3 Plus, which has its own section, own observations. But I would say Steve has been the biggest source of researchers looking into H3 Plus, certainly.
So sort of raise the flag and say, hey, we should take a look at this.
Yes, exactly.
Okay. So excellent. Well, he's going to be here and he's going to tell us his story himself. So be here for 1 o'clock for that with Professor Miller to talk about this whole, why are we looking at H3 Plus? And I'm sure Emma will mention that as well. But Professor Miller, no pressure, Emma. But I'm sure Professor Miller will definitely be able to tell us, because he's been doing it for, I don't know, since is it the 70s? Yeah,
I would say so, yeah.
A long time. So if anyone has all the answers, because I certainly don't, Professor Miller will. And again, we'll be going through updates on the telescope, and then Dr. O'Donoghue has brought in a couple of speakers, Dr. Elizabeth Tasker, Associate Professor, I believe, and giving us some, I can't remember, I don't have it in front of me what she's talking about. She's on the other, let me just see here. What is today? It's Saturday, day 2. we are going to have her speak about, first of all, Ophelia is going to speak about future observations, XMM Newton. We have Elizabeth Tasker she's from JAXA. She's going to talk to us about exoplanets. Wow, I am so excited about that actually, because I love Uranus, I love our solar system, but exoplanets are like, mind-boggling. It's amazing that you look out at stars and now we know the likelihood there's planets going around those other stars. Pretty exciting. And then Heidi Hamel, Dr. Heidi Hamel, who's possibly will talk to us about Webb, the James Webb Telescope, and she's also an ice giant expert. So that's really exciting to have those talks to look forward to today. Let's see if we have anything else. Again, if you have any questions or comments, we do have our chat open on Zoom. If you want to join us on Zoom, the Eventbrite registration is open until tomorrow at noon. We are over 500 registrations by this time, but so we can have up to 950, almost 1,000. So if you want to join us here on Zoom, you're watching us from YouTube, go to Eventbrite, Royal Astronomical Society's page, and you can still register to be with us here on Zoom. And if you have any questions, please post them we're on YouTube, so you can post your questions to YouTube if you'd like to. And if you're joining us on Zoom, we have the chat open, so you can chat directly with Emma. All right, Emma, do you want to tell us what's going on with the telescope?
Yeah, well, so I was going to go through the science first off, because at the moment we're still setting up. So we've got the star in place at the moment, but that is a lot of fiddling around, so it's not going to be too interesting. So instead I've brought along Henrik's slides from yesterday, which is kind of going over, I guess, like a brief background, but about Uranus, about the history, about what we know, what we are still befuddled on, and what we today are trying to enlighten ourselves with the science. So I'm going to hopefully be able to share this in just a moment. Sorry, Lucinda, I can't actually share the screen on my end. It says it's unallowed.
My bad.
Okay, there we are.
You're all good now.
Perfect. So let's hopefully, there we go. And then share screen. Okay. There we go. Hopefully that is, yeah, there we go. So welcome everyone. Apologies, I'm just going to get my notes out because I was trying very quickly this morning to sort this out, as Henrik very kindly gave me these slides, and I've been doing my best to try and cover over everything that's in here. So yeah, welcome to the weird and wonderful world of Uranus, the live stream that we're focusing on the planet Uranus. My name is Emma Thomas. I am an astronomer, but also a third-year PhD student at the University of Leicester, where my focus is looking at the infrared aurorae at Uranus, as we have been looking for them for pretty much the last 30 years, and I haven't had a great amount of success. So as I said, we're having a look at observations of Uranus, and what are we trying to find out? Well, firstly, when looking up at the stars, or looking up in space in general, it's best to think kind of best to look back and see how early humans first saw the sky. So one big things, or at least one of the things Henrik had picked out, was that back in the ancient Roman eras, the Romans actually named their week after the sun, the moon, and then obviously the 5 other visible planets within the sky: Mars, Mercury, Jupiter, Venus, and Saturn, which is where we get some of our weekdays, these Sunday and Monday from. So obviously some of these we have kept for the English language at the moment. Of course, civilizations back in those days had much better views from the night sky, so they don't have the pollution or light pollution that we do have these days. But they definitely would have seen phenomenal displays of space, whether it be with comets passing by as well, or even being able to see the Milky Way. That would have been fantastic to see back in the day, certainly. But one of the things that probably is a little bit obvious from seeing this is that there isn't any Uranus or Neptune. And that's because, well, it took several hundreds of years before we even actually got to see Uranus and Neptune. We were pretty much struggling seeing them without any kind of optical equipment. And so it was only until pretty much, I think, in the 18th century, if I remember how you say centuries correctly. Before William Herschel, Caroline Herschel, and as we were mentioning with Charles Alexander's work, to make the discovery of Uranus possible, where he first thought this was actually a comet within his observations. Uranus itself is an interesting kind of planet. It's not as big as that of Jupiter and Saturn, certainly. Comparing it to Earth, it's only about 4 times as large. So it's not as giant as some people I know think it is. But the thing that kind of astounds me, at least, is the fact that it's over about 1.8 billion miles away, which is about 2.9 million kilometers, which puts it about 20 AU, which what I mean by an AU is that's the distance between Earth and the Sun. So 20 times that is that at Uranus. So it's pretty far away. Because of this, it actually only receives about 0.3% of the light that we have here at Earth. So we'd imagine it's pretty chilly with that, though I shall highlight on that part because it's quite interesting on that fact. And because it's so far away, we actually don't have, well, the light from the sun actually isn't received at Uranus until about 2 hours and 40 minutes later, rather than the 8 minutes that we have here at Earth. So again, kind of astounding to imagine that it would take 2 hours and 40 minutes to get to Uranus, then 2 hours and 40 minutes to get back. So yeah, it's outstanding stuff, really. Because of this distance, we've really struggled to get much data or even like a full understanding of Uranus and even at Neptune. So what we have really done in the last century is by trying to obtain those data, we flew Voyager 1 and Voyager 2 satellites, which both went in 1977, to basically go around the solar system on this grand tour, which Henrik has highlighted here, was only really possible every 178 years. So basically 2 to 3 humans' lifetimes. And the reason for that is basically the positioning of the planets in the solar system, which allow for us to complete there's a specific word and I have forgotten it just at this moment, but for us to do a slingshot or have a assistance through gravitational assistance pull from the planets themselves to be actually able to see all of the outer planets. It certainly was an ambitious project for its time, and touching on similar themes as yesterday, any satellite or orbiter or even probe that we send out to the outer giants is going to take a very, very, very long time. We were saying yesterday about 15 years, and it took, I think, just under that for these Voyager 1 and Voyager 2 spacecrafts. But again, that was due to the orientation of the solar system at this time. Henrik has made sure to highlight that it came, well, the year that we actually sent the Voyager probes out, Voyager 1, the Voyager probes out was back when Star Wars first released. So for anyone who's back around then, I'm sure you heard about it. So what do we hear from Voyager 1? Well, back with Jupiter. Yes, well, what we heard from the Voyager probe, sorry. We gained a lot of insight at Jupiter and Saturn. And sorry, the sun is making its way in, so I'm currently being blotted out by the sunlight on this end. But what did we see from Jupiter itself? Well, we had the biggest surprise at Jupiter was the fact that we observed Io. Io itself was actually a massive surprise, the fact that it was such a volcanic moon. At the moment, I think my understanding is that it has about 1 ton of plasma every second. I think that is. Feel free to correct me on that. But it was the surprising thing, it has such active volcanism, which was pretty much the first time we'd ever seen kind of volcanoes, well, active volcanism, apologies, on another body in the solar system. Equally, we got pretty much a jaw-dropping view of the Great Red Spot, which we were able to observe a lot of atmospheric conditions and understand how the atmosphere moved into the patterns that we know as the belts and zones and how those kind of interacted with the Great Red Spot as well. Additionally, and key to kind of what we're looking at today, we saw the northern aurora. You can see just in this picture, just to the right of on the Jupiter, half the slide, where scientists began to perhaps decipher where these northern lights could have come from, at the time linking it possibly to the plasma that we saw at Io. But again, that was a further discussion down the road. And lastly, we got a look at cloud top lightning at Jupiter, which is incredibly similar to the top atmosphere lightning that we see here at Earth. At Saturn, back in, well, a good couple of years later, we had a much closer look and saw the structure of Saturn's rings, actually able to discern that there were gaps in between, which at the time scientists thought were due to satellites basically interacting or creating these gaps due to tiny satellites, as mentioned. We also got a great view of Titan, which is Saturn's largest moon at the time, with the thickest, or very thickest, incredibly dense atmosphere, which previously we thought, oh, it was the largest satellite in the whole solar system. Turned out the majority of that was due to the fact that we just couldn't see through the atmosphere itself. So when they did take detections of Titan, they found that it was actually a little bit smaller than Ganymede, which is Jupiter's largest moon. So an incredibly wild kind of place. And finally, we got to observe Enceladus's surface, which we found about 5 different types of terrains. So it appeared incredibly spherical in shape. And one of the most interesting things, I think, for myself, was that it was, along with it, and I believe 3 to 4 other of the moons at Saturn are almost entirely made up of water ice. And because of this, actually reflects a massive amount of the sunlight, making it incredibly cold. So we then go on to looking with Voyager 2, which, again, as Henrik has pointed out, came out before the Comic Sans font, which is what we're using in this slide. So what did we really get from Voyager 2? Well, the first encounter with Voyager 2 with Uranus, at least, was in late 1985, I think November-ish, though up until about January, February time of 1986, though it is widely kind of, it's very picked up on that the main focus of Voyager 2, or a lot of the data that we came in contact with, the densest amount of data we got from Voyager 2 came within like the 6 hours of closest approach to the planet. So I would not be surprised a lot of the papers that we have from it come within this small window of time. During the flyby, we discovered 10 new moons at Uranus, which I think took it up to about just under 20, possibly about 15 or so, where we took the highest resolution of highest resolution of images, of the moons at Uranus, for example, such as that of Ariel and Miranda, along with Umbriel, Titania, and Oberon. We also were able to find that Titania and Oberon were about half the size of our own moon, so that was pretty spectacular to see. We also got a much closer look up of the rings at Uranus, which are, I think we were mentioning yesterday, are incredibly difficult to see from here at Earth. So it's fascinating to be able to get an actual close-up look of how these ring systems worked. Additionally, they were all able to be photographed, as you're seeing kind of an example here, but also they were able, for the first time, to be properly measured. Additionally, one of the interesting things that they did find was that there were incomplete rings and varying opacity levels, which led to scientists believing that the ring system itself was actually relatively young within our solar system. And then finally, the haze that we saw at Uranus, we noted there was definitely a higher layer of haze known as the photochemical smog, which was detected at the poles. So it certainly kind of led to a very fascinating view, which the last time we got to see with Voyager 2 can be seen here on the right before it headed off to Neptune to discover some more science. This kind of leads on to more in our area, where we focus on the magnetosphere and the magnetic field of Uranus, which the Voyager 2 probe found a lot of interesting stuff. One of the key things we found was that Uranus's magnetic field was actually tilted by about 60 degrees, about 59, 60 degrees from that of the rotational axis. I don't know if this is going to repeat. No, I'm going to have to press it play. So the dark blue arrow you're seeing here is actually the magnetic field. I'm trying to think, but it's the magnetic field vector, as we call it, but it's the direction of the magnetic field in comparison to the light blue arrow, which is the rotational axis. So it leads to a very weird and wonderful kind of magnetic field interaction with that of the atmosphere, or what we know as the northern lights and the southern lights. Yeah, sorry, I'm making sure to go through my notes correctly. So in order to actually observe the aurora as well as other atmospheric effects and interactions, we need instruments to do this. And on Voyager 2, we actually used a very large collection of instruments, though some of the key ones for our investigations are with the telescopes, which we found kind of on this top right side of Voyager 2. When looking for the aurora specifically, for example, we used what was known as the UVS, or that's the ultraviolet spectrometer, in order to document the auroras. Sorry. It is also with these telescopes and instruments, we actually got a better insight of the temperatures at these planets, as previous to this, and I'll bring this up in the next slide, we expected Jupiter, Saturn, Uranus, and Neptune to be fairly cold. And again, that's picking up on the point I mentioned before, is that they actually receive a lot less sunlight than we do here at Earth. However, whilst the Voyager probes went by, we actually observed incredibly hotter temperatures, and we're talking hundreds of difference, which really scratched everyone's heads, not only for the fact that we're just seeing something different, but trying to then go, okay, there's this difference. Why do we have this difference? Where is that temperature coming from? Where's that energy coming from? It can't be from the sun. So what else is driving this? And if I'm being honest, at this point, it is still kind of a fairly open question at these planets. We have been doing our best to solve, as we have called it, basically this energy crisis, where we have this loss of energy. Well, I say loss, we have this gain of energy, and we don't quite know where it's come from. There are current investigations. One good couple that James has been on actually have been focusing, or James has led himself, I believe a paper this year looking at the heating of the aurora, which is actually perhaps causing this increase in temperature, especially looking at that of Jupiter, where we've seen temperatures peak at the aurora, and perhaps the energy is dissipating towards the equator of the planet. Additionally, with HD+, we've also been investigating the Great Red Spot at Jupiter to see if this perhaps, I can remind myself exactly, that perhaps it is the Joule heating that we're observing above the Great Red Spot that is dissipating energy into the surrounding system, or due to gravity waves, or even lightning-driven acoustics. So a lot of fascinating and interesting theories that we're still kind of going into discussions with. So when trying to decipher some of these mysteries, or trying to investigate, especially when it comes to the aurora and even looking at temperatures and the atmosphere itself, we use a lot of telescopes. And today's telescope that we're doing the investigating for Uranus is with IRTF, which is the NASA Infrared Telescope Facility, which is found on Mauna Kea in Hawaii. I will apologize, I have not actually been myself. The start of my PhD was about six months before we went into lockdown here in the UK. So I am hoping in the next year to 2 years of my PhD that I will be able to go out to Hawaii and enjoy that. But for the moment, this is as close as I've possibly been myself. I think we mentioned yesterday that IRTF was actually constructed with the leftovers of the NASA budget from the Voyager probes. Again, feel free to correct me if I have that wrong. But it is used to support planetary science investigations such as the ones that we're doing today. Here we see an insight into NASA IRTF, and today I'll be showing a couple of the videos from inside NASA IRTF, which kind of shows you how the telescope operates. It's certainly a very fascinating telescope, and I would imagine being in person completely dwarfs the expectations that you have there. But inside NASA IRTF, there's actually, if I remember, 3 to 4 instruments. There might be a 5th. I apologize because I have mainly seen use of 2 myself. One of these being iShell, which is the instrument that we're using today. iShell was mounted on IRTF back in 2016, with its predecessor being C-Shell, which we used in our own investigations, and that's to look at spectra. Spectra is essentially the investigation of light coming from a source, whether that's a planet, a star, a brown dwarf, goodness, there's so many so many things that you can investigate in the solar system to basically look at the light. But weirdly, light actually tells us a lot, especially when we have what's known as a spectrograph, which basically takes in light and divides it up into its wavelengths or individual colors. Best way I've found to describe that is imagining if you have a prism where you take, your, I guess, a white light in and basically causes the colors to spread out. So in essence, we are spreading those colors out and then far beyond colors that we, with our human eyes, actually can't see. Ice shell itself specifically operates within the near infrared wavelength spectrum. Today, we're going to be focusing about 3 to 4 microns, where our main focus is actually going to be about 3.9 to 4 microns, as that's the wavelengths where the molecule we're focusing on today, Hc+, comes into play, which I will comment on a bit in a second. Apologies, I'm going to have a quick drink. Oh, goodness, good. So, a fun little insight we have for ice shell is that the imager for ice shell, that's where we get to see the planet and make sure that we have everything in the right place, is called Kyle, and the spectrograph is called Cartman, which, yes, is based off of South Park. Additionally, on top of this, we also have Ike and Kenny, and I do believe there is a bit of code, which if everything does break, then we do have an oh my god. I'm sure the rest of you know the rest of it from there, and I don't want to cause any trouble, so I'm gonna stop there before I continue. So yes, so what are we investigating today? Well, we're investigating with H3+. It is a molecule with 3 protons and 2 electrons. The rough kind of molecular structure can be seen here at the top rightish. It's an iron molecule that is predominantly found within the upper atmosphere of pretty much all the gas giants in the outer solar system. Predominantly because of the atmospheres that these planets are typically made out of hydrogen and helium, so it's very easy for H3+ to form due to interactions between hydrogen molecules. By observing the light from H3+ when it becomes excited with a spectrograph, we can actually determine physical properties of the upper atmosphere of these planets, such as the temperature as well as the density of the upper atmosphere. So that means like how many molecules are in the air. So as we kind of nickname it, it's kind of like a probe into understanding how the atmosphere of the planet works, as well as kind of the goings on that we see. So the history of H3+, well, the first ever detection was with Larry Trafton back in 1992, although he wrote the paper, I think, in 1993, which actually confirmed that H3+ was visible at Uranus. I think this was even before that we got, I think just a couple of months before we got a confirmation that we saw H3+ at Saturn. And it was incredible during this time. I would have loved to be during this time where we were seeing H3+ at Jupiter, and then it would have been Uranus, and then it would have been Saturn, and everyone just dying to see if we could find it at Neptune, which is still an ongoing mystery there. Hopefully James Webb Space Telescope may be able to provide us some insight to that. But obviously we started back in 1992, which is, it's been a while since it was 1992, and we've kind of continued investigations from there. Henrik has diligently, pretty much from, he wasn't there back in 1992, but has been taking the data since 1992 and onwards, constantly recording Uranus's temperature, or upper atmosphere temperature, to investigate what's going on. And it's been really peculiar. We've actually observed 30 years of continuous cooling. All the way through that, we kept thinking that perhaps Uranus may increase its temperature due to it coming out of equinox back in 2007. And making its way towards winter solstice, but that didn't happen. So we then thought, well, perhaps it is more to do with, I think, the positioning of where Uranus is in the solar system. And again, that got thrown out. I think there was a magnetic field, perhaps delay. And again, that theory got thrown out. I think the current theory at the moment is that we believe that we had the hottest time at 1986, and we're continuously cooling perhaps until 2028, where perhaps it'll be its coolest, and then we'll start to peak up again. But until we reach 2028 and confirm that we see those increases in temperatures, it's just a theory at the moment, and we've certainly got a bit to wait until we can fully put a pin into what's going on with Uranus. So today's setup with NASA looking at NASA IRTF, is that we'll see Uranus well, we're going to be lining our slit up with Uranus's north-south rotational axis. We can kind of see the slit layout here as Henrik has so kindly done for me. Uranus itself will actually move along the slit, basically in a process what we call nodding. What we mean by that is there is a position and there is a B position, and we basically move Uranus from A to B, B to A to B, B to A. The reason we do this is to remove the effect of the Earth's atmosphere. The Earth's atmosphere is really terrible to actually see through. It takes up or pretty much causes almost like best way I can call it is a curtain over the whole solar system, so you really can't see through it. But it stays mostly consistent through the night, as best as consistent as we can make it. So if we can basically take two pictures where we have the atmosphere in one and the effect of the Earth's atmosphere in one, but not the planet, and then the planet and the Earth's atmosphere, -1 from the other, we can basically effectively annihilate the Earth's atmosphere from the image and just get Uranus, which really helps when trying to take data. On top of that, you'll probably see little dots around Uranus. It's possible that these will be either the moons. You'll be able to just know if these are the moons, if they're actually moving along or moving around that of Uranus. Whilst you kind of see in the background of this image is, I think Henrik mentioned, was either possibly a galaxy or a comet, or at least something that is emitting in the same spectrum that we're doing with Kyle, our imager. Sorry, we've got a cat in the background who's decided she's done with the rest of this. We take the information from the slit and we put that into the spectrograph. That's the prism, in essence, which basically shows us the lines of HT plus at specific wavelengths. HT plus kind of picks specific, because of its composition, it produces emission lines at specific wavelengths, and that's where we can actually get an idea of the amount of light that's being emitted across the surface of the planet under the slit itself. But by comparing these lines, we actually get an idea about the temperature in the upper atmosphere, and comparing the expected intensity versus the intensity that we actually got, or the amount of light that we actually saw, we get a good idea on the density of the atmosphere of the planet. Finally, we want to kind of key in on one of the topics that's going to be talked about a lot today, which is the James Webb Space Telescope. It will be the most advanced telescope that we've ever built, and are hopefully launching it out for 18th of December 2021. At the moment, here at the University of Leicester, we have a lot of observations lined up for the James Webb Space Telescope, which will cover Jupiter, Saturn, Uranus, and even Neptune, which are planned for 2022, where hopefully we will get even better images than we're actually seeing here at Earth, because we're not being obscured by the Earth's atmosphere with sending a space telescope. So I think it would be a shame, because I know that I will be graduating, finalizing my thesis during that year, but I'm hoping I can still be on board to see some of the results, and even refined pictures that we're going to have from James Webb Space Telescope. I think one of the topics, though, that the James Webb Space Telescope is certainly, I believe, larger than that of IRTF. It's not the largest telescope we have. We certainly have larger here at Earth. We have the 30-meter telescope, the extremely large telescope, or ELT, and the giant Megalia telescope, which we're able to do observations with. I don't know if we have any data ourselves with those, but that would be great if we ever could. But unfortunately, as great as it is to have ground-based telescopes, at the end of the day, us in the ice giant community are desperately crying out that we can have a mission to Uranus. Highlighting before, I mentioned with Voyage 2, that is the first, the last, and the only visit that we've ever had to Uranus back in 1986. And as someone who wasn't around then, it's almost a little disheartening that we really haven't sent anything since. And equally, I think it's such a big stress on the fact that it is a mission that is going to take generations. It will take a generation to construct the mission itself and get the ideas of the research that you want to do. It will take almost another generation to send out the instrument to Uranus and have it actually deploy, if it's an orbiter, orbit around Uranus. And then I would imagine then another generation to start going through the data and actually building up probably the best picture that we've ever had of Uranus since we first discovered it. And I should highlight, obviously, we do still have Voyager 1 and Voyager 2 making their way out. They have now gone past the heliosphere, heliosheath, apology, past the heliosphere, past the heliopause, and past the heliosheath out into solar space. So it's not to say that we can't rely on the old stuff. They are still giving us the incredible amount of information that we do need to understand our solar system. So I think the main point we really want to take from this is we do have our own orbiters that we should remember that they last for such a long amount of time. They're incredibly important. The data they give back is so useful within the space environment, space community. Even right now, I can't imagine all the possibilities of scientific discoveries that we've made with the data that we found that we didn't even realize that we needed to find, you know. So overall, really, we're going to highlight back to, as Edric has pointed out, going back to HD Plus being one of these areas that for the meantime, we're hoping to kind of focus on using HD Plus to really define and get a better understanding of our whole solar system. And we hope today that you're all kind of engaged with us as we use HD Plus to hopefully look furthermore at the infrared aurora at Uranus. I'm going to stop there because I think that is the end. There we go, and I'm going to bring up now, hopefully we are starting our observations at Uranus. I think I've been given the heads up. Apologies, I need to flick over my screen. There we go. So we are just at the moment, I can see if I can pin. There we go. So at the moment we have now made our way over to Uranus. I think we're just finalizing the setup here. So we don't have the emission lines at the moment. We'll probably be zooming in once we have a better idea. At the moment, the spectrocam has, as I mentioned before, has Cartman, whilst Uranus has the view from Kyle. In the spectrocam, we're basically seeing all of the wavelengths from about 3 to 4 microns, which it's a lot of wavelengths that are in Cartman, so don't worry too much on that. We'll hopefully be able to show some emission lines a little further. Also in this image, we have a picture, well, we have a GIF of about 8 hours inside of IRTF. So hopefully you remember the pictures that I showed earlier, which has the IRTF telescope, and that just kind of gives you an insight as to the engineering that goes on with IRTF, where they have to make sure that the telescope still can operate for nighttime observations, but as well giving you an insight of the telescope operating within the nighttime and trying to take data during that. Finally, we have the sky above IRTF, which I think is from last night now, the view over about I think about a 12 to 14 hour time lapse. So this isn't the sky at the moment over IRTF. I need to double check if the link still works on my other slide that I have for this. If it does, then I can click over to that and give an actual idea of what is above the telescope today. Oh, sorry, so that's everything that's on this slide to give kind of an insight what's going on. I will briefly discuss a little bit about what happened yesterday. I won't have too much to add, unfortunately, because the data reduction side of things takes an incredibly long time. I did try and give it my best go last night, but unfortunately I wasn't able to pick out anything. Well, I wasn't able to detain anything useful from the data just at the moment. That's not to say there isn't useful data. That's just to say that coding takes a lot of time and a lot of patience, and I only had about an hour and a half to try it last night, and I just didn't have the time, so I'll apologize. I don't have anything shiny to show on that front, but I do have the video from last night. There we go. So just what we're seeing here, so this is the video, the view that we saw from Kyle, which you can see hopefully Uranus, which is here in the just off the middle in bright pink. Around it, you can almost see the rings. You can't see as much definition as we'd love to see, such as that with Saturn, but we can kind of see the rings around Uranus itself. We then have, if I remember from last night, Umbriel down at the bottom with Ariel just at the top. I'm not sure which moon that we're actually seeing just on the side at the very beginning of the clip. I believe that might have been Titania. I think we had discussions of that last night. And the small little moon that you can just see it is incredibly faint, unfortunately. We believe it's Puck that's kind of moving around incredibly quick around that of Uranus. But that is last night's observations in about 13 seconds of moving. And that's about 8 hours. So you can imagine how there's a lot of images in this, but it's incredibly quick.
Hi, Emma. I think that was fantastic. I just want to, did you just say we could see Uranus's rings in this image?
So I think you can just about see them. Again, it's going to be difficult to show on the Zoom.
I do know.
But the hue around the planet, the slightly greener hue, is the rings.
I can see that. It's so exciting, and I didn't know that if we would be able to, because you need to have a certain orientation and to be able to see them. Or I don't remember if we saw them yesterday at all.
So it's difficult to see in the imager. The coding that we use helps refine that a little bit, but it is because the imager that we actually see today is more of the raw form than anything. So what we then take in helps a little bit to try and actually kind of see some of the details going on.
So this was processed overnight or something, or because you did say this was yesterday's video. Well, that's fantastic.
Yes. So I'm hoping to do the same thing with today's observations and basically make another film for tomorrow to kind of give the insight of what's going on. So at the time it didn't feel like it, but actually going through the whole film, we can see how the planet's kind of moving around that of Uranus. It's quite fascinating here being able to see that.
It is. Absolutely. Thanks for sharing this. I'm sorry. I just wanted to kind of give you I wanted to check in with you if that was actually what I thought I heard you say, that those are some rings. Really cool. Thank you.
All right. I was just going to finalize on, and this is where things get a bit artsy because unfortunately I didn't make a slide for this. So I'm just going to share my screen with the, basically with what's our best view, I would say, a complete view of Uranus's Aurora that was back with UVS back in 1986. So I bring this up. I apologize in advance. I don't mean for this to be an art class. Let's see if I can plug in. I don't know if I can plug in a mouse. This is going to be by hand. So last night we thought we saw 2 peak points of emission, one at the beginning on the very edge of our slit, and one about the middle point of the slit. Now, taking James's animations, actually I'm going to stop sharing and I'm going to quickly share my other screen. Here we are. So with James's animations, if we imagine we have a rectangle over this, at some point I should just animate or just put in a rectangle myself, but you can see here the North Aurora is actually very close to the very edge of the planet. In comparison, the Southern Aurora, which is the red dot that we're seeing here, is more close to the middle of the planet. So for us, if we see anything lighting up at the edge, we're pretty excited that that's going to be the Northern Aurora coming into view, whilst anything that's more towards the middle of the slit itself is more to do with the Southern Aurora. Though it's hard to tell with the actual raw data itself, it does require a bit more investigating, and I'm hoping in the next week or so, perhaps we can start investigating, getting a better idea on that. So going back to the art project, what I'm meaning by this, or the reason I have brought this up, I promise it's not a tangent and I'm just trying to show off my art skills, but my thinking at the moment is that we may have seen anywhere, goodness, it's a fun rectangle. I'm just going to have to do it as an opaque rectangle, I'm so sorry. We'll do this in red. I'll see if I can move, there we go, yeah, new layer. So roughly we see about 150 degrees every night. At the moment, we're not able to see the North Pole. We're only able to really see the South Pole at Uranus. So if I get my rough degrees, so I would imagine it's roughly there-ish or so. Again, we're going to take that opacity down so you can actually see behind it. So this is roughly our field of view that we've covered. Uranus, again, this is a very rough approximation, but my thinking is we saw the Northern Aurora and Southern Aurora may have been that we observed about this section of Uranus. But equally, because of the rotational error of Uranus, what I mean by that is that we know that Uranus rotates every 17.24 hours, but there is a plus minus error of 0.01. Again, that doesn't sound like a lot, but it means that every 3 years we actually lose any idea of what's on the planets. So we actually end up with an error of about 360 degrees. And because of this, that means that we can't get a great idea of where anything is on the planet when it comes to its magnetic field and the auroras. So investigations like these are what will hopefully allow us to refine the error from 0.01 down to 0.05, perhaps even lower than that, to the point where we are able to confidently say where the aurora is at all times. Our colleagues in France are pretty much leading that at the moment, and we're hoping to join them in being able to give an infrared insight to this, rather than, I think at the moment the leading is more with ultraviolet.
This is amazing. Thank you. That's this is what I was asking. I think I asked you a question about this, like, what are the landmarks? How do you know what you're seeing? And you mentioned you look for the moons, but I was really wondering, how do you know where the aurora is at what time and all that? And so that's a really helpful diagram that you just shared with that square to show us what we were observing, what actually maybe what you think you're observing. That's difficult, because then you have to basically just look at the data and see what you get, then from that figure out what actually you were looking at. Is that right?
Yes. So basically some of the data that I've been using over the last year, which is back from 2006 when we were very close to equinox, has been myself essentially looking at those lines, finding out how much light is in that line for that 1 pixel, and then going, okay, that roughly covers between this amount of degrees to this degrees, from this degree's longitude, from this degree to longitude, and then next pixel, and then next pixel, and then next pixel, with about 150 sets of data. Thankfully, coding is wonderful at sorting that, so I don't have to manually do it. I just ask the code to do it, but it does take a lot of refinement.
What's so interesting about this is it just shows us how difficult it is to study these gas giants. I mean, I suppose Jupiter, you've got lots of landmarks on the surface at least, but Uranus and Neptune, for instance, maybe Neptune, there are some clouds I think that you can see, but there also are bands there. I think Dr. Fletcher talked yesterday about. So I guess if you're looking at a different wavelength, you could sort of see through the clouds. Was that so on Uranus as well? Do you remember?
Well, Uranus itself is quite featureless from what I remember. There are clouds in general, because I believe Lee mentioned that specifically. I think it varies depending on which wavelengths, on exactly where those features kind of stand out. Unfortunately, I'm going to focus a bit more with what I know with HT+. With HT+, it is very difficult. Main reason for that is the interaction, or how HT+ actually emits. Is due to 2 processes. One is due to the interaction from the extreme ultraviolet radiation that we get from the sun, so essentially the glow of the sun, which thankfully doesn't really emit on the night side of the planet, because there's no sun on the nighttime, thankfully. But usually we don't get to see the night side of the planet. Usually we only see kind of the part that's being lit up by the sun. So it means that any other interactions have to compete with what's being emitted by the sun. So in this case, that is the second interaction. So that's with energetic particles, such as the particles that flow down the magnetic field lines and create the aurora.
So since we know what kind of light we're getting from the sun, I'm assuming you just subtract that out. Is that what you?
Yes, you can just like what we normally do is we'll take a approximate mean of what we believe is data that doesn't have the aurora in, and we'll basically, what I'm doing at the moment is taking that out to then leave basically areas that are peaked that we can't explain with the solar side, that they are fluctuations that are unexplainable by error, unexplainable by the processes. And usually that's what we're doing at the moment, to be like, yes, we're actually observing points here where we are fairly confident that they're aurora, but it's interesting because with ultraviolet, it's usually there's a very different process that goes on with ultraviolet observations with Uranus. Laurent goes for the angle where he will look at ejections from the sun and look to see if the aurora has basically blown up in light like a firework almost and gone, hi, I'm here for a very small amount of time.
And is that because like it's affecting the magnetosphere of Uranus? Is that?
Yeah, so similar to when we have a lot of solar activity thrown at Earth, the aurora will move down well, I say move down, but in the sense we get a lot of magnetic fields, sorry, a lot of plasma thrown our way from the sun, which causes the aurora to basically brighten up. I don't know, actually, I should comment, I think it does, but again, feel free to unquote me on this, that the aurora moves up and down, obviously, the Earth in the latitude. So there are times where we can see the aurora at Scotland if we're lucky enough. And again, that's due to the fluctuations in solar activity.
Well, something you just said got me so excited because I think about when I don't know how much we've been at a solar minimum. I know last year, so there wasn't a lot of activity on the sun. I know there's some sunspots happening now, but when you said when there are these coronal mass ejections, that can possibly excite the aurora on Uranus. So who gets that observing time when we are expecting something like that? Is that like prime?
So this was something something I discussed in my first year, because I remember seeing Laurent come up with this idea, and I was there like, oh, this is incredible, actually, because I had previously done work with coronal mass ejections, and I was like, yeah, this is a great idea. This is what you should do. Unfortunately, with infrared telescopes, you have to ask for your time about 6 months in advance. And you just have to pray there might have been something, but at the same time, you can't rely on it. So we don't normally coordinate or, pray and hope to the science gods that there might be one. Whilst with UV, they can have the time where they're able to go, hey, in about a week's time, we're going to be seeing possibly a coronal mass ejection interact with Uranus. Could you give us 3-4 hours for us to see what's going on? Or sometimes even 2-3 days. Just because, again, sorry, I was going to say it's a weird thing for Uranus at the moment. Again, this goes back to the fact that we haven't had that many satellites go out to Uranus, so we aren't fully sure on how the solar wind travels past Jupiter and Saturn. So in terms that basically what that means is there's a very large error, I think about a day, 2 days on exactly the arrival time of when these big shocks occur at Uranus. So you have to be a bit flexible in terms of your days, because you may not see it on one day, and if that's the only day you've put in for observing, can't see anything. It may have come the next day, who knows, you might have missed it, it may have been the day earlier, so you have to be a bit flexible on the timings there.
So you just kind of roll the dice to try to get that perfect time. Lucky astronomer, but they could be pointing that telescope somewhere else. They might not be looking at Uranus. I mean, so that's kind of, I guess, par for the course for an astronomer. He's trying to get time on a telescope and observe some, groundbreaking data observations. Yeah. Oh goodness, I wish all astronomers got their own telescopes.
Goodness, I think we'd run out of space for anything else if all astronomers ended up with the big fancy telescopes.
So I did want to kind of connect a couple of questions on YouTube, just because this video you're showing from yesterday is green, and someone on YouTube was asking, is Uranus really green?
Oh goodness, sorry. Okay, so we just went for this color scheme. It's actually a movie made on Python. We went for this color scheme just because it was easiest to actually see the moons themselves and like the shape, because usually they are just a round dot than anything. So the color is artificial. It's just the coloring that we've gone for. I can do a grayscale one, but I feel like that's going to have questions, people going, is it really, gray? So apologies, no, it's not actually that green. And what we know from the images is that Uranus is actually quite blue, and that's due to the methane within its atmosphere, which basically causes it to reflect blue light.
Excellent. There are lots of questions, but I just wanted to, sorry to interrupt you there if you want to continue on, but I left some questions for you in the chat if you find them, and answer them when you're ready. And there's some in the Q&A, and I'm happy to just yield to you to answer those at your leisure.
Yeah, I'm just trying to think. which question should I answer first? So go for the Zoom ones first and then go for...
So there are questions in Zoom in the chat that I copied over from YouTube.
Oh, okay, apologies. Thank
you don't have to go to YouTube. So I tried to make it easy for you, but then I didn't triage them. So John's the one who asked about Uranus being green, and you're right. Yesterday it was pink.
Yes, exactly. It dramatically changes as we go. So when McNaull asking, why is the gas layer considered part of the planet rather than the planet's atmosphere? So I believe that's with Titan, back with Saturn. So back in the day, when we were looking at the planets, such as looking at Saturn's moons and whatnot, because the atmosphere was so dense, we actually couldn't see past it. So our initial deductions were, well, we weren't too sure what was going on. So we just had to deduce, okay, we see this sphere, the shape of a moon, and it starts from here and starts from there, and it was the largest that we'd actually seen in the whole solar system as a moon. So at the time it'd been measured as the complete diameter. It was only with the Voyager missions that we were able to go, actually, it's not that's not solid. That's actually the atmosphere. It's just incredibly dense atmosphere that it was seen as part of the moon itself.
I am just going to interject here with a question from YouTube that just came in because they want to know, Oliver wants to know, will we be able to see the live image from the IRTF today? I was just wondering, have we connected with it yet? I don't.
Yes, we have. Let's see if I can get it up. So this is what's going on at the moment. We're just in between a transition between A and B. So again, I promise this isn't Uranus suddenly duplicating. There we go. We've transitioned back to an A position. So I was mentioning before, there's a nodding of the planet along the slit. So we're now in the A position for Uranus. If I recall correctly, because I went to go quickly check on a very useful website. If you look up on Google Uranus Viewer, you can put in basically today's observation dates, approximately how much you want to see of space, and you get a great idea of how Uranus, the rings, as well as the moons around Uranus look like at this, at the point right now. So I believe, if I can get my mouse out, start having a look around. There we go. So there's two mouses. There's the one on the actual us doing remote observing. That's the black one, and the white one's myself. So we have here the two inner moons. We have I believe this one just here is Miranda, and then followed by it is Ariel, and just at the very edge is Umbriel. Again, actually, no, Umbriel and Ariel are both there now, back at the outer edge. So we're saying hi to them both again today, with Miranda now making its way in rather than with, actually, no, it was Miranda yesterday as well. Apologies. So same moons as yesterday. So nice to confirm them again. And yeah, hopefully we'll be seeing their rotation around Uranus whilst we do our observations today.
Excellent. I'm happy to feed you questions if you want me to. So let's see. Oh, there's some other questions from John. I can go in there. I'm not sure which question. And if we can't always answer all. We don't always have all the answers. So if we don't have the answer, not a problem. Let's see. Uranus shine. Okay, this is more about, does it make everything green on sub-Uranus, side of moons at long nights? Sub-Uranus. I'm actually not sure the question. I don't know if you.
I'm not sure. I think the question is possibly in line with the fact that it was green in the film, and possibly does Uranus have a light? Like, does the reflection of light from Uranus from the sun reflect onto the moons? I guess.
Okay, I'm going to move on. I think that. Thank you. I wonder. Are you familiar with the? I mean, not. Of course you are. I'm sorry. This doesn't mean to be a silly question, but maybe you haven't observed from there yet the extremely large telescope.
Yeah, I did see that one. So I am aware of the extremely large telescope, but I actually haven't used it. Dr. Rosie Johnson, who was with us yesterday, has used the very large telescope. So that's a step down from the extremely large telescope. But yeah, she had an incredible time being able to take data with the very large telescope, along with Henrik has also taken. But myself, I have not had any time on the very large telescope to look at these planets. It would be great to look at the astronauts with it. Yeah. But again, the very large telescope and the extremely large telescope are incredibly competitive. What with being so large, especially the extremely large telescope, I would understand entirely if more of the focus is towards planets that are beyond our solar system, because they need the increase in being able to actually see things than us at Uranus, where we can use these telescopes to try and obtain some data.
So I don't know, we could always hold off on this question as well, but I think you did mention it, and you did a great presentation with Henrik's slides. I thought that was fantastic overview of Uranus and what you're doing. Thank you so much for that. Jarek asks, why and how did it happen that rotational axis of Uranus is almost perpendicular to its orbital plane?
Goodness, yes, that's a very, very good question.
we'd like to know too, Jarek.
Yeah. So I think Tom and Henrik and I think even Lee may have touched on this yesterday, but there are a lot of theories that are going around at the moment on trying to figure out exactly the cause. I think one of the leading ones at the moment is that there is, okay, this may be pulling an answer from nowhere, so again, but my understanding from what, at least from the animation that James has provided and discussions with Henrik and Tom on this, there was at some point in the past, I guess similar to what happened with the Earth and the Moon, a collision with that of Uranus, which basically caused everything to be mixed around and caused the weird rotational axis, I believe. I'm not too sure on the magnetic field axis, why that is rotated just as much, about 60% as much, it's about 60 degrees rather than the 98 degrees that we have for Uranus's rotational axis. But it leads to a lot. There's so many fascinating questions, if I'm being honest. Yeah, this one, sorry. I was gonna make my way over to it, but yeah, this interaction.
Yeah,
this is one of the impacts that we have.
It's so great to have. I mean, James's animations. It's incredible. You know, in his bio, he wrote that he does this so that the public can better understand these things. And I am a very visual learner, so these animations are very helpful to me to understanding what might have happened, or what's possible, or even understanding, you know, the tilt of Uranus and where the aurora are. Because I think until you mentioned it once when we were in a chat earlier. In the static image you shared from a paper, I saw that those were these two splodges that weren't at the poles, and it was so incredible. James said, "Oh, you know, I think I can animate that." And then, like less than 12 hours later, it seemed he came up with the animation.
Exactly.
So, great.
We appreciate your work, James. Thank you.
Yeah, very much appreciate it. Look forward to speaking with him later about all of that as well. A good question. I didn't know if there was, so just to give you an update, we have about, I think, 15 minutes until we're expecting Dr. Sean Prosser. Yep. So I can continue on with questions, and I just want to check in with you, Emma, if there's anything you wanted to say or do right now.
I don't have anything in particular. I did want to highlight, I forgot to yesterday, and it's incredibly bad of me, but we did also have my colleagues Riyang and Nahid on the telescopes. They have been diligently doing the work. I was supposed to be doing some of the main observing yesterday, but I got very distracted, so they carried that on, and I am incredibly thankful for their work. They are both a joy to work with, and I'm very annoyed at myself for forgetting to say that they both.
Thank you, Nahid, and thank you, Rang. Yes, thank you very much. And we had Nahid last year for Jupiter 2020. He did a great job at doing our Q&As. Thank you very much. Are we going to be able to? Are they going to join us today?
I hope they may be able to. The slight issue we're having is that to communicate with the TO, that's the telescope operator, we use Zoom when we're doing remote observing, and unfortunately you can't sign into Zoom twice into two different meetings. You have to leave one meeting to go to the other meeting. So I will see if we can grab them from in the other observing, but it may mean that I will need to switch from this chat to the other one, but do keep an eye out. Hopefully we'll be able to get them on. It'd be great if we could.
You know, Zoom is, I would just start another account with another email. they're free. You can sign up.
True, but they are using the laptops that we have from the university, which
So,
they're
yeah.
good for what they need to do, but I don't know how great they're going to be happy with 2 Zooms at the same time and all the observing going on in the background.
It's too much. I'm like just so impressed with how much you are able to do. I mean, I talk about having brain fog and what we're dealing with the last 18 months, and it's just amazing. I'm trying to sort out what I'm doing just to get up in the morning, but let alone do my job. And then what you're doing is like, all the things that you're having to do, especially under the pressure of being the PI for this research. This is sort of, you're trying to finish your PhD, so it's really so much pressure, Emma. You're handling it wonderfully. So really, you're doing a fantastic job, and thank you so much for sharing all of this with everyone. You got people from Thailand, other parts of the UK are joining in. Yesterday we have someone from the United States who's staying up late to watch this right now. And like I said, yesterday got 2.7 thousand views. You and Henrik were inspiring young minds. It's just thank you so much from the Royal Astronomical Society, and myself, obviously, as Education Outreach Officer. What you're doing here is so much more than, I know it's important to you to get your research and stuff, but you're making a huge impact by doing this. So, well, really good job. Thank you for being with us.
Awesome. Thank you for hosting us.
Yeah, I love this. I love Jupiter. We had so much fun, and yeah, looking forward to the next 2 days. I wonder if you want me to maybe kind of do a quick overview. We do have Charles Draper from the Herschel Museum who's joined us this morning. Good morning, Charles. We'll bring you on in a little bit at 10:30. Is that all right if I do a little kind of station identification? Emma, if there isn't anything you want to show right now?
I don't think I have anything just at this moment to share. I'm very happy to continue having the Spectra and Uranus cameras, but I appreciate if we're going to have Charles on, then I can duck those to the side.
Okay, I'm going to share my screen then really quickly and just say hello again from the Royal Astronomical Society. We are here and collaborating with other organizations. And I'm just going to do this. There we go. Of course, we are observing Uranus here with astronomer Emma Thomas, and this is her research and data that she's collecting through these observations, and generously sharing her very precious telescope time with us to view alongside with her. And she's from the University of Leicester Department, School of Physics and Astronomy. And then we are also working with the Herschel Museum and the Bath Preservation Trust, so we're happy to be working with them as well. This important work started with William Herschel discovering Uranus 240 years ago, and this is an astronomer following in those footsteps and continuing on to learn more about what can about Uranus and other gas giants. So let's see what we have. This is day 2. Today is Saturday. Trying to mind myself, not you. The 9th of October. We're going to be here all day until about 5 o'clock. Yesterday we ran late, and that's okay. We were just having so much fun. We were talking with a class of students at Westminster School, and they had so many great questions. So I didn't want to stop. And the scientists did a fantastic job. We had a full panel, Dr. Tom Stallard, we had Dr. Will Dunn, we had Emma Thomas, and we had Dr. Rosie Johnson. So if you haven't seen that, see it on Monday after you're done watching all the live observations. You can rewatch day 1 or check it out at the end later. Today's program, so this morning we've been setting up, it's 10:21 or so right now, and Emma gave us this fantastic overview with some slides made by Dr. Mellon. And if you missed it, again, you can rewind on YouTube and check it out. All about what the science is, what we're doing, and why they're looking at it. The missions that have been sent to Uranus since 1976, a date I probably won't forget. I hope I got that right. I think she said it because she said it was when Star Wars came out, and that was like right in my brain thinking that's the date to remember. Hopefully I got that right. She'll give us updates from the telescope atop Mauna Kea in Hawaii periodically throughout the day. We have Herschel Museum coming up next with Dr. Sean Prosser. Sorry, Charles Draper's name should be there at 10:30. And then we're going to have Sean Dr. Prosser with us afterwards. Coming up, we'll have Ophelia Wibisono as well today. Do a Q&A with the H3 Plus team. And I'm going to hand over the reins to Dr. O'Donoghue later today, because I'm going to only host half the day and sharing the hosting responsibilities with others. So, and learning a new thing for me as well. But they're going to be great. And again, if you have any questions, I know there's still a queue of questions in the Q&A that we haven't gotten to. That's okay. They're really great. We thank you for your curiosity and asking us questions. And I'm sure Emma and the team will get to them. I see Dr. Stallard has joined us as well. And so they'll also be working together to answer your questions. So hello, Tom. Hi, I'm going to stop sharing here and say hello to you. Good morning. How are you?
Good morning. I'm good. Thank you very much. I'm fresh back in from the telescope. So I thought I was duty bound to make sure that we got all the way to having an identification of a H3 plus line. And due to our own inability to see fuzzy blobs inside of noisy boxes, we weren't able to find it for a while. So we were making sure we hadn't done anything wrong. And the only thing we'd done wrong was look in the wrong place on the spectra. So eventually the old hand figured out where the line was supposed to be, and I managed to confirm that we were looking and we were starting to see H3 plus come through. So I thought that was a good time to come back over to you guys.
I was going to add, I think I can see the Q3 line there as well.
Is it on the screen?
Yeah, we can see both lines.
I currently have it on the spectra one. I'll see if I can.
Yeah, I'll let you handle that.
Shift that a little.
So why don't you perhaps, I guess, maybe point that out. We still have 7 minutes until Dr. Draper is on, so I'll
okay, this is back to me technical fun of adding in the fun circle as last time. Hopefully it's I do regret now making it red because it is rather difficult to see it, but hopefully I can point it out. So we have our Q1 line, and that's there.
Surprisingly bright, given that we couldn't find it, but there you go.
It's true, but I would expect it about now because we're coming up to about an hour on Uranus. Yeah, which we were mentioning yesterday. It takes about, for us to confidently get data, about an hour to 90 minutes at Uranus these days to get a set.
So it maybe looks slightly asymmetric. It's hard to tell for sure, but maybe slightly brighter in the north. But something to think about. And then there's also the Q3 line, the other line that we're really hoping to get. It's a little bit weaker, right? But it's coming through now, so that's good. If we get both those lines, we can get temperatures, and that's what we really want. So
exactly, our temperatures and then ion densities, because that's the main things that we use to try and actually confirm that there's aurora. Because it's great being able to go, hey, we saw a brightening happening at one end or another end or the middle of the planet, but you need to back that up as to why that brightening is happening. And the way that we back that up is by going, well, hey, there isn't actually a increase in temperature. So it's actually a increase in the amount of ions, the amount of particles that we're seeing. And by having a flux, or as we call it a flux, but this increase of ions, we can say, oh, well, actually one of the methods, one of the processes that this happens is due to the solar wind flowing down the magnetic field lines, and magnetic field lines only go into the atmosphere due to the magnetosphere itself, and to create this interaction between the atmosphere and the magnetic field is what we see here at the aurora, and hence why it kind of gives us the leadway of, hey, this brightening is actually due to peak increases of ions, and those ions are due to the magnetic field, which creates the aurora. So the end little arrow process is, hey, we've seen the aurora. So that's how we go about detecting these things. I don't know if you had anything to add on to that, Tom, because you're more of the expert, especially at other planets, especially.
So I mean, that's a perfectly good explanation of what's going on. I think we've got a tiny bit of time before we move on to Sean, but I'd like to say that the joy of these observing runs is, especially now because we're doing it remotely, we get to share with a wide range of colleagues. So James is on the call here, otherwise he would be at the telescope as well. But right now, Luke Moore from Boston is on. We've got our PhD students, one of the joys of doing this is that it's a great way of training up PhD students. So currently running the telescope is my first year PhD student, Ryan Wang. And so he's taking his first steps into leading an observation, which is great. He and Nahid was valuable this morning because he was the one that spotted we'd done something wrong. That's why having more people on hand is always good. So those guys were also working on things a lot yesterday in the background, and they are continuing to do that today. And then Omakshi is on, who was at Imperial and is now over at Boston. So there's a whole range of people, and of course we have the telescope operator in Hawaii also working with us. So Japan, Hawaii, Boston, UK are all involved in these observations right now.
Exactly. It's crazy. It's crazy to think how much, but it is what it is, you know. I think that's the only way we can say it is. So what you've always got to remember that these aren't like an individual person working on. I know back in the day it always seemed like, oh well, this one astronomer made this whole big discovery. But I think even they're saying these days there was so much international connections and so much work collaboration that there's so much science that just would never have come to be without the collaboration element, you know.
That's absolutely true.
I was just going to comment. You missed my attempts of artwork this morning across Uranus.
I caught a tiny bit of it, yeah. But you know, there's a lot of creativity right now. We don't really know what's going on with the Aurora yet. So
exactly.
The great thing about that is we can sort of make up what we see. We saw that with James's wonderful animations, which are as good a guess as anyone's.
Yeah. And then back again, because again, I think something just to highlight a little. Sorry, I'll come back to I think just a quick question from Charles, but I think that one of the things I guess to highlight is that the auroras that we know at the moment are that we fully understand are back from 1986. So that's the only full map that we actually have seeing all the aurora across the surface of Uranus, and even then it was incredibly dotty and smudgy because remember we're using instruments from back in the 1970s.
We're effectively using a certain number of photons, so rather than getting a nice, beautiful, clear, crisp image, we're detecting individual photons at particular energy levels of UV, which happen to fall very close to where we would expect the aurora to be, which is why we assume they were auroral, and that's all we have to go on.
Nice. Yeah, it's crazy to think, certainly, that it's just a couple of photons, and that is what we are defining all of our research on. But at the same time, I guess it's the nice thing of knowing there is this flexibility in what we're seeing, that though we think we know what we're seeing, if we send an orbiter or even what we see with James Webb, we might even still see a whole lot more that we weren't expecting, which I know, talking to yourself, we often talk about, if something doesn't go right or something is completely different, it's never a disadvantage. It's more often than not, that's always an advantage if we don't see what we're expecting. Because it just leads to more science and more understanding and more theory and more guessing, which is incredibly entertaining.
It's all good fun.
Exactly.
Great. Well, we're at 10:30, so hopefully we can start talking about my favorite bit of this. This whole thing is just a ruse to make you guys tell me about the history of astronomy, frankly.
It's nice to give you an opportunity to kind of just sit back and relax, and exactly. I do have Dr. Sean Prosser with us. We were going to start with Charles Draper, who just confirmed with me, and he's here. We're going to start with Charles today for the Herschel Museum. Hi, Sean. I see her here on the video, and I'm going to share my screen to get those videos up. If you missed them and you weren't with us yesterday, today is the day to show them again. So let's see if I can get these up here. This is it. And I'm going to bring in Charles. Let's get him over here. If I can find a panel now that I'm sharing. There we go. There it is.
I'm here now, Lucinda, if you want to
Great. I am looking around for things here. I don't know if your camera is on or not.
Do my camera on? Fine, here you go. Yeah.
Yeah. So Charles is the Draper. Thank you for joining us. He is the.
Okay.
Can you hear me, Charles?
I can hear you. Can you hear me?
Yes, great. So he's the chairman of the Herschel Society. Is that correct, Charles?
I am. That's correct.
Yes. And how long have you been with the Herschel Society?
Oh, I joined, I suppose, about 10 years ago, and I've been chairman since 2016.
And what can I ask you? What got you interested in this?
Oh, sure. I mean, I was going to be a kid as an astronomer, and I've been observing since I was, very young. So my, first telescope I had, 55 years ago. But then I went to university and spent my time in university doing the other things people do, So my academic career was not stellar, but I joined the Ministry of Defence for 35 years, which was interesting. And that brought me here to Bath, where I now live. But my interest in astronomy never waned, and I came back to it as an amateur. And living in Bath, came to see Herschel's stuff, and helped to restart Bath Astronomers as an observing group. And through that joined the Herschel Society, and from that came to understand and learn a great deal about William Herschel and his family, and joined their committee. And after a while, when it was time for succession, they said, "Do you mind taking over?" And it's sort of my experience in my professional life sort of helped with that in terms of running an enterprise, publicizing things, running meetings, and that kind of stuff. It's sort of been useful. So I'm sort of applying some professional skills to the world I might have been in. And the fun thing now is that quite a lot of what I do, which I'll say a bit about later, I guess, deals with professional astronomers. And just sort of, it's quite fun to got back into the world I might have been in anyway if I did my life differently.
Excellent. And is there anything you want to tell us what's going on coming up this year for the Herschel Museum or the Society?
Well, I mean, the big thing we are doing is we're preparing for next year. Next year is 200th anniversary of William's death. And we're going to use that to celebrate his achievements. And indeed, the museum's going to do the same thing. I should say about the museum, the way it operates is this. Our society was formed in, which I'll send the video. But just to anticipate slightly, we set up the museum, but it's now operated separately by the Bath Preservation Trust. So we work closely with them, but happily they have all the business about running the museum. We just have the fun stuff of doing astronomy and various things. So next year we're going to have a conference. We'll have 1 day conference about things astronomical, and that'll talk quite a lot about why William and Caroline particularly, and their method of observing was so important to astronomy today, which I'll say about later, I guess. But we'll also have his music, because he's one of those classic people who have had 2 careers. So we'll have certainly concert with music here in Bath, and we're planning other various things too, which I might talk a bit about later. So there's quite a lot to do in preparing for next year.
Yeah, that's fantastic.
Yeah.
Good. Okay, so do you want to carry on with the videos?
Sure, okay. So basically, because we knew we wouldn't be able to film in the museum, I made a little series of videos to sort of tell the story, if you like. And they're in sort of short clips. So I'll sort of introduce each one, if I may. And the first one is just an introduction to the Herschel Museum and how it came to be founded.
Excellent, thank you.
Hello, my name is Charles Draper. I'm chairman of the Herschel Society. Our society was formed in the 1970s to rescue the house in Bath where William Herschel discovered the planet Uranus. I'm standing in that house because it's now the Herschel Museum of Astronomy. The campaign to rescue it was started locally, but also strongly supported by Patrick Moore, and it became something very successfully done, and the museum opened in 1981 on the 200th anniversary of the discovery of the planet. It is now a very successful museum with lots to see, including this fascinating object, which is a replica of the telescope that Herschel used to discover the planet Uranus. I'll say a bit more about that later.
Okay.
So the next video is about William's early career, and he's coming to Bath.
William Herschel was born in Hanover in 1738, and he, like most of his family, began their lives as military musicians. He first came to England in that particular role, and he liked what he saw. So when he got his discharge from the army, he came here as a musician and initially went to the north of the country, where he quickly established himself as a very successful concert organizer, music teacher, and he did very well for himself. And then he saw an advertisement in 1766 to be the organist of the newly built Octagon Chapel in Bath, and he applied to win that post, and he did. So he came to Bath in 1766, and he quickly established himself here as a very successful musician, director of music, and teacher. Bath, of course, was a great social hub in those days, so there's plenty of demand for entertainment, music included. And William did that very successfully, and quite quickly he was basically the key man of music in Bath. But as time went by, he slightly got bored with just music, and he had wide interests in things scientific, and particularly astronomy. And he took to see what he could do to pursue this interest. He tried to hire telescopes and to buy telescopes, but he found it very difficult to do, find one good enough. He had high standards, so he began to make his own. And increasingly he was quite successful at realizing how to make good telescopes by just studying, getting advice where he could, but experimenting. And that is how he came to make the telescope that he used to discover the planet Uranus in 1781. This is a replica of that telescope, and I'll say a bit more about that shortly.
So the next video is about the telescope and the discovery of Uranus.
So this is the wonderful replica telescope that our colleague Michael Tabb made for the opening of the museum. Michael sadly died very recently, but this is one of the museum's objects of great esteem and joy. And it's a very good way of illustrating the way Herschel worked. He was a very systematic man, and he worked systematically with his observing. He's built this telescope, as you can see on this wooden frame. It's a basic Newtonian style reflector mirror, specular mirror back here, and diagonal up here, and so on. But the mount is an altazimuth one, and it's basically designed so you can move things up and down a bit, and from side to side a bit. But it's very clearly designed to look at a particular part of the sky, and that's what William did. He used to do what he called his sweeps. He would examine a particular part of the sky very thoroughly for an evening, and do that night after night when he could. And he was doing one of those sweeps when he saw this fuzzy blob that he did not recognize in the constellation of Gemini. And he called this place and looked again a few nights later and saw it had moved. He reported this, and that began a long process, but that was what the discovery of Uranus turned out to be. This fuzzy blob that William found in his garden. And he found it when Uranus happened to be very high in the sky. And some people said afterwards he was lucky to have happened across Uranus because just by sheer chance. He said he was so thorough in doing his sweeps that he would have found it at some point. That's true, but Uranus takes a long time to get around the sun, so he was lucky in his timing. And Uranus, as it happened, was very high in the sky at the discovery date of March 1781, so it was well placed. So William was a fortunate man in that he made this discovery. But what he's very good was making good use of his fortune. He was very socially adept at seeing what he could take with the opportunities he had, and he took full use of them in his later career.
So the next video is about the partnership with Caroline Herschel and its importance in modern astronomy.
The discovery of Uranus made William famous, and one of the things he gave him was an appointment by the king as the king's astronomer. If he came to Slough, so the king could be close to the king, so the king could see what he's doing and also use it to help entertain his guests. So William and his establishment moved quite quickly from there, from Bath up to Slough. One key part of that, of course, was Caroline, his sister, who he brought over from Hanover and had been in turn his housekeeper, an excellent soprano singer, and also a helper in terms of the telescope. When he moved to Slough, he used the money he had from the king and also the money he made from making lots of these telescopes, because they were very popular. He made lots of them with his brother Alexander and sold them around Europe. His own focus moved to still systematically studying the sky, but studying particularly stars, double stars, trying to help work out why it was, how you could measure the distance the stars were using the parallax method. But also there's fuzzy blobs. Most people regarded fuzzy blobs in the sky as being things that were a sort of nuisance because they surprised you if you're looking for a comet. William wanted to know what these fuzzy blobs were, and he applied his systematic habits to doing so. So he would do his sweeps and he would track and look at all these fuzzy blobs and made bigger and bigger telescopes to help do so. After a while he realised the best way to do that was to work with his sister Caroline. He would be at the eyepiece observing stuff and seeing what he saw, and he would call down what he saw to Caroline. She would note that down and then write that up. And this was the start of a process that led to the production of the first catalogues of the deep sky. And they did this a number of times and produced very systematic catalogues, and Caroline particularly was very good at organising information in ways helpful to observers. And this became the foundation of modern astronomy, because you have to have lots of data about what's out there and how to know where it is and what it is. And the catalogues that William and Caroline produced this foundation that makes them so important to astronomy today.
So the next video is about the telescopes that William used.
William made many telescopes over his career, and indeed he made most of his money from selling telescopes to wealthy individuals or even around the courts of Europe who wanted to have some input into this wonderful new hobby and pastime. So the 7-foot was a very good model from that point of view, but William realised that to see more he needed to have bigger telescopes, and he made several bigger ones. The biggest he made was the one he persuaded the king to fund. This is the 40-foot telescope, and he persuaded the king that it was a good idea to have a telescope that was as big as he could make it. So you have this huge tube, there's a 49-inch mirror at the bottom of it, vast wooden structure, still the same basic design, alt-azimuth telescope that you can sort of move from side to side a bit and up and down a bit. It's the same basic observing method. And the idea is he'll be up at the top observing, and Caroline will be down in the shed below noting down what William was doing. But it was too big. It was too cumbersome. The mirror was very difficult to make in the first place. It weighed half a ton. It lost its reflectivity very, very rapidly because with specular mirrors you had to repolish them frequently and it depended critically on the metal mix. So he discovered a couple of moons of Saturn with it, but basically it was a failure. It was a step too far. By far his most successful telescope was his 20-foot telescope. And there's a picture of it here in the corner of the room. And this was the telescope they used in Slough. Again, same basic observing method. He'd do the observing, Caroline would do the noting down. And it was this telescope that he used to make his amazing catalogues, all these galaxies and star clusters and nebulae. that formed the basis of our knowledge of the heavens as we understand it today. And it was a great tribute to what he did. His son, John Herschel, took the same telescope to South Africa in the 1830s to expand the knowledge of this survey to the southern hemisphere. And it is still around today. It is in the NASA Museum of Science in Washington, D.C.
And the next video is about Caroline herself.
William came from a musical family, and all his brothers were trained as musicians, but sadly his sisters were not. And William was very fond of his younger sister, Caroline, Lena, he called her. So when he was successfully established here in Bath in 1772, he decided to go back to Hanover to rescue her from a life of drudgery she was stuck with her mother. And he persuaded her mother to bring her back. Now, William was acting partly for her sake and partly for his, because he brought Caroline back, and she initially acted as his housekeeper, and then began to also sing, because he realised that she had acquired the family's musical talents, and she became a very good soprano. She also became increasingly involved in the astronomical activities, helping him and his brothers make telescopes, and supporting him when he did. And in time, he actually made a telescope for Caroline to use, so she could make some discoveries of her own. And as this went by, this partnership became increasingly important. Caroline discovered 8 comets and did quite a lot of observing by herself. But the key way the partnership worked was with William at the observing end of the telescope and Caroline doing the note-taking, if you like, initially, and then turning that into catalogues, and then actually organising the catalogues in a way that could be used very successfully by other observers. And this meant that Caroline, in those various roles, as William's assistant, but also as an observer in her own right, she became the first paid female astronomer. She got a pension from the king for doing so. And her role in doing this has made her very much an iconic figure of women in science suddenly appearing rather than just being sort of hidden behind the men. And she's increasingly recognised as a key figure in science. We tried to support that. We set up the Caroline Herschel Prize Lectureship for female astronomers early in their careers 4 years ago, and that's now very successful. And only this year, the government agreed, the German government, to establish a new Caroline Herschel Medal to celebrate particular achievements by German or English or British female scientists. So she's now quite an iconic figure, and very well regarded. This is a picture of her in old age when she went back to Hanover, and it's a very sensitive picture of her pointing at the solar system, and quite an iconic figure in history.
Now there's one more video which my colleague Jonathan Hall talking about Bath observers in the garden at the museum, where of course is where Uranus was discovered.
Hello, my name's Jonathan Hall. I'm a local amateur astronomer, an enthusiast, and a member of the Bath Astronomers. And one of the really nice things about our local society here within Bath and the surrounding area is we're able to make use of the Herschel Museum of Astronomy here in Bath at 19 New King Street. The very home where on the 13th of March 1781 William Herschel discovered the planet Uranus from the very garden here behind me. He shared this house with his sister Caroline, who became a very capable assistant and later in life went on to become a very capable observer in her own capacity. The really nice thing about our club and society is we're able to engage with local clubs, organisations, community centres, schools, and put on events here at the museum for people to come and visit, and we're able to actually observe from the very garden where William first made that discovery. So it's continuing that long tradition of actually observing from the very garden here in Bath. And the nice thing is we can do both modern solar observing during the daytime as well as nighttime observing. And we actually use effectively modern telescopes very, very similar to the one that he first made that discovery of Uranus.
Hi, Charles. I think
Okay.
that was it for the videos. Is that correct?
Yeah, that's it. Yes. Anything you want me to add now, or do you want to go on to Sean, or what do you want to do next?
Yeah, I think we're going to bring Dr. Sean Prosser on from the
Fine.
RAS
Okay.
Library. Thank you, Charles. Charles, don't go away. Stick around.
Oh, wait.
There will be,
Sure.
there will be questions after.
That's fine. Okay.
Thank you for being with us. Hi, Dr. Prosser. How are you? Thank you so much for joining us this morning. A weekend, and you're probably from home now. Thank you and welcome. The floor is yours.
Thank you so much, Lucinda. Hello, everyone who's joined us on the live stream. And it's great to be with Emma and the other panelists as they share their live scientific work. And like yesterday, I shared some interesting items from the RAS Library and Archives while I was on the site. And today I'm just going to quickly share some images of these documents, and I hope it's going to complement Charles Draper's wonderful spotlights on different aspects of William and Caroline Herschel's work, and especially how it tied into the discovery of Uranus. So I'm going to share my slides if I can get this to work. Excuse me one moment. Okay, so I hope that you can see the slides. The first image showing the Royal Astronomical Society library, which is partially open. We are open by appointment on Fridays now, I'm glad to say. So we have been collecting books and manuscripts since we were founded. That's an activity that's happened as long as we've been organising scientific meetings and publishing research and all our other activities. And we have some really interesting, amazing books, but we also have some handwritten manuscripts, observations that astronomers or their descendants have given to the society over the years. We have literally hundreds, if not, well, hundreds of thousands of really interesting observations that we like to share with researchers and the public. And I was hoping that there would be a picture of, yes, okay. So we have a huge number of star atlases, and this is John Flamsteed's Atlas Coelestis. That is, let me just check, I've got the caption wrong here, but he was the Astronomer Royal in the 18th century. And the reason that I'm sharing this page, this constellation of Taurus, is to show that Uranus actually had been observed over centuries, particularly in the 18th century when telescopes were becoming more powerful, but it was assumed to be a star, and it was referred to by John Flamsteed in his catalogue as 34 Taurus in his list of the positions of various stars. So, Flamsteed and other astronomers did record the presence of this celestial object, but it took William Herschel to, as Charles said, to observe the behavior and the movements of this very slow moving planet and realize what it was. But he didn't immediately identify it as such. And that's what I hope to demonstrate to you as I show you the observation notebook, which we're very lucky to have in the Royal Astronomical Society archives, along with many of the observational papers of the Herschel family. So this is the covering page of a notebook which is entitled Observations on the Georgian Planet and its Satellites. The Georgian Planet, that refers to the original title of Uranus. Basically, William Herschel, as the discoverer of this planet, had the privilege of choosing a name for it, and it was politically expedient to name it after the ruling monarch, George III. So its official name for a time was Georgium Sidus. I don't think people started calling it Planet George, but they certainly did refer to it as the Georgian planet, as it is written on this notebook here. It was in the next century that the worldwide community of astronomers decided that it wasn't really sensible to name a planet that could be visible by everyone on Earth after the monarch of one single country on Earth. And I think it was Johann Elert Bode, a German astronomer, who suggested naming it Uranus, keeping in the tradition of classical mythology. And Uranus also is the father in mythology of Saturn, who is the father of Jupiter. So it makes sense if you think about the structure of the orbits. So on the very first page, we have the fateful night of the 13th of March. But as you can see from William Herschel's very clear writing in the top of the page, he's saying, I discovered a comet. It's in this line here, if you can see my cursor. And that is because he can see that it looks different to the twinkling stars around it. And he sees, it's new, he's not seen it before, he knows the sky and its constellations pretty well by now. But, it takes page after page of observations, measurements, comparisons for him to not only satisfy himself, but to satisfy other astronomers and mathematicians in the scientific community. Sorry, I hope you didn't hear that noise in the background. Everything's under control. And he was able to share his data with the Astronomer Royal, Neville Maskelyne, and the lead astronomer of Oxford Observatory, Thomas Hornsby. And Neville Maskelyne really was starting to accept the hypothesis that this was not a comet. Here we see again, it's 1782. On February the 8th, this is an observation where William Herschel says the star is left behind by the comet. But on August 29th, 1782, when he's able to see Uranus high in the sky again, he says, I saw my planet. Full as well defined with 460. Charles Draper explained yesterday that's the magnification, as Jupiter would have been at that altitude with the same power. So, after over a year of measurement and communication and verification, they are, pretty confident of this momentous discovery, the first person since the dawn of time to have discovered a new planet. And here we have it referred to by its new name in October the 13th, the Georgium Sidus. So that was a momentous occasion, not just for astronomy, but also for William Herschel's life. And it had a huge impact on the life of his sister Caroline as well. Now, I'm looping back to the atlas now, because it's very special, not just because it's a rare copy of a historical atlas, but because of who it belonged to. It belonged to Caroline Herschel, and she referred to it directly as she was assisting William with his work of observing the night sky. And he, as Charles very clearly explained, would make his observations. He would pull a cable which would alert Caroline, either in a booth or in the house where she was working, that a new celestial object had been observed, and she would refer to her charts, to this atlas, and to John Flamsteed's catalogue, and make a really accurate note. Her role in this was so crucial to the systematic observation of the night sky, because William Herschel tried to do it all on his own. He would observe a star and then go inside or use candlelight to note down the position, and then he'd lose his ability to see where the star was, because he'd have lost his night sight, if you see what I mean. Amateur astronomers in the audience will know all about this. And, you know, he brought her in to be his right-hand woman. She was doing the incredibly demanding and accurate work of recording his observations. But she was carrying this out. By this time, they'd moved to Datchet in Slough, and later they moved to an area closer to Windsor Castle. She'd been taken from the social whirl of Bath to a country house with a leaky roof in the middle of nowhere. And it was an incredibly difficult adjustment for someone who was, you know, on the outset of a really successful musical career. But she did make that adjustment, and she got really into astronomy in her own right. I'm going to share with you the first. This is the portrait of Caroline that Charles showed us, that's hanging up in the Herschel Museum of Astronomy. And, you know, from August 28th, 1782, by this time, because they had the king's favour, they were living close at hand to Windsor Castle, so that they could you know, provide astronomical services to the king and his family and his court. So it's 1782, and she is carrying out her own observations, and she makes important discoveries in her own right. This is the first time that she discovered a comet. As she writes in her submission to the top journal of the time, the Philosophical Transactions of the Royal Society, she basically explains that her brother was out of town, so she was able to use his powerful telescope, and she discovered what, in her very clear writing, she says, in the notes, I saw the object in the center of figure 1 like a star out of focus. Now that immediately tells us that this is a fuzzy object that is not behaving like a star, and that could have the characteristics of a comet that people were so interested in at the time. And she makes, you know, just as William made his observations night after night of Uranus, she makes her observations night after night of this comet as it's trucking across the sky. And she finally becomes satisfied that this is indeed a comet. And she discovered at least 5, maybe 8 comets in her time. And she also discovered nebulae. This is a kind of cloudy patch in the sky. Sometimes they can be mistaken for comets. And we now know a lot more about what nebulae are, but at the time in the 18th century, they were seen as, you know, fixed celestial objects, but not twinkling. There were smudges in the night sky. And she discovered, this is one that she discovered, which was NGC 205 or M110. So it was in recognition of her work, not just as the assistant of William, but as a successful astronomer in her own right, making many discoveries of comets and nebulae, and her excellent work in publishing the catalogues and the data tables that, as Charles explained, astronomers rely on completely. That meant she got recognition in terms of being the first woman of the RAS to be awarded the gold medal of the Royal Astronomical Society. That was in 1828. The next woman to be awarded the gold medal was Vera Rubin in 1996. Well, we have to get better, and we are getting better. And she was the first woman to be allowed to join as an honorary member, not as a full elected member, as a fellow. She was at the same time as Mary Somerville in 1835. So that's just a quick run through of William Herschel, first president of the Royal Astronomical Society, Caroline Herschel, first woman to be awarded the gold medal of the Royal Astronomical Society, and their links with the discovery of Uranus and the discoveries of so many interesting objects.
Thank you, Sean. That was amazing. I just so blown away. Your presentation was absolutely lovely, and the images of these books. You showed us yesterday live in the library, which was So exciting. But we didn't get to see the clarity of those images, even though it was fantastic to be in the library and see those. You can read this book. And I definitely I think I mentioned to you after your talk, I wanted to go to the library and sit down in Herschel's diary and come through it if I can. Just because you read some really important parts, but I want to read all the other stuff too. So what I'm going to do now is I'm going to bring on Charles, and I was wondering if anyone from the H3 Plus team wants to also join in, and maybe if they have any questions for our wonderful speakers today, that they could ask them themselves. So I know, Tom, you were very excited to have both of them with us today. So Sean, I'm just going to stop sharing your screen. I think I'd love to keep it up.
Yeah, sure.
There we go. Thank you. Let's see if we can bring him. We can bring Charles. I'm going to add him. And is Tom still with us?
So Tom is currently with the observing team at the moment, as we're just having a look at the lines to try and see if we can spot any peaks in the emission, see if we're seeing any aurora.
Okay, great.
So I'm afraid he's out at the moment. He may he may pop back in, but yeah, he's currently discussing with the team over there. So I'm afraid it's just myself from the H2 Plus at the moment.
Okay, well, if there's any questions from the H3 Plus, please do let us know. I was wondering if the two of you are, I know that you mentioned the medal winner, or the is it Herschel Society's Carolyn Herschel winner, Charles. Are you going to have that individual? Can you mention them again? And
Sure.
Speaking.
Yes, I mentioned during my talk about Caroline Herschel that one thing we had done, which I'm rather proud of, is set up a prize lectureship to support women astronomers early in their careers. And we had the idea a few years ago. And I must say, I must give my thanks to Mike Edmonds, who is one of our vice presidents, but also the incoming president of the RAS, who helped me turn the idea into reality. And the thought was that, we all know there's lots of statistics showing that women don't get a fair crack of the whip in terms of getting into professional science. That's true of astronomy and elsewhere. Various efforts to try and help it. And the thought was use Caroline's name and reputation as a means of doing so. And perhaps I could say that there's a curious story, in fact, how it came about. I had the idea a few years ago, and then one of our society members started a big campaign. So at that moment we're still called the William Herschel Society, and one of our society members started a big campaign to change our name from William Herschel Society to the William and Caroline Herschel Society. And he was a guy called Joseph Heaven. He was very adept at social media. And he got a huge sort of social media campaign going across the whole American community, sending us messages saying, yes, we should celebrate Caroline as well as William. And in many ways, it's fantastic. And I said, well, okay, I get the point. But trouble is, if you start sort of saying William and Caroline, then well, what about John? So where do you stop? So there are two consequences of that. One of them, it helps get support, and need financial support for the Caroline Herschel Prize Medal. And the main financial support came from a wonderful British astronomer called Fran Bagenal, who works at the University of Boulder in Colorado. She's a planetary scientist. And she gave us some money, basically, to support this effort to celebrate Caroline. So that helps fund the prize lectureship. And the thing where Mike Edmonds was particularly helpful was identifying what this is for. And it's aimed at people, at women who have got their PhDs, and they're typically doing fellowships. They haven't got tenure. Because getting tenure is the key step that turns you from somebody who is trying to be a long-term professional in the business to actually having a secure job, if you like. So it's aimed at that particular group, and the idea is they're applying to a committee, and I have a committee of 3 splendid female professors of astronomy who assess the applications, and they choose the most promising winner every year. And we've now had 4 of them. And the 4th is Dr. Jenny Carter, who works on the interaction of the sun and the earth, in effect. And she is this year's Caroline Herschel Prize lecturer, and she'll be giving her lecture virtually. I'm afraid we're still COVID bound a bit, in November, and hosted by the University of Bath, because they've been involved in this from the very start. So that's something we're very proud of, and the RAS is very helpful because they do a sort of a part of the admin task, enabling to happen. So that it's done in association with them. But it's a great way of celebrating Caroline. I'm pleased to say that the sort of after 4 years, there seems to be an established part of the firmament. So much so that when Prime Minister Johnson met Chancellor Merkel in the summer to discuss very Anglo-German things, they built on our example, and they decided to have a Caroline Herschel medal to celebrate particular achievements. And I think the RAS is working with its German counterparts on how to do this. So Caroline will have 2 awards named after her, and not many scientists have that.
Wow, that's amazing and fantastic. Yeah. And I haven't mentioned this, but we are having this event as part of World Space Week, which this year's theme is Women in Space. And that was one of the reasons why we wanted to have, it was a fantastic opportunity to highlight Emma Thomas as an astronomer, finishing up her PhD. She'll be breaking out into the world soon as a female astronomer. And opportunities like the Caroline Herschel Medal sounds amazing.
Sure. Well, Emma, once you got your PhD, give it a go.
Of course. So, I mean, I was just going to add, it's weird, but things are such a small world. Jenny actually works in my office.
Really? Okay.
Yes,
fine.
so we both work in the same office. So, as I said, it's been one of the high points that we've been discussing since the beginning of term, obviously.
Good. Fantastic.
Well, I just want to thank you both. And Sean, thank you so much for taking the time out this weekend and sharing this fantastic, it's something that I can actually cut out and use again tomorrow. And Charles, mentioning the work that Caroline Herschel did as well.
Yeah, sure.
And Sean, and if I missed it, that book, I'm so glad you actually took a picture of the cover, because yesterday I missed the cover of that book.
Oh, okay.
The journal, so beautiful. Were those Carolyn's notes or were those William's notes? Those were Carolyn, right? Because Charles mentioned it was Carolyn who was making all the notations.
It depends when you're talking about, to be honest. Yeah, sorry.
No, after you, Charles.
Okay. I mean, they both have wonderful writing. And in the earlier period, I think it was William directly, but later on, quite a lot was done by Caroline. But Sean, you know better than I do, really, which you should.
Yeah, but I need to know a lot better than I do. I know, for example, that there are 2 sets of the sweep books. Now, a sweep was a strip of sky that William and Caroline would observe in one session. And the originals are at the Royal Society, and the fair copies, Caroline basically spent a long time writing up the fair copies there with the Royal Astronomical Society. So that, Caroline did a lot of fair copying, and still need to completely get my head around what looked suspiciously neat and what was actually written in the moment.
But they both have wonderful handwriting.
Yeah.
I mean, my writing's ghastly. I can't read it, but you can read their stuff.
Yeah, and it's so good to use with primary school children. It's we do invite children to read out Caroline's sort of nightly observations and think about what it was like to be an astronomer at that time and how she grappled with the weather. And sometimes she'd be like, "Oh, it's a nebula," and the next night it'd be like, "Oh, actually, it was a lantern shining in a barn in the nearby fields." Everyone. It doesn't matter if you make mistakes, you just have to record it and then learn from it.
And often you learn more from your mistakes than other things. As I mentioned yesterday, I think, when William studied double stars a lot, but he started doing double stars was because in the 18th century, everyone was trying to work out how to work out how far stars were away from the solar system, and they realized the stars were basically like our sun, but further away. And from their brightness, you can sort of say they're millions of times further away. And they also realized that they had to use the parallax method to actually judge the distance. But the telescopes were struggled to actually be accurate enough to do that. So what William thought was, if I look at these stars that appear to be in the same part of the sky, and that may help me. Now he made two assumptions. He assumed that all stars were roughly the same brightness, and the stars were individual things, and they weren't going around in twos and threes, gravitationally bound. Now both those assumptions were wrong. Stars vary hugely in brightness, and most of them are multiple stars. Our sun's unusual from that point of view. But that led him to study them, and it led him to realize that he was wrong. So it's a classic case of making a wrong assumption, but pursuing the logic of that and learning a great deal because of it. So I think making mistakes sometimes can sort of teach you more than doing a thing right.
Absolutely, a really great lesson to realize that that's a really important part of the process.
Yeah.
And I highly recommend heading over to Bath when you can, when things are definitely safer to do so, and visit the Herschel Museum. We're going to hear from the Bath astronomers tomorrow. I want to thank our guests, Dr. Sean Prosser from the RAS Library, and also Charles Draper from the Herschel Society. Thank you both for being with us today.
Okay.
We're going to move.
You're
Thank
welcome.
you.
Right.
Thank you very much.
Thank you.
Good
We're
luck.
going to move on to Emma Thomas, who's going to give us an update of the telescope today.
Yes, so hello, I'm back again. So I've been back and forth a little bit with the observers today. So I ended up having a slight discussion whilst I was with them about the fact that I could see a fourth object, or a fourth, I think 1, 2, 3, yeah, a fourth moon at the time. I was very excited because I was there like, I can't see it in the Uranus viewer. I can't see, like, part of me was thinking, oh, well, maybe it's a small moon and then we're seeing it, but typically if it's about the same size as the larger moons, it's got to be something about that size. It's also giving light. But we discussed with the TO, so that's the telescope operator, and we think it is Bernie, who is the TO for today, mentioned it is an A0 star that we're seeing. I'll see if I can get the magical circle that I've been using and getting better all the way through this. There we go. So if I get that out and move it over. So this very faint blob, just about in the middle of our screen. That in there, I believe, is a A0 star that is making its way through the image at the moment. So hopefully we'll be able to see that in the movie. It will probably just look like a streak going past in the sky. But I think that almost kind of links in with yesterday, where we had someone ask, how do you make sure that there aren't other planets or moons or stars or galaxies that aren't going to, interact with your slit? It can usually just be sorry, bear with me. It can be kind of a random chance of what you'll end up seeing in the background. When looking this like close to the sky, because you got to remember what we're looking at isn't like kilometers. It is what is known as arc seconds. Arc seconds are like fractions of a degree of the night sky. So we're looking at like incredibly small in the sky itself. So the amount that we actually see, or like especially when it comes to bright objects like Uranus, we usually only just see Uranus and the moons, but we get these really interesting chances where we'll see, like with the Henrik's movie that I've shown a couple of times, we have like a galaxy moving in the background, and in this case we think we have an A0 star that is moving in the background to come to say hi. Thankfully it's not interacting with the slit, but even if it was, I think Tom mentioned yesterday, when we take our data, especially when we take a lot of data, because that star is only there for a small amount of time, it will not affect the overall results, because the signal from Uranus will just blot out the signal from that one blip from the star in the background. But it's a nice little cosmic hello from a star from beyond ours. Otherwise, with the signal on the update inside of that, so we're getting a much stronger signal. We've currently got the observers at the moment are using the Q3 just to see if we're getting a good enough signal. We're definitely getting a strong signal with the Q1. Well, I say by Q1, actually, apologies, is that the Q1 line is the brightest line that we get from Uranus. It's the biggest hello with HC plus that we get in terms of the light that's emitted at the specific wavelength. The next brightest one that we have is Q3. So we look for Q3, and the reason we're very excited to get a Q1 and a Q3 is we use these two to basically compare with each other so that we can effectively work out a temperature as well as a ion density within the atmosphere to get an idea of kind of how dense the atmosphere is of HC plus. So yeah, currently our astronomers in the background are having a bit of a discussion on what we're seeing. If we're seeing kind of a peak of emissions on one end of the line, on the middle, or on the edge. Currently, it's looking like we may be seeing a higher emissions at the, I believe, the more towards the northern pole. So again, we may be seeing at the moment the end part of the northern aurora, possibly. But again, it's still up in the air at exactly what we saw yesterday. So it's possible that these are just raised emissions due to the sun. It is still quite hard to actually pick up the aurora. This isn't something I discussed much, but all the way for the history of HC plus, especially at Uranus, one of the big difficulties we've had is that we know there have been variations of HC plus that is above the threshold that we expect from HC plus emissions from Uranus. And what I mean by that is the emissions from the sun basically cause a day side glow across the whole, well, across the day, the sun-facing side of the planet. So the aurora has to be bright enough to actually be on top of that for us to actually even see it, because if it doesn't, it gets blotted out and we can't see anything. Over pretty much the last 20 to 30 years, the understanding has been that there has at least be a 20 to 30% variation of this HC plus emission above that of what we expect on the surface of the planet. But because, and again, touching a little bit on what I said earlier, that Uranus has been continuously cooling in the upper atmosphere since our first detections back in 1993, the signal that we've received from this planet has got steadily and steadily weaker. So it has been incredibly important to try and take as many observations as we can before we get to a point where possibly we're just not able to detect it anymore, and we're going to have to wait for Uranus to cool back up, which may take another 21, possibly past that 21 years. Sorry, take a quick breath. I'm just trying to think, so I'm gonna just get rid of the circle just in case it's going to be slightly distracting. Just trying to, I don't know if we have any other lines to share at the moment. Oh, I realize we have Tom with us. Hello, Tom. I'm just covering over. So I think Brian was mentioning that we see possibly a star in the background of our observations.
That's entirely possible. Yeah, I've just come back in from the observing team. Everyone's in high spirits. We've gotten some really nice data so far, so it's really positive.
It was quite funny. I went in about an hour ago and we were discussing about the color schemes that are used for observing. I think that's been a big point, especially at the beginning of these observations. We had a lot of people ask, why is Uranus green? Why is Uranus red? Why is Uranus this color? And I should probably reiterate, when we take these observations, we're actually just taking signal. So essentially, black and white pictures than anything. To make it easier for us to see, as just humans looking at a screen, we will pick colors just to make it easier to see variations. So usually for HC plus, we go for kind of this pinky purple red color in our observations because we're working in infrared. But that doesn't mean we necessarily have to. I think earlier our team was experimenting a little bit with other colors.
There is a huge ongoing debate about what is the best color scheme, and lots of agreements and disagreements about which we should be using. This pinky, purpley, yellowy color scheme is definitely favored by a lot of people.
I like it.
Excellent. but yes, as I said, it just honestly depends. The videos that I've been making, once I've been very kindly, Henrik has made the code so I can make. Henrik specifically put that color, as he commented to me, was that it just made it easier to see the moons in the black and white, because there's quite a lot of noise in the background. It can be very difficult to pick them out. So we'll usually just pick colors that for human eyes, it's so much easier to pick stuff out. But that doesn't mean that's the actual, like that doesn't mean that's the visible wavelength. That's what we're seeing. We're just putting an artificial coloring on the top of it to make it easier for visualization than anything.
I ask a quick question about that.
Mm.
Wondering, do any of the colors help with seeing the rings? Are there probably more factors that help us see the rings? And your processing video was really great.
I would say possibly color can help. Again, got to remember it's going to be some difficulties, because got to include, color blindness and all of this. There's going to be some people who are like, I can't see that, and I will apologize because I don't have color blindness myself. But other factors, it is more on the other factor side of things, because at the end of the day, you still have the data that you've collected. It will just sometimes appear more easier to see on other colors depending on what your eyes are used to. But what helps with seeing stuff like the rings, and even, I don't know if other moons, because that's more of a zooming out than anything, but definitely for the rings is, well, one, the data that you're taking, the data reduction side of things. So I mentioned yesterday, there's a lot of cleaning up you have to do with your data. So that is taking out dead pixels, that's getting rid of other interactions like galactic cosmic rays that decide to pop up and blast a couple of pixels on your screen, as well as just hoping that you don't have any clouds and hoping that the seeing on the night is really great. The big thing that really helps with seeing the rings is if the seeing on the night is great. And what we mean by that is just how clear it is up in the sky to really see what you want to. The better the seeing, the better that we can see stuff such as the rings.
Is this clearer than yesterday? Because it looks really clear. I don't know if it's the colors or the brightness of Uranus and that, but it looks really good.
I think we're at similar seeing, perhaps a little bit better seeing, but I know that we're not having as much clouds today, I think. That was the big issue yesterday.
Yeah,
we kept having clouds coming in.
Yeah.
Yeah. Clouds, unfortunately, is a big nemesis of astronomers.
Yeah. Another reason why the rings are maybe a little difficult to see is just the wavelength that we're using with the camera. So we can't see it in the visible. We're using infrared light, and we have picked a particular wavelength window. Naturally, the focus is on the science. So we want something that gives us as nice a clear sort of circle that we can guide on as possible. And actually the rings are detrimental to that. If the rings are too bright, they will pull us away from that circular shape, and it will make the guider work less effectively. So unfortunately, we're actually selecting wavelengths that give us a nice boring planet without any of those rings, because it will help us guide on the planet better.
So thank you for covering that bit, Tom. I hadn't forgotten that part. So I am just going to come up to, so we're at about 11:30 here in the UK, and we're now getting on to our, second speaker now of the day, Ophelia Wibisono, who joins us from University College London, or UCL, from the Muller Space Science Laboratory, or MSSL. It's already mouthfuls, apologies. So Ophelia's research continues to enlighten us on understanding X-ray aurorae at the outer planets. With 10 years prior experience in science communications, Ophelia is a grand expert, I would say, in presenting complex theories and concepts in a digestible format, whilst ensuring that they're still engaging and full of curiosity. As a PhD student, she has received the Rishbeth Prize for Best Student Talk at NAM in 2019, and this week has been sat on the panel for Stargazing London's event, An Evening with the Northern Lights, celebrating the art and science of auroras. On top of this, and at the heart of today's discussion, and hopefully discussion than anything, she's a lead investigator in combined observations with the James Webb Space Telescope using XMM Newton to investigate Uranus in the X-ray spectrum. Ophelia, I will leave it to you if you want to share your slides, or again, I'm very happy for any discussions that you wish.
Great, thank you very much. and hopefully you should be able to see this. So yeah, thanks very much for having me, and thanks for that introduction, Emma. So today I thought I'd talk about the aurora, but also about X-rays from the outer planets, and also about our future observing hopes for Uranus. But first up, the aurora. So this is a video of the Earth's aurora. Our ancestors have marveled at them for millennia, and we can often see them around the Arctic and Antarctic Circle. So for the Earth, it all starts off with the sun. The sun releases a constant stream of charged particles, also known as plasma, in something called the solar wind. And this solar wind carries with it the sun's magnetic field that will then interact with the Earth's magnetic field. So the Earth's magnetic field gets opened up like this, and then it gets dragged over and away from the planet as the solar wind flows past the Earth. And then at the nighttime side, in what we call the magnetotail, as the solar wind moves past, this puts pressure on the Earth's magnetic field lines, and then they get squashed, and then they eventually snap and then shoots plasma back towards the Earth, and then it will interact with the atmosphere and produce the aurora. The first extraterrestrial aurora discovered was actually discovered in 1979 by Voyager 1, and that was Jupiter's ultraviolet aurora. And Jupiter's aurora covers almost every part of the electromagnetic spectrum. So nowadays we usually study the UV aurora using data from Hubble and also the Juno spacecraft, which is currently orbiting around Jupiter right now. So this particular image was actually taken by Juno as it moved over the North Pole. And you can see quite a lot of detail actually in the UV aurora. For example, this bright dot here is caused by one of Jupiter's moons, Io or Io, and so these are produced when the moon orbits around Jupiter. They disturb the magnetic field lines, and then they imprint sort of that disturbance in the aurora. Sometimes you can have brightenings as well. So this kidney bean shaped ring is the main oval. You can have brightenings along that main oval. You can have pulses and flashes in the polar emissions as well. So there's quite a lot going on. A few months after the UV aurora was discovered, Jupiter's X-ray aurora was detected. So this image is quite a recent image. We've overlaid a Hubble optical image of Jupiter, and in the purple is the X-rays, and that was from Chandra data. The visible aurora on Jupiter is the dimmest of the lots. It can only be seen on the nighttime side because it gets easily lost in the sunlight. Tom and colleagues at Leicester are experts on the infrared aurora, so I'm not going to say much in case I get something wrong. And then the electrons that precipitate into the atmosphere, they also emit radio waves. So how does Jupiter produce all of these emissions? And that's partly thanks to its magnetosphere. So the magnetosphere is this bubble of like magnetism around a planet, and Jupiter's magnetosphere is huge. Will yesterday said it's the largest coherent structure in the solar system, and you can see how big it is there compared to the Earth's magnetosphere. As well as that, Jupiter has this moon, Io, and it's the most volcanic place in the whole solar system. It has hundreds of active volcanoes on its surface, and every second, these volcanoes release 1,000 kilograms of stuff out into space. And some of that material gets electrically charged, and then they get dragged around Jupiter by the planet's magnetic field lines, and that creates a ring of plasma around Jupiter called the Ioplasma torus. And this torus actually helps to make Jupiter's magnetosphere bigger. Jupiter spins once every 10 hours, so that's pretty fast compared to the Earth. And all of this plasma inside the magnetosphere gets whipped around, the magnetic field lines get twisted, and so Jupiter's aurora are mostly driven by this fast spinning magnetosphere and by Io. And so Jupiter would still have its aurora if the sun disappeared. But I do focus on the X-ray aurora on Jupiter. It's I think it's the brightest planet in the solar system in X-rays. So I don't think that's a coincidence that, you know, we know more about its X-ray emissions than from any other planet. It was discovered in 1979. So that was using data from the Einstein Observatory. And this is one of the earliest images of Jupiter in X-rays. I mean, to me, that just looks like two blobs coming out of, out of Jupiter. And then in the mid 1990s, we had the Rosat satellite. And now it had a better spatial resolution. So now we can clearly see where the aurora are coming from. They're separated out. And we've also got some disk emission as well from around Jupiter's equator. And then in 1999, XMM Newton and Chandra were launched, and they really revolutionized our understanding of Jupiter's X-ray aurora. And these two telescopes work very well together. They're good at different things. So Chandra has high spatial resolution, so it can really pinpoint where these X-rays are coming from. And so you can get quite nice images of Jupiter like this. And again, you can clearly see where the northern and the southern aurora are. And during that particular observation, the sun was releasing a lot of X-rays, and those X-rays were reflecting off Jupiter's atmosphere. And that's how we can see Jupiter here against the background. XMM Newton, on the other hand, hasn't got such a good spatial resolution. So instead of getting nice, pretty images, this is what I get to see. But, you know, you've got the northern aurora here, the southern aurora here. Jupiter's disk is highlighted in green, and then the pink rectangle there is the equator. So in this color scheme, we've got yellows and whites. That's where you get the brightest X-rays. Blues and blacks are where it's dimmest. So, I mean, I'm more interested in the energies of the X-rays, because that's how I get the spectra, and that's how we can figure out what caused or emits the X-rays. So that's what XMM is good at. It's got very good spectral or energy resolution. Suzaku and NuStar have also observed Jupiter in the X-rays, but we mostly use Chandra and XMM. We've also got X-rays coming from the Galilean moons and the Io Plasma Taurus. So for the moons, that's due to fluorescence. So how Jupiter's X-ray aurora is produced is slightly different to how the other wave bands are produced. So the ultraviolet, infrared, and visible aurora are emitted by the molecules in Jupiter's atmosphere, whereas for the X-rays, it's actual incoming particles themselves that give off the X-rays. And we've got two types of aurora X-ray emissions, low energy and high energy X-rays. So the low energy or soft X-rays are emitted by ions. So these are positively charged atoms, and they emit X-rays through a process called charge exchange. So what happens is you have an ion that gets close to a neutral atom or a molecule. In this case, we've got a hydrogen atom, and the ion steals an electron from that neutral, and then the captured electron is excited, and later on it will de-excite and emit an X-ray photon. The higher energy or hard X-rays are emitted by electrons. So as these electrons enter the atmosphere, they slow down, give off X-rays through bremsstrahlung radiation. You also get X-rays emitted in cathode ray tubes. So you have them in LTVs and some particle accelerators as well. And these two types of auroral X-ray emissions are found in slightly different places. So in this picture here, we're looking down onto Jupiter's North Pole. And we've overlaid Hubble data, which is in ultraviolet wavelengths in orange, and then you've got the Chandra data in green. So these were taken simultaneously. So you can see the main auroral over here in orange. And most of the large green dots, which are the high energy X-rays, coincide with that main oval. So the same population of energetic electrons produce the hard X-ray aurora and the UV aurora that's found along the main oval. And then most of the small dots, the softer and low energy X-rays, are found inside this oval, closer to the poles. And you've got like a cluster of them here too. So this is a just an animation of Jupiter's X-ray aurora. So using real data. So 10 hours here has been sped up into a few seconds. So you can see the aurora rotate in and out of view. They're fixed on Jupiter's frame. So in this case, Jupiter is like a lighthouse or a pulsar. And you can see that the northern aurora is tilted in our favor. So we can see them a bit more easily than the south. And that's one of the reasons why the northern X-ray aurora tend to be brighter than the southern counterpart. And then on this side, we've got a light curve of the northern and southern aurora. So this just shows how bright the aurora looks to us. And it appears that, you know, for the north, for the blue light curve, the aurora gets brighter and dimmer, brighter and dimmer. And that's just because it's rotating in and out of view. So using this light curve, you can see Jupiter's 10-hour-long rotation period. And within that 10-hour-long envelope, you've also got these pulsations. We call these quasi-periodic pulsations. And the periods last for tens of minutes. They can range from 8 minutes to 45 minutes. And we also see these pulsations in the UV and the infrared aurora, and also in the radio emissions. But how are they produced? Well, we think it's caused by wave particle interactions in Jupiter's magnetosphere. So there's loads of waves in the magnetosphere. So what we think happens is something shocks Jupiter's magnetosphere, makes it ring like a bell. So this could be a big gust of solar wind that shocks the magnetosphere, and that sets up standing waves to travel along the field lines, and that helps to scatter ions and electrons into Jupiter's atmosphere at the same period as those standing waves. And then we get the X-ray and the UV pulses and the radio bursts as well. So they've been seen to sort of have the same periods as well. So all of these pulses have the same periods as each other, and they also have the same periods as the waves. So that's quite a new discovery. Will and our colleague Zhonghao actually led that study. And before we move on, actually, I want to say that the Earth has an X-ray aurora as well. So these are due to electron brimstoning and also fluorescence. So electrons slowing down and also electrons colliding with the molecules in the atmosphere and making it glow. So actually, when this video was taken, Integral was observing a faraway galaxy, and then the Earth just got in the way. So this was a complete accident, and we don't need to worry about these X-rays because they get emitted out into space. They don't go down towards the ground, so we're completely fine. We're safe. On to Saturn. Saturn's X-rays were first observed by the Rosat satellite in 1992. So these images were from Chandra observations, and we can see that the X-rays are concentrated around Saturn's equator and also on this edge, the eastern edge of the rings. The different colors there tells us there's different energies involved. So red, that's where the X-rays have the lowest energies. Greens is like the next step up, and then blue the highest energies. And then on the right, they actually produced a spectrum from the rings, and they show that there was a strong emission line at 0.53 kilo electron volts. So this told them that the likely source mechanism for the ring X-rays is fluorescent scattering of solar X-rays from oxygen atoms in the water ice ring material. And they also found that the disk X-ray emission got dimmer as the solar activity declined, but the ring emission didn't vary in the same way. So those are scattered disk emission and also ring fluorescence. But what about the aurora? Does Saturn have X-ray aurora? So we know at Jupiter and the Earth that when these planets get hit by a huge gust of solar wind, the aurora get brighter. And in 2011, they predicted that Saturn was going to get hit by one of these events. And so they managed to get time using Chandra to see what happens. So these two here, they're from the same observation, just looking at different energy ranges. Each orange dot is an X-ray photon, and they found no sign of an X-ray aurora. And then last year, in November of last year, we managed to get time using Chandra again. So this time, Saturn was actually inside Jupiter's magnetosphere. So every 20 years or so, that happens. And so Saturn's magnetosphere itself was sort of alternately immersed in the solar wind and also in Jupiter's magnetotail. So every 2 to 3 days, it would swap from one to the other. And we assume that Saturn's magnetosphere would experience a more powerful fluctuation as it moves from the rarefied plasma in Jupiter's magnetotail to the denser solar wind. And so the magnetosphere, Saturn's magnetosphere, would feel a stronger shock as it moves between them. This is a data that we got. So here we've got each blue dot is an X-ray photon. We split up Chandra's CCD into Saturn-sized grids and then counted how many photons were in each grid. And unfortunately, there was as many X-rays on Saturn's grid as there were on the other boxes, so we couldn't say that we had detected X-rays from Saturn. And to this day, we haven't detected Saturn's X-ray aurora, and we don't know if it even has an X-ray aurora. And Will spoke about this yesterday, but in 2002, Chandra first observed Uranus. That was during solar maximum. And then again in 2017, they predicted one of these solar wind shocks that was going to hit Uranus in November 2017. What I'm showing you here is the data from the 2002 observation. And again, each blue dot is an X-ray photon, and we detected more X-rays from Uranus than what was expected if it was from scattered solar emissions only. So that suggests that maybe Uranus was reflecting more X-rays in Jupiter and Saturn, or maybe there were other additional X-ray production processes. So maybe ring fluorescence or aurora. The observation from 2017 showed a non-detection, but there was a 40-minute period where the X-rays from Uranus was brighter than surroundings. So these three observations, there were three observations, they were each about 8 hours long. So for an X-ray observation, that's not particularly long, that's actually quite short. So we need more observations to test this and to sort of confirm that this was a detection and maybe find out what's going on. So that's what we're hoping to do in August of next year, and also January, February 2023. And just 2 days ago, I submitted a proposal to use XMM Newton to look at Uranus. XMM is more sensitive, it's about 3 to 8 times more sensitive than Chandra, so it can collect more X-ray photons. XMM has 3 X-ray telescopes, these big circles here, and then the smaller one there, that is its optical and ultraviolet telescope. So we asked time to use all of those telescopes. We also asked for 100 hours of observing time, so quite a big step up from what we had before. So we'd be able to see almost 6 Uranian days. So what we're hoping to do is we're hoping to confirm and strengthen the detection made by Chandra, see if there are any variations in the emissions as Uranus rotates, compare sort of the X-rays and the UV, see if they sort of brighten and dim at the same time, because that might suggest that Uranus has an X-ray aurora, because we know it has a UV aurora. We hope to produce a spectrum to see how these X-rays are produced. So are they all from solar scattering, or have we got fluorescence and charge exchange occurring as well? We're hoping that these XMM observations will coincide with the James Webb Space Telescope observations, which your colleague Lee is leading on. So JWST will look at Uranus in the infrared. So hopefully we'll get simultaneous X-ray, UV, and infrared data, and we can compare what the three wave bands are doing, and hopefully find out more about this really weird world. So yeah, that's all I've got to say. Thank you very much for listening.
Oh, yeah, thank you so much, Ophelia. I really appreciate your time. Thank you so much for your slides, because I appreciate I asked very last minute on that one. But honestly, we really appreciate your time, especially you've had an incredibly busy week, I can imagine. So I really appreciate it. I know that I think we've had a couple of questions coming in. If you're happy to take any questions, Ophelia, if I shoot them your way. I'm just going to put in the background a little bit to, I won't say distract, but just kind of to set the mood up, I suppose. We have basically the view at Gemini and at IRTF on Mauna Kea. This is from the previous night rather than from tonight. And this is basically time lapses of several views across the Mauna Kea itself. Anyway, distracting myself from the Q&A. So first off, let's see if we have any questions for Ophelia. Just having a look. I think Tom has answered quite a few on YouTube, so I can ask one of my own. Otherwise, I know we do have some Zoom questions. I may check some with yourself if they are more kind of X-ray related. So Ophelia, I was going to comment then. So the observations that you're putting in with the XMM Newtons, that is for, you're saying about 6 days at Uranus. In terms of writing the proposal that you're making for it, how difficult did you find that? Was this your first proposal that you're doing, or is this been like are you now like an expert, I suppose, or has this been your first one?
No, this was actually my second. So last year I asked for a similar amount of time for Jupiter. So yeah, we managed to get that, and I'm currently working through that data. So yeah, hopefully we'll get this one too.
Oh, awesome. That's really good to hear. Well, awesome to hear. I think awesome, cool. Yeah, sorry, it just blows my mind because today we're doing well, we've done 3 days and a bit of Uranus. Thankfully, IRTF has given us. But typically, when we do the HD plus stuff, we've usually done like a day, and then another month later we'll do I wouldn't even say a day, we do about 8 hours, so not even like half a day, and that's usually just to help out with Henrik with his temperature readings than anything. But so, it blows my mind.
Yeah, I mean they won't happen continuously for 100 hours. Course, we'll split them up into 3. And yeah, so hopefully 1 or 2 will happen in each window, so when JWC is observing, so then we can add up all the data. Yeah.
That's awesome. Yeah, sorry, I hadn't meant to mean that you were going to be doing.
Oh no.
God, I could only imagine the poor person that has to sit there for 100 hours staring at the screen. But it still blows my mind. So it'll be 3 sections then of oh wow. That's all in one slot, so like 30 hours at a time, or
yeah 30 hours at a time.
Whoa, sorry, that blows my mind. We're only doing 8 hours today, and it takes, it doesn't feel like it, but a lot of the observers will also come up for HD plus. It takes a lot out of the day when it's like an 8-hour observing run. Worse more so when it's 2 in the morning and you're there staring at the screen half awake. But oh wow, that blows my mind. Sorry, that absolutely blows it. Yeah, there's a good topic I actually want to kind of discuss. Obviously there's a bit of a difference here where we've obviously got space-based telescopes and Earth-based telescopes. If we can kind of perhaps like discuss a little bit on some of the benefits, the negatives that we have to obviously counteract, interact with, and like what I guess the pluses and minuses of using space-based versus the Earth and Earth versus space. If you would be able to lead that perhaps in that kind of discussion.
So for X-ray observations, we need to be above the atmosphere. The Earth's atmosphere blocks out the X-rays, and also for UV as well. And I mean, one bonus, we don't need to worry about the weather or clouds or whether it's daytime or nighttime. But we do need to check that. So we can't turn on XMM's instruments if it's at its closest point to the Earth. So XMM has this really like elliptical orbit, so we can't observe when it's inside the Earth's radiation belts, because that will damage the instruments. We also need to make sure that it doesn't point too close to the sun, because that will damage the telescopes. Yeah, and we just need to make sure that what we're observing isn't too bright. We're using the right filters, and so we don't get the data straight away. So they'll get I guess there'll be a certain point in time when the data gets transferred from the telescope down to mission control, and then they'll sort of clean it up for us, and then about 2 weeks later we'll get the data.
Wow, so it's a bit of a process, I suppose, from like obviously going in, taking the observations, then obviously waiting for them to be cleaned up, transferred back to Earth, and then actually being able to use them yourself. And then even then it's actually doing the data analysis, which I'm sure you can attest to, can take weeks, can take months.
Yeah.
Goodness, wow. I guess from a versus, when I say a versus sounds a bit much. Yeah, obviously, as you're mentioning, ground-based, we do have to have fun with the weather. If it is snowing, if it's too cold, if there's too many clouds, we just have to pack up for the night and shrug and go, it's a shame, but there goes our day of observing. Equally, as we mentioned before, we have to include techniques to mitigate the Earth's atmosphere, because that has it just essentially clouds our view. We just can't see anything past it. So we have to do the nodding technique we were mentioning earlier, which is why we're seeing two lines on our spectra. I'll see if I can actually bring that slide up. Bear with me. It's a close up. There we go. Yeah. So we're seeing, in fact, if I get the spectral camera a bit brighter, we're seeing the two lines, and that is Uranus. This is both pictures of Uranus. It's like oh, there's a better word for it. I can't remember. But the photonegative, essentially. So we've got a lit up version of Uranus on one side, and then we've got the negative lit up version of Uranus on the other side, but it's still the same planet on both parts. And that we basically just use that to mitigate the effect on Earth's atmosphere at both of these points, which helps with us doubling up a signal. So it's always good. It's always positive points. Thankfully, we can literally just grab our data then and there. Literally last night, I was downloading all the data that we took last night. It took a while, I'll tell you that much. It was a lot of megabytes, but got through it in about an hour or so. And yeah, I'm free to start playing with it and go from there. So there's not too much of a difficulty, but unfortunately, I do have to clean it myself and get everything as nice and shiny, which can be a fun experience. It's just a very long experience in trying to clean it up, certainly. But awesome. I realized you had another question, which is with XMM Newton. Do you know what cools the telescope itself?
Not really, to be honest. I'm sure there's like, I don't know, they use some kind of nitrogen
coolant.
Yeah, coolant in there.
That's fair. Yeah, no, I was just curious, because I think for ice shell, I didn't know off the top of my head specifically, because they try and keep ice shell as cool as humanly possible, so it's as close we can try and get towards 0 Kelvin. And I think, as you mentioned, I think they use some sort of nitrogen, or at least something that is relatively cool, coolant wise. But again, I knew it better at another point. Oh, sorry, Tom.
I can weigh in if you want me to.
Yes,
on this.
Apologies.
So if we were observing at a shorter wavelength, like 1 or 2 micron, we could use just liquid hydrogen. But when we're out at 3 or 4 micron, it would just be super hot. We'd get so much brightness in our instrumentation there. So we actually use liquid helium on the chip itself. So the chip is cooled down. I'm looking at the temperature summaries right now. The chip array is currently cooled to 30 Kelvin. And that's basically through a closed loop of liquid helium. and then the whole instrument is broadly cooled down to a higher temperature. I'm looking at the temperature readouts and I'm not seeing it right now for the whole instrument, but that's liquid nitrogen. So that's the real limitation for a mission like James Webb Space Telescope that will be going up. It has to include a whole lot of coolant on there. The advantage of X-ray is that a bit of heat in your instrument is not going to cause a signal, so you don't have to worry about that.
Awesome. Thank you very much for weighing in there, Tom. So just having another check on questions this morning. So some lovely chatter in the YouTube chat at the moment. Just kind of glancing through.
I'd like to ask Ophelia a question, if that's okay. Hi, Ophelia. This is Lucinda Offer. How are you? Thank you so much for joining us. What got you interested in taking this path that you're on? What kind of inspiration did you have? Did you know an astronomer? Did you go hear an astronomer? Did you have an astronomer in your family already?
Yeah. So none of my family are scientists. Most of them are artists. And I mean, if you want to go right back to the beginning, I was, 6 and I read a book by Sir Patrick Moore. And that was when I realized that, wow, there are other things out there are other worlds out there. I want to know more about these worlds. And after university, I realized that I prefer to talk about science more than I did doing science. So that's how I became a science communicator. And then I just kind of missed science. I mean, I was like working in science, but I wasn't doing any science. And working at the Royal Observatory, I got to meet lots of astronomers and researchers, and they seemed to like really love what they were doing. And I thought, oh, actually, maybe this is something I can do. Maybe this sounds kind of fun, and let's see what happens.
Emma, what about you?
Awesome.
What got you to become an astronomer? Because this is important. We're women scientists who in a very male-oriented world, industry, and so this is important to share with other girls and other females around the world. What got you so inspired, and how also share? Is it how easy is it, or how difficult is it?
Goodness. So I'm going to apologize because I didn't actually know too much about Patrick Moore when I was a kid, so my starting out were very different. I'm going to be very disappointing because I think I mentioned yesterday, back when I was in primary school and high school, I was half determined. I don't know if I was fully determined now, thinking on it, but it was up there that I wanted to look at being a doctor. Unfortunately, at the time, my mother was quite ill, so as a kid, the first thing in your mind, you're like, I want to help my parents. So I really wanted to try and be a doctor to try and help out, and then found out that my chemistry grades were really terrible. So I was encouraged not to look towards medicine and that side. So instead, at the time, I remember going, okay, if I'm not good at chemistry and a lot of biology themes require you to have chemistry, what can I look at instead? And I went, oh, well, there's physics. I remember thinking to myself, well, actually, you're not very good at physics. We get average grades at best in physics. And I went, yeah, but, if we actually gave a go and really did it, I think we'd manage to do it. And it ended up being a big challenge because I remember I just wasn't very good at physics at all. I still fail to these days to do just simple basic mechanics because my head just can't get around it. But I absolutely loved hearing about electromagnetics. It's the basic course that everyone always does from high school going into university, and I loved hearing about it. And then being at Leicester, because it's a space-based university, it of course had to be, and here's EM in space, and my mind was absolutely blown by the fact that you could actually have electromagnetics happening in space on such vast and big scales and have such very different environments that were going on. And then, yeah, I ended up taking on Tom's project in my third year for my degree, which was essentially the same project I'm doing at the moment, which is looking at Uranus for the Aurora. And yeah, from then it's pretty much got hooked on wanting to know more about auroras at the planets. I pretty much just continue doing that all the way through. And yeah, I've ended up in where I am at the moment. It feels weird to say, because I've always been like, oh man, I really should get a telescope and do more observing myself, because I do it as a job. But in the back of my head, I've never felt like I'm an actual astronomer. I've always felt like, I don't know, like I'm an astronomer, but I'm pretending almost like I'm not a proper astronomer. But thinking on it, I have done a lot of observing of the sky, so I should give myself more credit, you know.
Absolutely. I'm just gonna join you for just a second about that story, because it's really great. So I worked at NASA Ames in California. My father worked at NASA as well, and I remember being a geology student, is what my background is in geology. I remember being at NASA, and my supervisor, Dr. Chris McKay, said, he just looked at me and said, "Listen, you're a scientist now." And I just felt like that just sounded so foreign or odd to call myself a scientist. I really hadn't published, and that's kind of when I was in university, that's kind of what they put in our head, is like, you're not a scientist until you publish. But he was like, no, you're doing science. I was working in the field, bringing in scientists and teachers to work together. And it was that I was, in some way, I'm a bit disappointed I have to wait until someone told me that. And you sort of have to, you are an astronomer. And that's, just keep saying that. You are an astronomer.
I go for it. Sorry, Philly.
Sorry. I got to say, like, I still sometimes, often I don't see myself as a scientist. I still see myself as a presenter. And so when I'm sciencing, I do feel like an imposter sometimes. So yeah, you're not alone.
Thank you. I mean, that almost kind of, there's a big topic, especially with I see on Twitter a lot with the academic chatter on Twitter, that imposter syndrome. That's a big one that always comes up in big discussion, especially in academia, where we always feel like we are not good enough for what we've done. Like we're pretending that we're good enough, and actually we don't feel that we're good enough. It's just it's a weird concept to try and wrap your head around at times, that actually, yeah, you are doing. I mean, even for everyone in the audience at the moment, really, we are all astronomers at the moment, because we're all together. We're looking at Uranus to try and find these observations. So honestly, I never feel. Same message for myself, I suppose. Same lesson for myself. Never feel that you can't say that you are an astronomer or you're a scientist. If you're going out there and you're inquiring about the world, you want to know how it works, I would say that you are definitely a scientist trying to look at how the motions and how our whole world works. But yeah, sorry, that's a whole tangent on itself that I covered there. Apologies. Any more questions that we have at the moment?
I do have another one.
Go for it, listener.
Well, since it's World Space Week and the focus is women in space, do you want to maybe share, do you have any women scientists or astronomers who inspire you? Or what do you think about celebrating women in space this year? Is it about time? Much needed? Continue to do so? What do you think?
Who wants to speak first? Sorry, if you want to go first, brilliant. Thank you.
I mean, my answers to who inspires me is probably quite cheesy, but it's like, honestly, my physics teacher at school, she was great, and my supervisor right now, Graziella, is amazing. So yeah, those two people.
I'm probably going to be a cheesy. Everyone's got to be a good bit of cheese here. I guess I have like two sources of inspiration. I was going to kind of touch up on one bit, but obviously there's so many amazing women scientists that work at Leicester who I so frequently talk with, whether it is, hey, do you want some cake? Or whether just going to them going, you know what, today has been such a hard day. Can I just see a video of a cat, please? It's just been a really terrible day. But they are some of the world leading experts. They're amazing. I talked before that Jenny Carter, who I work with at my office. My goodness, she's so busy half the time. She's running off to do outreach or take obviously awards or helping out with the SMILE mission. I just don't know how she fits everything in the day, and I am astounded by her work. I also work along with goodness, I could go through every PhD student that I work with, and they're all incredible. I have used a lot of Rosie Johnson's work as well, which we saw Dr. Rosie Johnson yesterday, and her work has been incredibly helpful for what I've been doing with the Uranus mapping. Sorry, just feel free to
I'm waiting till you're done. I want to say
okay, apologies.
Let me know.
I guess the second side of this, and this is where I guess it gets more cheesy. I did send a link to my family just to let them know. So I don't know if anyone from my family is watching, but my aunts in my family have all incredibly inspired me. They have a long mixture. I have one aunt who is a nurse. I have several aunts who work in TV, whether that's like doing line producing, making programs. I have one aunt who is the lead designer, I believe, with EastEnders. So she is incredibly busy, as well as a aunt who works with Sky on managing the programs and is a big lead head on that. And they are all incredible women in their own right. I am always blown away by the amount that they manage, but also that they can additionally just deal with me calling them up in tears going, oh my God, my thing didn't work and it's all going downhill. Do I deserve to be doing this? And they're there like, well, they'll be there going, of course you do. Like you've got the brain, you've got the whole thing. It's no big deal. Like, just all right, calm down. It's all going to be fine. Let's go for it, and you'll be fine. And yeah, they're always right.
That is so important, I think, for women today to have the support of other women around them. So that's even more so to have your family supporting you. And so that's you're really lucky to have that. And I just wanted to chime in about who inspired me. Growing up in California, I'm originally from Silicon Valley, and I went to my local university there, good old San Jose State. But my first astronomy teacher was Natalie Battaglia, who became the science director for the Kepler Space Telescope. She was a huge inspiration for me, and I used to see her at conferences all the time and have a chat with her because she was my very friendly teacher. So, great for teachers, because you both mentioned teachers, and they're huge inspirations to students and make a huge impact and a difference in our lives and inspire us, inspire our curiosity, and for us to kind of follow that through. I see Tom has a hand up too, Tom.
Can I join in, please?
Yeah, please.
I've got so many women that have inspired me over the years. Very early on, my dad's an engineer, so science was never considered to be the right drive, right? You got to be an engineer. But my grandmother, his mother, was one of the first people who worked on semiconductors post-war. So it was always ingrained in us, the sort of the pathway of following research and understanding things in the real world. And then, throughout my career, there's been inspirational women that have really inspired me in terms of the work. So many, it's hard to keep up. But certainly recently, obviously my PhD students have continued to inspire me. Always mentioned Rosie. All my PhD students, whether women or men, continue to inspire me greatly. I'd like to mention, because I've been working on space missions to Neptune recently, there's been a lot of leadership in both of those missions that I've been involved with. So an old friend of mine, Abby Reiber, was leading a diagnostic of whether we could go to orbit Neptune, and she was incredibly inspirational in her leadership of that. And then Louise Proctor was the PI on the Trident mission that I was a part of, which sadly wasn't funded, but probably was one of the most inspirational pieces of fun I've ever had as a scientist. So her leadership was utterly invaluable to building that case, and feeling like you were part of a team. And then Collie Howard was the deputy on that as well, and both of them provided incredible leadership and made me feel better as a scientist, which is what you want from a leader, what you want from someone to inspire you to greatness, right?
Thanks for sharing that, Tom. It's really great. Emma, did you want to say something?
Yeah, no, I was just going to add very, very quickly that obviously a lot of the work that we do here for Leicester as well, one of the people I didn't mention, I really should have mentioned, is obviously with Emma Bunce, who is the head of our department at the University of Leicester, who's also very, very, very involved with RAS.
That's right. She's our current RAS president, and I wish we could keep presidents longer, but I believe their term is only 2 years, and then they leave. I don't want to think about when her term is up, so I'm not thinking about it. She was with us last time at Jupiter. She did such a fantastic job. She was at the National Astronomy meeting this year, our virtual one in Bath, actually. So we're very Bath-centered today as well. She had shared so much. She's so personable. She's extreme generosity. She'll send me an email just to thank me for whatever I did that day as support. Just very generous with her time when she has it. She is, and very thankful. So I'm looking at the time. I'm gonna check out here and leave it to you, Emma, to wrap it up, because I think then you're going to have an update.
Yes, so we do have an update. I was going to ask if it'd be okay if I have one last question for you, perhaps just to round this all off. There's been a lot of discussion, obviously, with everybody, including in the observational chat, about if we could have a mission to Uranus or Neptune, or both. I think everyone would probably go for both, but just in case, which would be your pick for sending a mission?
Oh, that's a hard question. I mean, obviously, I'd want to have an X-ray instrument,
of course,
on board, and I mean, having an X-ray instrument go to Uranus or Neptune would just greatly revolutionize our understanding. I mean, Uranus has a crazy magnetosphere, like we know nothing about its auroras, but then we've also got like Triton at Neptune, and so maybe we can like use X-ray fluorescence to study Triton a bit more. So I don't know. As long as I have an X-ray detector, I'm happy.
Fair. That's really great to hear. Yeah, I think it's a tricky one. I'm so sorry. I know it's the trickiest one to have to shoot on the end, but it's a good question to ask for people. Awesome. Well, I was gonna say we are now making our way towards a telescope update. So thank you so much, Philly, again. Everyone, if you can clap your hands virtually and in person. There we go. Thank you so much for your time. Really, really do appreciate it. It's been wonderful to hear about your work, as well as having you here today. And we hope that you continue to watch for the rest of the day if you have time, and maybe tomorrow as well.
Oh, will do. Thanks very much.
Awesome. Thank you so much. So today, yes, we are now at about 12:15 here in the UK. If I recall correctly, let's do my maths very, very quickly. Yeah, so I think we're about 1 in the morning in Hawaii. So our current view, let's see if I can get a close up. There we go. So we have the Uranus cam in the middle. So this is going to be kind of reiterating what we saw originally. So we've seen 3 moons, I believe now. I think we have Miranda on the right-hand side, followed by Ariel and Umbriel, which are on the left-hand side. I think we may only just be able to see it, but it's very difficult to see it on the stream at the moment. Tom, did you have something to add on that?
Well, I'm just trying to get a view of the rings. I've been playing around in a different window and it fades in and out, but what I hadn't appreciated was that the rings are actually effectively a halo around the disk. So they don't cross in and across the planet at all at the moment, which is great for us, obviously, but it makes it a little tricky to see them. But I can certainly play with that and try and zoom in on that Uranus cam a little bit if you'd like me to, and I'll see whether I can
if it's possible,
pull out something that's worthy of I'll work on that in the background. You carry
Yeah, no
on.
worries. I was gonna look over. So I believe we still have the star. It's incredibly hard to see, but there's a larger smudge. I'll see if I can get my mouse over to it. Just about here. I think that is still our A0 star that is making its way in the background.
That is not. I think
Oh,
that
it's
is the
not?
moon. That
Okay.
the star is this bright object off to the right slightly. It's
Ah,
moved away from the planet. It was actually covering the rings and has moved to the right, basically, because
okay.
Uranus is drifting to the left across the sky. So the
My
three,
apologies.
the three up at the left-hand side here are three of the moons. I'm going to pull up. I'm going to sound like I know what I'm talking about now because I've got a little picture to tell me. But yeah, so Miranda is that faint blob. And then Ariel and Umbriel are the two brighter moons.
Okay.
And then that big bright object is
This one's the
actually
sun.
a star moving out of the way, which one of our viewers told me was a magnitude 10 star. I mean, I can't. It's a
Wow.
star. I wouldn't know, but I
It's
believe them.
exceptionally bright. Awesome. Well, thank you very much for the update on that, Tom. I do appreciate it. So we're going to look towards the spectra now. So I'm going to dart over as Tom has a bit of a zoom in on the Uranus cam. So I'm just going to have a little bit of a wonder because we now have the Q1 line that is now making its way out. As Tom mentioned before, we are getting what looks like perhaps a asymmetry in the line. What we mean by an asymmetry is that the top part of the line is brighter than that of the bottom part. For us, if we look back at, let's see if I can get James's wonderful video. That's the previous one. For us, what we're really excited for is if we're seeing in peaks of emission at the edge of the slit, that's probably evidence that we're seeing the northern aurora. Though if it is more towards the middle, that's probably the southern aurora that's kind of making its way out. So any kind of these asymmetries that we're seeing are key points that perhaps we're observing the aurora at. So I didn't know if you had something you wanted to add there, Tom.
Just that rather usefully, they've also James has also included the halo of the rings in that diagram.
Yes.
So that oval that we saw is the location of the rings. But Uranus is actually really bright, so it's sort of bigger than it actually is in reality in terms of its size because it comes out. In this figure, you can sort of see the rings fading in and out. But hopefully we can get that live. I'm waiting for the beam switch to happen, so we move back. But I'm not sure how far that is off. So once the planet moves, we should hopefully get back to where we were, and I'll see if I can tweak the colors to the point where the rings reappear.
Sorry, there we go. So, but yes, that's kind of a round off of where we are with the telescope at the moment. In the meantime, we have, let me just quickly check, make sure on our schedule how long we've got. So we have a Q&A session at the moment till about for another 20 minutes or so. So that's where we can now finally get towards the questions that we've been having queued up in the Zone. Thank you so much, everyone, for your patience with this. So first off, let's see where we have. So we have another question from Gwen McNoll, who asks a question for the queue, perhaps for Heidi Hamill when she's on. So perhaps that's one I should leave for a little bit later, actually. Apologies. We have, what is the average surface temperature on Uranus in Celsius? That's a good question. I don't know if I'm going to be able to exactly answer this because I'm more knowledgeable on the temperature in the upper atmosphere of Uranus. There are different, well, perhaps Tom, I could talk with you about on that part. I mean,
well,
the temperature.
That would just be me going to Google and looking the answer up for everyone else. Again, people like Lee Fletcher would be completely au fait with this. And the big question is, where do you mean? So the temperature structures of these atmospheres changes very dramatically with positioning. And so, sometimes you're looking at a temperature for various different layers of the atmosphere. For a planet like Earth or Mars, it's much easier. You go to the surface, but even there, of course, are you in the pole or are you at the equator? And the temperatures can vary significantly.
Exactly.
If we switch back to the Uranus cam, you can see a halo. Look at this beautiful purple fringe around the planet, and that fringe is the rings. So we're picking up reflection off of the rings all the way around the planet here. If I move the camera down a little bit, you can see it on the bottom side too, and slightly to the edges. It's a little hard because it's caught up in the glow of the planet itself, but we're picking up enough light that we're able to see a slightly oblate shape, which is really beautiful. So that's the rings, everyone.
Wonderful. Thank you so much for that, Tom. Yeah, I was just going to add on, similar to what we were mentioning earlier, that it honestly depends where you mean on temperature with Uranus. James has let us know that the surface, you could say, which is at 1 bar pressure, is about minus 195 degrees Celsius. So that's certainly very, 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 very chilly. Here for infrared, we have continuously documented the upper atmosphere of Uranus, and we saw it back at, I think, 750, I think is a bit too high, but about that area back in 1993. And since then, we have continuously seen about 8 Kelvin per year decline in the temperature at the upper atmosphere, to the point where we're now looking at temperatures of almost half that we saw back in 1992, 1993. So it's phenomenal. And it's crazy what's kind of going on with Uranus. And as Tom pointed out, that there's so many ways that you can answer what's the temperature for Uranus.
I mean, the important point is that that's really, really cold, right? And what makes Uranus really unique is that it's basically heated by the sun. There's no thermal energy coming out. So certainly at Earth, we have a thermal radiance out. That's what makes all of the volcanoes. But it's especially true for places like Jupiter and Saturn and Neptune, more than any, actually. What particularly makes the contrast between Neptune and Uranus special is that Neptune has more heat coming out of it than Jupiter or Saturn, and Uranus has less, and so we really don't understand that contrast. And so it's super cold, basically, because the sun is very far away, and there don't appear to be any other ways of heating the atmosphere.
So I was just looking through some of the other questions we have. We had a lot of questions from Zayan, who I noticed I think there's one that we can at least very quickly comment on, which is, why is Uranus blue? And that one's to do, if I recall correctly, we were discussing yesterday, that's to do with the methane within Uranus's atmosphere, which basically reflects, absorbs the rest of the light and reflects out predominantly blue light. And that's why we see Uranus light up blue in its color. Today, obviously, it looks yellow in our spectra and in our cameras, but that's due to the artificial light that we have we have here. So that's that one. Does Uranus have any volcanoes? Is another one from Zayan. Which, to my knowledge, Uranus does not have any volcanoes. I don't think any of the moons have any kind of volcanoes like we see at Jupiter with Io, if I'm correct.
That's a much harder question, right? And I don't think we know the answer to that.
Yeah.
Uranus doesn't have volcanoes in the traditional sense because it doesn't have a surface. If you dropped something into Uranus, it would keep falling until we would lose contact with it as the pressure crushed it. There might be a surface somewhere far down, and there might be volcanoes on it, but it would be a very ethereal place that we wouldn't really understand in the way we understand volcanoes on Earth, for instance. There's no evidence for any volcanoes at Uranus, but we have so little data that it's very hard to get a real sense of that. And what I would say is there is evidence that some of the surfaces of Uranus are weird or fresh. So Ariel has a surface that is quite fresh. Fresh means, the surface is less than billions of years old, but it certainly indicates that maybe there's some kind of resurfacing. And if there's some kind of resurfacing, that may indicate that there's outgassing similar to like Enceladus or maybe Europa. So there's a definite possibility that if we go back, we will find some of those volcanoes, but we don't know.
Awesome. Thank you very much for the help with that, Tom. So I have another question, which I think we discussed a little bit yesterday, if you don't mind me asking. which was, has Uranus probably been hit as to why its rotation is so out of kilter? I think we were discussing yesterday that there are a lot of theories into why Uranus is so funky, essentially, with its orientation. Would you be able to enlighten us a little bit?
Yeah, well, it's an interesting field. It's not my field, so I don't know the current thinking, but I've certainly been in meetings before, scientific meetings, where lots of discussions about how you tilt a planet over. Some people argue that, well, the Earth is slightly tilted, and so are quite a lot of the other planets, so maybe they were hit once, and Uranus was actually hit multiple times to make it tip over that much. Other people argued that it was indicator of just one impact, and then most planets maybe were hit less than that. I've seen arguments that there used to be two giant planets around Uranus, and they gravitationally destabilized each other. One fell into the planet, the other was slung out of the system completely, and that gravitational interaction was enough to destabilize the pole. There's also all sorts of really interesting arguments about that tilt for other planets. So one of the things that we do know is that we have a very stable long-term climate on Earth, because the moon stabilizes our precession and stops us tilting over. And there are some people that have modeled Mars and shown that potentially Mars has had much more inclined tilts in the past. So maybe it isn't so surprising that there is a tilt, and maybe it's not a permanent thing. Although the fact that the rings themselves are, and more importantly the moons are there, does suggest that they've been pretty stable for a long time.
Wonderful. Thank you so much for that, Tom. I have another question whilst we're continuing with our Q&As. We have a wonderful amount of questions from everyone. Please do feel free to keep sending those questions in to us. So we have another question with Zoom, which I think is really interesting, perhaps for both my perspective and Tom's perspective on this, but are there any suggestions on how someone can enter the field, I presume of space observing, and are there any internships offered to someone that they can apply for?
I mean, there are pretty hard limits on getting into astronomy in terms of needing a degree, right? And so you need a scientific degree, I would say. You don't need a physics degree necessarily, but you do need a degree in one of the STEM subjects as an undergraduate. And then typically the way forward from there is to do a PhD either in planetary science or in an associated field. The specifics of what you do actually don't matter too much, and all of us have come from different areas. So Lucinda was saying that she came through from geology. I came through a planetary science degree that was very geology based. I've had colleagues that have gone the other way and now study the geology of the surfaces of the moons that started out with a physics degree. So the exact pathways are never quite so important, but it's very difficult to get into a PhD program if you don't have a STEM degree. It's unlikely that you'll be able to get a funded position, certainly. And then, there are certain skills that you just need to learn, and the apprenticeship effectively is what Emma is working through now. In completing your PhD, you're learning a lot of skills about how to research, but also how to know how to research, and building up your skill base in terms of self-guidance and self-awareness in terms of that learning process. And just like learning to create a Damascus sword by hammering at the metal for many years under the tutelage of someone who's done it before, it's just a natural course of what we need to do in order to become able to do these kind of skills and be able to think scientifically. So that's the pathway. It's not as narrow as some people might think. You don't absolutely have to do the exact thing that you ultimately want to end up doing, but it is fairly restricted in being able to become a professional astronomer, certainly. But there's lots of avenues for investigating the solar system. There's no limitations on buying a pair of binoculars and going into your back garden. So there's lots of ways that you can investigate the solar system and the universe on your own as well.
I was going to add on that at the moment, there is such an incredible push, I would say, in the scientific community at the moment to get a lot more investment with just with amateur telescope operators, with anyone that uses their own telescope. I hate using the word amateur because you'll have people who have been using telescopes for probably longer than I've used telescopes. So I would say anyone that has a telescope being able to just take observations of the moon, being able to just give us ideas of what's going on for day to day for Jupiter. Because again, I think today highlights we're getting 3 days at Uranus, but that's only for these 3 days. And then we're not going to be looking at Uranus for another 2 months, I believe. And it could have done anything in that time. So if somebody was able to come to us and go, hey, actually, I've spotted this, that would be phenomenal, because one, we could actually discuss with yourself and looking at stuff, but second of all, getting that data in really fills in the blanks where we, as astronomers who give our time to try and sort this, don't always have that data on hand.
Oh, it's a fundamental point, I think. There's a lot of science now that happens through direct communication between astronomers that can work every night looking at objects and astronomers that have dedicated observations for only a few nights a year. And that's really the only distinction. So Lee Fletcher, who was on yesterday, is a big proponent of this and works very closely with astronomers that observe daily. So the range of quality that you can see will vary greatly when you go into your back garden. And if you're looking with your binoculars, you can see amazing things. But some of the people that work in that community are able to produce images vastly better than we are seeing now in terms of the quality that you can get. And their long-term monitoring is essential for a lower atmospheric understanding of what's going on in these planets. And also, they're able to detect impacts on these ones. So certainly a week or two ago, there was another impact into Jupiter that was detected by an astronomer observing every night using their own technology. And those alerts go out. So there's a throughput from astronomers looking in their back gardens, reporting on what is happening in these worlds, either because they're able to see features on the atmosphere or changes in the atmosphere on short term. They're able to see impacts that happen right there and then, and it allows people with access to these large international telescopes to slew over. And so often we'll be asked by colleagues in the wider community to spend 5 minutes looking at something slightly different from our science aims. Certainly we've done that in the past at Jupiter. Instead of going straight to the Aurora, we'll have taken some filtered images at different wavelengths, basically because someone observed something in their back garden. And it's so interesting and important that we'll take a little bit of time out of ours to pass on to colleagues that know more about the lower atmosphere.
Awesome. I was going to add one final thing. I appreciate that we've probably been about 5 minutes on this question. I kind of wanted to add a spin that I had whilst trying to sort out, trying to get a PhD myself. I originally was trying to debate whether I wanted to go and look at internship projects and get into space that way, because my area I'm focusing with is kind of looking more towards the industry side of things. And there is it depends if the anonymity that sent this question is from the UK, but there is what's known as the SPIN internships, or the space placements internship in industry. It's run by the Satellite Applications Cohort, but they actually work with a lot of industries in space industries in the UK, which typically may not have the kind of research that we're doing, but certainly help a lot with the instrumentation, with satellite construction, and a lot with the communication side of things. So if you are interested in kind of going into that area, I would definitely suggest looking at SPIN. There are other internships that also come up. It's just simply, for me, I find that as soon as you start looking at these specific areas that are like, hey, we have a placement, you'll find other industries that are going, hey, we also have a placement. Come along, and we'd love to have you come along and basically take these placements. Again, it's similar to what Tom was saying. They will have these restrictions, unfortunately, with the academic side of things. I know some internships, I think it's A levels rather than having to have a degree. But again, that will vary on the amount of information and the amount of work or data or project that you'll be working with and who you'll be working with on that side of things. But if you are interested, I would definitely, it sounds very dull to say it, but having just a thorough Google search of what industry placements there are out there is always a good one.
There's also a lot of opportunities to do citizen science. So there's all sorts of wonderful projects like Galaxy Zoo that allow anyone from the public to to get involved and work and help, because basically the human mind is by far the best machine for processing data. So often if you just get 1,000 or 2,000 people to look at your data, it's a much more effective way than running it through some rather weak machine learning process, or by having some fundamentally flawed process.
I have another quick question, I think, from Gwen McNoll, who asks, it was mentioned yesterday that you're using infrared telescopes. Is this because infrared delivers the best quality, or do different wavelengths give different information? I think this is a good one. I think Ophelia kind of touched up on this actually, because I think looking at the time on this is just before Ophelia's discussion. But we pick up similar things, well, I say similar things at different wavelengths. So over many wavelengths, we can detect auroras. In Ophelia's discussion, she was saying earlier that we can see Jupiter's aurora in X-ray, in visible, in ultraviolet, and in infrared. So obviously it can show us a lot, but depending on the wavelength is how much information we can actually get. So for us with infrared, we are able to get an idea of the atmospheric temperature, or really the upper atmospheric temperature, the ion density, and depending on which way that we have the slit on the planet, we can actually get a measure on the velocity, or how quickly the winds are in the upper atmosphere. So that's why we look at infrared, because not only do we get an idea of what's being very excited, going, hello, I'm here. We can also get a great idea of what internal changes are happening if we see long-term changes, short-term changes of those temperatures, and actually get an idea. I know one of our colleagues at the moment is writing a paper at Saturn looking at the ion winds and seeing how those how those move on Saturn, and how it actually leads to a very fascinating concept that I said our colleague is currently writing up and hoping to publish soon.
Yeah, I mean, it's fundamental, isn't it? The question of whether you aim for higher quality or you aim for something specific. It's always something specific with science. So the spectra that we can see in the spectrocam are useless if you want to understand the lower atmosphere. You can't even see the lower atmosphere in these wavelengths, which is good for us because it means that the lower atmosphere is not getting in the way of the upper atmosphere, and we're able to get very clean signature. It does mean that the quality that we see is lower than if we looked at other wavelengths. It's very energy specific, so the shorter the wavelength, the better the quality that you get. So when you see adaptive optic images from Keck, they are usually at much shorter wavelengths because you can get crisper, cleaner images out. But our focus is looking at specific wavelengths, specific windows, looking and hoping to find unique characteristics of an atmosphere, and that's how we decide where we're going to look, for sure.
Awesome, thank you so much, Tom. So I think we have got to the end of our Q&A for the moment. That's not to say that we're not going to be coming back. We should hopefully have some time later on in today's live stream. If you have any more questions for us at the HT Plus team, feel free to let us know. Otherwise, we're handing over back to Lucinda and hopefully to our new host for the afternoon.
Ooh, gotta remember to unmute myself. Not yet. Anyway, let me do a station identification. I am excited to bring our host in. He doesn't officially start until 1, so it's still me. Okay, so let me just let our audience know. Thank you again, attendees, for being here. We have a lot of people on YouTube. I want to let HT Plus team know that I don't know if you noticed, we as of last night, we had 2.7 thousand views on day 1 already. And the registrations have kept increasing. I think probably up to 600 now, if not more. So lots of really cool stuff. People are enjoying it. As you heard from Dr. Dunn, he was also like, love the concept. And again, this was an idea that, as far as I can tell, came from Dr. Tom Stallard to do remote science. He was going to do it for NAM 2020, which got postponed by us. And really happy he contacted us. And I'm really feeling very grateful to be a part of it again. So thank you very much for having me Royal Astronomical Society be a part of this with the University of Leicester. We are here in day 2 of the weird and wonderful world of Uranus, a live stream, a 3-day event that we started yesterday, and we're going to keep going until tomorrow. This is going to be the last time you're going to see me, and that's okay because it's time for other people to take the reins, and I'm happy to pass them over. But let me just go over with today's schedule and what we've done so far. We started with watching Emma on her own this morning, setting up and working with remote astronomers, I think Nahid and Rang and possibly Dr. Stallard as well, trying to set up the telescope this morning and making sure we wanted to see what we want to see and get the data that she needs for the science. And she gave us a great presentation this morning on Uranus. And we also heard again from Charles Draper and Dr. Sean Prosser from our RAS librarian. She wasn't at the library today, but that's okay. She gave a fantastic presentation. You can watch it on YouTube if you'd like. All of this is being live streamed on YouTube as well at your leisure when you have time to. She had some fantastic, crisp, clear images of books from Carolyn Herschel, which are a treat to always have an option to see. We're going to get throughout the day, we're getting telescope updates and views from Emma. Thank you so much. We just heard from Ophelia Robisono on the work that she does with XMM Newton. And we just finished up a Q&A with the H3 Plus team members, Tom Stallard and Emma Thomas. And just to remind you all what we're doing, I'm Lucinda Offer, Education Outreach and Events Officer for the Royal Astronomical Society. And we're just sharing with you what professional astronomers do. This is World Space Week, and we are highlighting the research of Emma Thomas. And she's in her 3rd year PhD at the University of Leicester, whose research is to investigate and document infrared aurorae at Uranus, so that we can understand how space weather interacts with Uranus's magnetic field and atmosphere. We've had Dr. Tom Stallard, who's a planetary astronomer, also at the University of Leicester. And I think it's about time we do a little chat here with Dr. James O'Donoghue, who is a planetary astronomer at JAXA. So he's tuning in from Japan. I've been wanting to say konnichiwa, O'Donoghue-san.
Thank you.
Oh, genki desu ka? So
I would say hi.
He graduated from the University of Leicester in the UK with a PhD in planetary space science before moving on to Boston University and even a fellowship at NASA's Goddard Space Flight Center. And I've been excited to speak with you. I'm going to stop sharing my screen now because I'm going to bring Dr. O'Donoghue in here and add to the spotlight so that we can have a little chat about, I think it's so exciting to share some of your fantastic animations. Even though I have a science background, I also have an art background as well. I was very interested in graphic arts, and what I love about the work that you do, and I'm going to share my screen here, and if you want something to share, just let me know, not a problem, but is so helpful to me. I'm so grateful and thankful that you do this work because it helps me understand these concepts, and I'm sure it helps lots of others also understand these very complex concepts, especially now looking at Uranus. And with these animations, is there something you want to talk about? I'm going to play some while you do. This is one that's pretty cool, I think. So what inspires you to do these?
So basically a series of unusual events, I think. So towards the end of 2018, we had a press release on Saturn's rings. Saturn's rings are leaking water into the planet. That's eroding the rings. It's going to make their lifetime a lot shorter. They're not going to be there forever. They're going to disappear in a few 100 million years. So get out and see them while you can, I guess is the usual thing we say. But what happened was we had a press release coming out on a Monday, and we'd shown the mechanism of ring rain. We'd shown how water is falling in from the rings to the planet. But what we hadn't shown, as I realized at the weekend, was what the rings might look like in the future. So I ended up making a video to show roughly the rings disappearing. And that was kind of a rush job. Maybe took me about 12 hours or so. I think if I even uploaded it, it's at the bottom of that list there.
Was it one of these?
Probably one of the first ones. So right at the bottom.
Oh, way at the bottom. Oh gosh.
Yeah, that's the one. The demise of Saturn's rings there. Yeah. So this one, oh no, not that one actually. that's a sunspot thing. Yeah, really amateur. I didn't realize it was still there. The one above, it says the demise of Saturn's rings, has like a fast forward symbol on it. There we go. Yeah. Okay. So this one was the first video I ever made. It took about a day on a Saturday, and then that was the first video. I've never made an animation before this. And then on Monday, the New York Times used it as in the top of their article, and I was thinking, wow, okay, that took not very much time. I mean, it took a whole day, but when you make a press release, you normally have to kind of beg for someone to make a graphic for you, and you have to tell them months in advance. And so, that leaves you quite despondent about being able to make a graphic for you. And so taking charge ourselves was really nice. And then the US government shut down days later, actually. This is the 35-day long US government shutdown. This is when I worked at NASA. And because of that, I was at a loose end. We were told not to come into work, not even to check our emails, but we were paid. So what a terrible situation. But yeah, I made lots of light speed animations after that. And and this one, yeah, this is one of the first ones.
We've been using this one.
Yeah. Yeah. They're still spinning every time I click on them. Yeah, it's been a long journey actually in the end, and sharing these things on Twitter, lots of good feedback from the public and from educators using them. And that's really, there was a bit of a catalyst at first, sort of seeing how much impact the number of hours put in to make a video versus the number of sort of viewers and everything seemed like a really good, convenient way of doing it. And so, yeah, it just kind of spiraled out of control since there.
Yeah, they're amazing. I mean, you have there was one that it was just showing, that's very helpful to see all the axis tilt of the planets and also their spin and direction of spin. And especially looking at Uranus, so many questions come in again about what happened to Uranus. So we've been showing your theory video, but there was one that they're all really excellent, obviously, but there was one that showed a Venus, which is, also a very interesting planet in its rotation. And because of what its year is, its day is longer than its year. I think that's what
you're So, yeah, that might be closer to the top.
I saw it early and I was like, oh, there it is.
There it is, yeah. Yeah, it's actually quite confusing. So we always quote, a day is longer than a year on Venus, but that's for a sidereal day. And when we think of a day, we think of the time between sunsets, right? That's our daily life. You ask anyone on the street, how long a day is, they're not going to be talking about stars relative to stars. But actually, if you consider the time between two sunsets on Venus, there's actually nearly 2 of those days in a year. So it's not really a misconception. It's just kind of a nuance. And I wanted to highlight that with this animation, just showing explicitly, obviously not to scale, I was going to say, and that stick doesn't exist. But I think I wanted to sort of bury it. Whenever someone mentions it, it's actually quite hard. It takes probably, at least on Twitter, a couple of long tweets to explain it or a big explanation. And so having a video just to hand is really convenient. And in fact... Yeah. Oh, in Japan, for example, like I've done an outreach event or two here before the pandemic started. And sometimes it actually cuts through the language barriers a bit because they have a question and I can say, I know what they're asking, but then I just pull out my phone and then I point at an animation and like, okay. And it does a lot of the work for me, actually. So it's helps me be more lazy. Yeah.
It's such an incredible sort of this one's one of my favorites. I laughed when I saw it because I'm thinking 5 hours.
Yeah, this is a 5.5 hour long video showing light speed from the sun to Pluto, and this will be what I'm going to show for the next 5 hours. Actually, yeah. So I'll see you tomorrow. Yeah. there's music at the beginning, and this is I guess a side thing, but there's actually, I think there's some music on it. There's some basic free music from YouTube. The longest track I could find, maybe about an hour long. After an hour, it just fades out, and then there's no music for the rest of it, which I think it's kind of nice and eerie now, thinking back to this. This isn't one of my most popular animations.
I'm playing it. Okay.
Yeah, and then it just
something.
disappears. Yeah, I think maybe near or after Jupiter, it's gone, and then you think, okay, well, I guess you don't hear anything in space or something. But...
Well, I mean, I'm looking at it now, and I keep checking. Am I playing it? Is it playing? Because I don't see anything.
Yeah. It's very subtle. Yeah, you have to scrub through it.
Nothing says the speed of light like very slow, ominous piano music.
Yeah, that's right. Hard to get free music out there. Yeah,
I know. That's it. Well, I mean, are you getting paid for these? Like, makes a lot of sense. I've licensed.
No.
Yeah, exactly.
I don't monetize it. There's no ads. If I add music, I could add music for free, but some music you add that's popular, like the good music, is not free usually. So I don't bother with music or any sounds, because if you do add music, YouTube can add adverts to your videos by themselves. It's a big hurdle for me. I can't be bothered to learn all of the copyright stuff. I don't want to cause any problems, actually, so I just kind of ignore it. And then I just say to people, oh, you can't hear it in space because it's a vacuum. So well, so it's my cop out. If I had more time, maybe. Yeah.
So impressed by this video that you just turned out like the next day for this event. So thank you very much. It's been very helpful.
Oh yeah, no problem. Yeah, I based it off the figure from the actual proposal that Emma Thomas and Tom Stow and everything made the. It was a nice figure showing in each step. So that was the inspiration, really. So I just basically copied the idea and span it around a bit. But
so yeah, I'm showing these pages because, well, this is your Twitter feed. If anyone wants to follow Dr. James O'Donoghue, you can at PhysicsJ. Here's another. This one's really cool as well. Huh.
I leave that on the top as a pinned tweet forever.
Yeah.
It makes me dizzy going back to my own page.
Yeah, this one. Okay. Oh, yes. Oh, this is like a two-parter, isn't it?
Oh, a 4-part. Yeah.
Oh, really? That's 3 or 4. Got it.
I have a secret story about this that my wife might not like, but I actually made all of these as separate parts. And then after maybe a few months, I just thought I was kind of a loose end for a little bit. And I thought, I'm going to combine just a little slice of each one of these 4 videos and put them together in one. And she said, what are you doing? You've already done that. And I said, I don't know, really. I'm just playing around. And then it got like 3.2 million views. So I kind of go, aha.
Yeah.
But to be fair, I've done the same thing before. I've duplicated sort of things and it hasn't gone so well. But yeah, it was fun to link them together. Yeah, it was easy to do. But
and we're so lucky that you, well, I mean, obviously enjoy doing this because it takes time to do video. I do a lot of editing for the IRS and stuff, but you seem to churn these out pretty well. So you're highly skilled at it as well as an amazing planetary scientist, astronomer, astrophysicist.
I actually find the Premiere Pro, the editing of video voice stuff and all of that, I would find that a lot harder. I gave a talk which was pre-recorded, and editing that it took me the whole night, and I prefer making an animation, honestly.
So can I ask what you use to make these animations then, if you're not using?
Microsoft Paint, mostly. I'm kidding. No, I use After Effects, Adobe After Effects. But you can use Blender, which is a free tool as well. I don't use that much, but Professor Elizabeth Tasker, who's coming on later, actually uses Blender. We're the only 2 English astronomers in JAXA. And we do animations on the side. I don't know if it's a prerequisite for working here, but
these are fantastic tools for the public, but of course for teachers as well. I just think they're absolutely fantastic. I wanted to also say to you that, I think YouTube is kind of making it mandatory to have ads. So, go to his YouTube page now to see these ad lists, because I think at some point YouTube's just going to smack ads on the front of every video that gets played. So
is it?
Yeah, and you, I mean, if it helps you to do more, I know it seems like you're really happy to do them, but I mean, if they're going to monetize it anyway, you should get some benefits from that. This is a fantastic service from it. Am I wrong? Did you recently get an award for the work that you do? As far as
it was a Nobel Prize in animating recently. No, good. It was a Europlanet Prize for outreach. Yeah, so it was the Europlanet Society based in Europe. It's an outreach prize. Yeah, I
am very gullible because look at that. So
I'm sorry. Yeah, it's going to be jokes for the rest of the night. It's Saturday night here.
Everything you say. Oh, right, you're in Japan. What time is it?
Oh, it's 9 p.m.
Okay.
Yeah, coming up to 9 p.m.
Not too late. Okay. Well,
not too bad.
This is gorgeous. Absolutely gorgeous. So what I'm going to do now is I'm going to check in.
That's not mine, but.
Am I playing someone else's? Oh,
yeah. How dare you?
Well, just take a look. So, how do people find? I guess if they just do a search on Dr. James O'Donoghue, I'm sure it'll all come up. You do even have your Twitter.
It's linked to the Twitter actually, so it's probably easiest. Physics J on Twitter, and then you see there's a link on my profile to this. Yeah.
Click on videos. And look at all the resources, that you have made. And this is only in the last 2 years.
It doesn't feel like I've done those. To be honest, some of them are duplicates. So if you see some that look the same, maybe you see like 3 or 4 different ones of 4 or with 8 planets or 10. You can actually see that they get sort of maybe better with being more close to now. And that's basically kind of one of my styles I like to employ to when I post things on Twitter, I get lots of feedback, lots of questions and answers. So I make a new version based on that again and again so some of them are on version 4 or 5 after feedback from dozens of astronomers and thousands of people. And so hopefully they're getting to a point where I'm happy with them. But also, it's fun to sort of preempt people's frequently asked questions with things. When I post things again, maybe I could answer the main questions instantly as well. Kind of getting greedy, just trying to condense all of it into a small time period. I know people are busy, right? So they're in a metro or something, and I need to learn about Uranus right now. I try and
they get greedy because the word for me is generosity. The amazing generosity you have in creating these and sharing these freely with the public. Just thank you so much for doing that, and obviously also a thank you obviously from your 135. Is it now almost 136,000?
135 followers. Yeah.
You told us the other day it was 134. Well, it's
nearly. I went up a bit. Yeah.
A little bit. So
it doubles every year or something.
I'm going to pass the baton to you now, and you're going to take on hosting the rest of today's event. I know you're a natural and have tons of followers, so I'm sure you're going to be really busy on YouTube following the chat. I'll be around to help out with that as well. And I'm so excited to listen to your next guest. So I'm going to leave it to you to take the reins. And I probably should make you co-host. And as soon as let me do that first. So hold on, James. There we go. Okay, great. I think I just made you.
Thank you.
Co-host. Is that right?
Oh yeah. I think I can see all sorts of new options now.
Okay, thank you so much.
Yeah, it's like I just got an infinity stone or something.
Well, thank you so much, and I'll still be here around the background, and have a great day. Some exciting speakers with you as well. All right.
Yeah. Thank you very much, Lucinda. That's awesome.
Yes, thank you so much, Lucinda. Thank you for today.
Yeah, it's been a real pleasure to see all the events yesterday and this morning, making sure I'm saying the right thing since it's 9 p.m. here. So earlier today for me. But thank you very much. And Emma Thomas, you're doing an amazing job. I'm just in awe, actually, the amount of things you're running at the same time, and getting good science results at the same time. Good, so science, outreach, fun. I was told this is like a planetary party in a sense.
In a sense, yeah, essentially.
It has not disappointed. Thank you. I think So yeah, we have Steve Miller. I see Professor Steve Miller is online
Hopefully in the
now.
room.
Yeah, if you can unmute and show your video, and there we go. Hi, Steve.
Hi, James.
Hey,
Hi, Emma.
hey, nice to see you.
Hi, Steve.
Background. Hi, Lucinda.
Yeah, are you speaking to us from London or Hawaii?
No, London.
London. Okay, that's good, because these would not be so favorable hours if it was Hawaii. Although you're a seasoned observer, so
yes, that's true. It would be 2 a.m, and I've done stuff at 2 a.m. On many occasions, so not so difficult.
exactly right. Thank you very much for joining us today, and I'll give the proper introduction for Steve. So Steve Miller is a professor of science communication and planetary science at University College London. He's also the vice president of the UK's Royal Astronomical Society, which you might have heard of, and chairs their £1 million outreach and engagement program, RAS 200. Steve's background is in chemistry, which he studied at Southampton University, and he was also a political journalist for the Labour Party in London in the early 1980s, before joining UCL, so University College London's Department of Physics and Astronomy. Steve has used his journalistic experience to help to found UCL's Department of Science and Technology Studies, which he headed from 2002 to 2011, and which made UCL the first university in the world to offer an undergraduate degree in science communication. And that's something I'll get to in a bit as well, actually. His work on calculating accurate spectra of the H3 plus molecular ion, as we'll hear about soon, and that's the subject of of what we're looking at Uranus, helped to identify the auroral emissions at Jupiter in 1988, which is the first time that H3 plus has ever been found outside of the laboratory, outside of Earth. And so, as well as using H3 plus to study Jupiter's upper atmosphere, Steve was part of the team that discovered it at Uranus as well, just 4 years after the discovery at Jupiter, and has since made observations, calculations, and modeling to understand the implications of this ion for all the solar system's giant planets and for exoplanets. A founding member of Europlanet, the European Planetary Science Network, and has led many observing campaigns, including the UK Infrared Telescope's 1994 observations of the collision of Shoemaker Levy 9 with Jupiter, and that's another thing I'll talk about later too. Steve has also run and participated in several European projects on science communication, public engagement, and responsible research practices. And so with that, I will let Steve do the talking, and if you have some slides to show, it would be wonderful. And I just want to point out that speakers are all titans of science and outreach, so I'm very gifted, very lucky today, and maybe take it from here, Steve. Professor Miller, thank you.
Okay, thank you very much, James. It's good to be with you and to be with all the people who are online with us at the moment. I take it the observations are going on even as we speak up on Mauna Kea, is that right?
That's right, yeah. So yeah, they're ongoing now, and Emma is leading the way.
And how are they doing?
Yeah, let's see if we can pull up Emma or Tom to discuss the current status of the observations.
I'm not sure if Emma is around, so I'll step in if she's
Okay.
not here. It's beautiful.
Hey,
We've
Tom.
got some very clear observations today. So some of the people watching online will have seen that we're even able to discern the rings today. It's very clear and clean. And then looking over at the H3+, we've got some beautiful H3+ lines coming through. Of course, whether that will provide us with a meaningful science result will need further analysis. But you can see in the pinned video, we've got a nice clear guiding on the Uranus, and hopefully I will move this window over slightly so we can pick up on the H3+ line and Steve will recognize the Q1 line immediately, of course, down at the bottom there. It's a very nice, clear and clean signal. And the Q3 line up in the top left corner means that we should be able to resolve temperatures and column densities at some level for this data as well. So it's going very well. Thank you, Steve.
That looks absolutely beautiful. Nice, clean spectra. I thought, James, if it's okay with you, I'd just say something about the original detection of H3 plus outside of the laboratory. And I'm afraid I didn't get round to doing a special PowerPoint presentation for this session, but I'm going to use one that I used for a Royal Society project, looking at various collaborations and how they gave rise to new branches of science or new uses of things in science. So is it okay with you if I share my screen?
Absolutely, yeah. Thank you.
Okay, let me go back here and share screen. And is everybody getting that? You getting that, James?
Yes, that's right. It's all there. Thank you.
Right. Okay. So this is the discovery, and you can see at the top there, I put the Royal Society Collaboration Project, and I think I sent James a little article, or the Royal Society put out this booklet 2 or 3 years ago on collaborations in science. And so what I sent James was a copy of my chapter on the discovery of H3 plus in the Jovian atmosphere in 1988. So if anybody wants to download that, please do so. And I think James will explain to you how to do that.
Yes, so just to interject, yeah, I'll paste that link right now into the Zoom, and then I'll paste to everybody, for everybody to see, and I'll paste it onto the live chat on YouTube. And after the session is concluded, I'll post it as a comment as well. So there's no excuses not to click, not to see.
Right.
Thank you.
Okay, so what we're looking at here, I don't know if other people have shown something like this, but this is the summit of Mauna Kea in Hawaii. We as astronomers are incredibly privileged to be using Mauna Kea for our sciences. It's a mountain that is sacred to the Hawaiian people. It's an absolutely amazing site. It's the highest astronomical site in the world at just under 14,000 feet. And it has incredible conditions for viewing. And as Tom has shown you, you can get some really nice clean spectra. So James said my background is in chemistry, and spectroscopy is one of the key tools of chemistry. And chemistry is a vital part of understanding the planets, because it's through chemistry, through looking at the spectra of atoms and molecules in planetary atmospheres, that we understand how they work and what they're doing. And I'm going to be talking about observations. Does my little pointer show up here? Yeah?
It does, yes.
Yeah. Okay, so I'm going to be talking about observations that were initially made using this telescope here, which is the Canada-France-Hawaii telescope. But H3 plus has been observed using this telescope, the NASA infrared telescope, these telescopes, the Keck, the twin Keck telescopes, this telescope, which is Subaru, this telescope, which is Gemini. Where's Ukert? There's Ukert. And I'm not sure about the 88-inch University of Hawaii telescope, but certainly this one, whoops, this one, and that wasn't meant to happen, sorry, going back. this one, this one, this one, this one, this one, and this one. These have all been used on the site of the Mauna Kea Observatory to study H3+. And I thought, because when people hear me say H3+, they think I might mean tritium. I'm actually talking about a molecular ion. So I'm going to introduce this molecular ion. It's a triangular molecule, an equilateral triangle. It's 1, 2, 3 hydrogen atoms joined together, and then you actually find 3 neutral hydrogen atoms. Is not a very stable configuration, but if you take away an electron and if you make the molecule positively charged, you have something that is extremely stable. Why we don't see more of it everywhere is very simple. It's extremely stable, but molecular ions and ions in general are incredibly reactive. So H3+ will react just about with anything it can get its sticky mitts on. And so it's always, in planetary atmospheres, a process of formation followed by chemical reactions, followed by destruction, followed by more formation, and so on and so forth. But this is our friend, H3+, the simplest of all polyatomic molecular ions. In fact, the simplest of all polyatomic molecules, because the whole thing is just held together with 2 electrons, and very challenging as a molecule for chemists originally to understand it, because they could not understand how you could hold 3 atoms together with just 2 electrons. And when it was discovered in 1911 by J.J. Thomson, that very, very famous British physicist, J.J. Thomson, he said, well, this is what it's got to be. And then a little while later, he said, oh, maybe it's not after all. And it wasn't until sometime in the really late 1930s, 1940s, that it was discovered that this H3+ molecule could really, really be stable. So we're going back to September in 1988, and a large consortium involved in this discovery. So the first 2 here, Pierre Jossard, Jean-Pierre Maillard, they're French astronomers from Paris. John Caldwell is a Canadian astronomer. I forget where he was from now. Sang-Jae Kim, Korean. Jim Watson is a theoretical spectroscopist from the Hertzberg Institute in Canada. Wojciech Maciejewski, he's a theoretical and experimental spectroscopist, again from the Hertzberg Institute in Canada. Jonathan Tennyson is my very good friend at University College London, doing incredible calculations of the spectra of molecules that are needed for all kinds of astrophysical environments, including exoplanets. This is me. Sushil Atreya is a very well-known planetary scientist, along with John Clark, Jack Hunter-Waite, and Rob Waggoner. So quite a big team of people actually on the paper that announced the detection of H3+ on Jupiter. And this was the first time, as James has said, that the molecule was found outside of the laboratory, and was a bit of a shock, frankly, for a number of reasons. And then there are people who didn't make it on the paper. Takashi Oka, who's a world-renowned experimental spectroscopist, he discovered the first infrared spectrum of the H3 plus molecular iron. Meyer, Boschwiener, and Burton, these were the people who made a very, very accurate, what's called potential energy surface. So that's what governs how the atoms in the H3 plus molecule move around and give rise to infrared spectra. And then, as I've said, the people and the natural resources of Hawaii deserve an enormous credit in all of this. So we're going to September 1988, and then eventually the publication in Nature in August 1989. Okay, so what was it that Pierre Drossard and his team found? Well, they were looking in the auroral regions of Jupiter. So Jupiter is big enough that you can point the telescope to different parts of Jupiter. That makes it different from a star, for example, where you could, a star is a point source, but a planet is an extended source, or a solar system planet is an extended source. So they were looking at the auroral regions, and they were following up a suggestion from Sang Kim that it ought to be possible to see the infrared spectrum of molecular hydrogen from these regions. And they were looking in what is called the K window, which is an infrared spectroscopic window that runs from just short of 2 microns to about 2.3, 2.4 microns. So a micron is a millionth of a meter, and we're talking about wavelengths here. And there are some key molecular hydrogen H2 lines that they picked up, and this is one of them. This is called the S1 line, and I won't go into all the details as to why it's called that. But here you can see quite a strong, clean signal, lovely clean signal of this S1 molecular hydrogen line. But then all of these guys here, what on earth is going on? And this one is 3 or more times stronger than this line of molecular hydrogen. Well, when you consider that Jupiter is really just a dirty, great big ball of hydrogen, and that's mainly in the form of the hydrogen molecule, H2, the fact that you've got something so strong against the signal from the main constituents, the main stuff in hydrogen, molecular hydrogen, means either there's an awful lot of it, or that it's got a very, very, very strong spectrum. So what was this stuff? Well, I said it was found by the observational team. They didn't know what it was. So they sent it across to Jim Watson and Wojciech Majewski in the Herzberg Institute, and at that time, Gerd Herzberg, who won the Nobel Prize for services to molecular spectroscopy, the father of molecular spectroscopy, he was still working there. And they looked at this and they said, fantastic, we've got a spectrum just like that, and we have no idea what it is either. So they were scratching their heads and they said, well, could it be this molecule H3? Well, okay, that got batted backwards and forwards. And eventually they got hold of Takashi Oka, who'd moved from the Herzberg to Chicago. And Oka had been in touch with Jonathan Tennyson's group, which included myself, and was aware of new calculations on what's called the overtone spectrum of H3 plus. The overtone, normally, if you think of spectroscopy as a molecule from jumping from the rungs of a ladder to a lower rung, then the main spectrum, the fundamental, jumps from rung 1 down to rung 0. The overtone, which should be incredibly weak, jumps from rung 2 down to rung 0, but actually H3 plus is a weird molecule and has an incredibly strong overtone spectrum. So when eventually we compared the overtone spectrum that had been calculated at University College London, went to the Hertzberg Institute via Chicago, and went back to the French, Canadian, Korean team of astronomers, we got that kind of correspondence, and we could tell people exactly what it was. So just go back again. There's their spectrum. Here is the fit from the calculated spectrum. Obviously, we don't fit this line because this is the molecular line of hydrogen. There's one or two other lines that we didn't fit at the time that we fitted later, but you can see these lines of the emission spectrum of the overtone of H3 plus, and it was hot. It was, and why Jupiter and the other giant planets have very hot outer atmospheres is still a bit of a mystery today. So that was it. That was the detection. Now, what was it that enabled this to happen? Well, firstly, you had to have a terrific telescope. The Canada, France, Hawaii telescope is a terrific telescope, absolutely first rate, still doing first rate cutting edge science, even though it was built in 1978. So these guys were built, and all of them on the top of Mauna Kea were built to last, built to very, very high engineering specifications, fantastic instruments. The second thing you had to have was this amazing spectrometer. I myself can't follow it all around, but it was designed by Jean-Pierre Maillard, who has to be one of the greatest infrared instrument builders in the whole of astronomy. And then finally, and this is a very, very young Seymour Cray, who built one of the first real supercomputers in the world and had this amazing chip that could do what was known as vector processing. So this was ahead of all of these parallel processing, multi-processor computers. He had a single chip that could calculate 64 calculations at any one particular time and was an amazing computer. And then one more element in this collaboration story, and that's email, which we all kind of go, oh, old technology now, you know, we take all this for granted. Not a bit of it. When this work was being done, it could take 3 days for an email message to get through to Germany. Hard to think of this now because email's pretty much instantaneous, but that was it. But it was true that email played a really important part in linking all of these things together and in enabling a collaboration, a worldwide, reaching right across the globe, collaboration to come together to make this discovery of the H3 plus molecule. And if you don't mind a little bit of writing, I'm afraid some things that I think make this a good story for collaboration and why the Royal Society decided to include this one, which is a bit quirky, in their book on collaborations in science, alongside all kinds of much more well-known collaborations. So firstly, French, Korean, Canadian and American scientists all using a telescope in Hawaii. The American scientists were obviously the telescope operators based in Waimea on the Big Island, just down the hill, a few thousand feet down the hill, not just down the hill from the summit. Then they looked to a couple of spectroscopists. Well, Oka is Japanese American. Jim Watson is, or was, unfortunately, he's now died, British Canadian. And then they came over to our laboratory in University College London because they heard us talk about the new spectrum that we were calculating of this H3 plus molecule. We were using this potential energy surface calculated by a German-Australian team. And there were times when, because of the time difference, Jonathan Tennyson was actually in Israel at the time. I was in London, Jim Watson obviously in Canada. So Jonathan and I were using email to say, well, we've got these lines, what do you think they could be? We were sending over what we thought they could be to Jim Watson at the Herzberg Institute in Ottawa, and he was saying yes, no, maybe, etc. And we were doing this back and forwards several times a day because of the time differences. We were able to sort of be in touch with one another. Absolutely amazing time, very exciting in my view. And really, you can date the use of H3 plus as an astronomical tool, which is now being used not just in planets, but in the interstellar medium, in our own galaxy, even talk about looking for it in exoplanets and external galaxies and so on. This is where the use of this H3 plus molecule started out. And nowadays it's used almost as routinely as way back when carbon monoxide was being used as a way of understanding the physics and chemistry and space. Now, this is meant to be a session on Uranus, so I have to leave you with the detection spectrum of H3 plus on Uranus. And here it is, 1st of April. No, not an April Fool's joke. 1st of April, 1992. This was, again, incredibly serendipitous. This was made using the not such high spectral resolution, but very, very sensitive spectrometer on the United Kingdom Infrared Telescope. It was, again, a collaboration. Tom Jabal as telescope director, Larry Trafton from the University of Texas, Jonathan Tennyson and myself. And we came to the end of our ability to look at Jupiter on the night sky. It had sunk too low. It was about 3, a bit later than that in the morning. And Larry Trafton said, oh, you know, what's available? Why don't we look at Uranus? And we kind of looked at Larry, oh, come on, you got to be joking. But we did. Why not? Why waste the time? It was going to be 6 o'clock before we could go down in the morning to get the wonderful breakfasts they do at Halepahaku at the ground station on Mauna Kea. So we did, and this is what we got. And as soon as it became clear that you could see it on Uranus, then obviously it made sense to look for it on Saturn. We've been looking for it on Neptune. To my knowledge, unless Henrik Milleen has done something very, very recently, we still haven't found it on Neptune, but it's used as a tool now for at least 3 of the solar system's giant planets. So I think I'll call that a day. I hope I haven't gone on for too long. I'm happy to take any questions that there may be. And James, if you want to jump in with any comments, or Emma.
Yeah, thank you very much for that enlightening talk. And it's one thing that I have your book from that you wrote about H3 plus. It's not actually in this house though, it's at work. I just went to my bookshelf to get it, and I realized I left it at work. Maybe you have a copy. Yeah. So Steve wrote a wonderful book, and this topic about H3 plus, and H3 plus basically holds the universe together. There we go, the chemical cosmos. And when I first met Steve came to the University of Leicester while I was a PhD student, and I got Steve to sign my copy, and it's probably the first scientist signature I have in a book, actually. So I treasure it. Obviously, I treasure it so much that I've left it at work. Safer at work, maybe. Yeah, in a glass case. Yeah, thank you very much. And we have some views of Uranus too as part of this. I don't know if we can see. Okay, but yeah, in terms of questions, I'm going to have a look at the YouTube channel and see if any questions came in. But before I do that, actually, one of the points that was raised by Lucinda before she left was that if it wasn't for your work in the past, none of us would be here today, which is absolutely on point, because without H3 plus, there is no careers for any of us. So thank you very much for finding it.
It's quite fun that I now guess I've got scientific children, grandchildren, and maybe even now great-grandchildren. I'm not sure how many generations it's gone down. What's rather nice about that is that occasionally I still get asked to participate in observing runs and contribute to papers, but I don't have to do any of the really hard work. And I take my hat off to the kind of things that you guys are doing now, and all of these wonderful animations and the way in which you just go through gazillions of bytes of data like this, totally effortlessly. I mean,
more data, more problems.
We were actually measuring those spectra by hand and putting the numbers into data.
It's like a collaboration, but also through time. You mentioned collaboration is very important at any stage, but also it seems to propagate through time, and the branches of knowledge, rather like the tree behind me, which is totally real, branches out into other areas. And we're just on little branches right now, I think, from the main trunk of all of this work. So yeah, it's very fascinating, and yeah, I hope it long continues as well. I had it's kind of like standing on the shoulders of giants, right? So as well, yeah. So one thing I was
going to add one thing, which is
please.
It sounds very silly to say it, but I'm very appreciative that you did take those 3 hours to go see if there was H3 plus at Uranus, or else I wouldn't have really ended up with a PhD project looking for it at all.
You can thank Larry Trafton for that.
Certainly, yeah.
We all kind of went, "Oh, Larry, give over." But he said, "No.
Let's give it a shot.
Give it a shot. Why not?"
Oh, it's wonderful. But it's appreciated, definitely.
So we have detection of H3 plus at Jupiter 1988, then Uranus in 1992, and then what was the year Saturn's was discovered?
So I think it was later in 92. Yeah.
Right. Okay.
So 92 was both Uranus earlier and then Saturn.
You say it was more difficult at Saturn at the time, or?
Yeah. I mean, again, this is something that is a bit weird. I mean, you would have thought Uranus much further away from the sun than Jupiter and Saturn, therefore getting less sunlight, therefore less radiation to create ionization in the atmosphere, to make these ions that you need to form H3 plus initially. Weird magnetic field configuration, weird rotational configuration compared with all of the other planets. I mean, you've probably already explained that Uranus has been kicked over on its side somehow, and its magnetic field is really all over the place. So you would have thought that Saturn would be easier than Uranus, but actually the H3 plus spectrum on Uranus is much cleaner and much, considerably more intense than on Saturn. It's not as intense as on Jupiter, but I mean that was quite a big surprise, I have to say. But science is about surprises, and science is about serendipity and lucky comings together and so on, as much as it is about carefully planned projects and observations.
Yeah, I think that's a good point that can get lost in time almost when you look back at old results and you because the way we write them is very clean, and it's, we went to the telescope, we observed this, and we found this, and it looks so neat. But there's a lot behind the scenes that is not reported, actually. Yeah. And there's a lot of struggles, a lot of accidents, a lot of happy accidents. Most of the work that we've done. Most of the work that I've done, actually, we look at Jupiter or Saturn, and we have one purpose in mind. Oh, we just want to do it for this reason, and then we end up finding unexpected phenomenon, and then it makes us look like we knew what we were doing. Yeah. But speaking of past observations and things, so Shoemaker-Levy 9 was or the impact, the comet that impacted Jupiter in 1994, right? 1994.
Yeah,
so
94. Yeah.
So you were very busy at that time, and between 1988 and 1994, all of these discoveries of H3 plus, and then multiple planets, and then Jupiter got impacted. It's almost like a golden age.
It was exciting times, and that observing campaign. I was up on the summit of Mauna Kea for a month, so a long time. And it was a huge team that we had up there, because doing the kind of remote observing that's going on at the moment just wasn't on. So I think at one point there were 80 people on the summit of Mauna Kea, involved on all of the telescopes, all of them looking, and it wasn't easy observing either, because at that time Jupiter was visible from the afternoon through to the early evening, so the observing conditions were very, very far from ideal. But I never forget. From Hawaii, we got to see the third bit of Shoemaker-Levy 9, fragment C, because Shoemaker-Levy 9 was a comet that got too close to Jupiter, and Jupiter's gravity broke it apart into 20 plus pieces, and then each of these pieces orbited Jupiter one more time before smashing in one by one over a period of a week into the upper atmosphere and even below of Jupiter. So we got to see the third fragment hit from Hawaii, and it was simply amazing to see this enormous. I mean, if you think about a nuclear, this isn't a nuclear explosion, it's just due to the fact that something hitting something else. But if you've got pictures of what the mushroom clouds from nuclear explosions looked like, then this is what we're seeing, only we're seeing it on another planet. And we're seeing it actually 40 some minutes after it's occurred, because that's the light travel time from Jupiter to Earth. So it was quite an amazing period of time, and nobody really knew in advance, would it be just a bit of a damp squib? Would it be spectacular? And there were people who were doing calculations that said it would be spectacular. And there were others who were getting quite a lot of traction saying, no, it's going to be, like, I think the late Patrick Moore described it as trying to stop a rhinoceros with a pea shooter. So, okay, we didn't do any damage to Jupiter, but it was still a little bit more spectacular than the impact of a pea shooter on a rhinoceros. So they were incredibly exciting times, and people were getting data, analyzing it in real time. We noticed, for example, that the H3 plus emissions from the body of the planet completely disappeared because they were swamped by an eruption of super hot methane coming from below, from the stratosphere of Jupiter up into the atmosphere. And it was going so fast that it actually exceeded the escape velocity. So you had the escape velocity of Jupiter at 60 kilometers a second. Well, this stuff was coming towards us at over 100 kilometers a second. So it's the first time we've actually seen a planetary atmosphere blasted off into space as a result of an impact. We know it's happened in the past, particularly at the time of the late heavy bombardment, something like 3.9 or so billion years ago on Earth, and so on. But it's the first time we'd ever seen it actually happening in real time. And then we noticed that, because of the location in the southern hemisphere of these, pretty much halfway down the southern hemisphere of these impacts, that they were putting so much dust and dirt and other stuff into the atmosphere of Jupiter that we lost the aurora in the south of the planet. And the aurora in the north of the planet brightened hugely. And my colleague Nick Achilleos had this great explanation as to how that was happening, that the northern aurorae were brighter because there was a lot more ionization in the north to make up for the loss of ionization in the south, and we needed that ionization to keep the whole plasma sheet that spins around Jupiter like a ballerina's skirt. To keep that going, we needed that extra ionization in the north because we'd lost it in the south. So, that's a kind of a hand-waving explanation, and Nick's explanation is mathematically very rigorous and so on. But these kinds of things we noticed. And then, of course, other people were looking at the impact scars that were left on the planet. So it was a very, very exciting time.
That's right. And actually, our next guest is, in about 15 minutes, Dr. Heidi Hamel also observed this at Hubble with visible images. So in a rare event, equally as rare as it happening, we have both people who are two of the main people who are looking at it at the time. So you were up there leading the IRTF infrared observations.
No, I wasn't leading IRTF. I was leading UCURT, but I was involved in IRTF as well. And I have to say that Heidi's kind of minute by minute analysis of the Hubble images was awe-inspiring. I mean, I note from her bio, how much she's done for public outreach, as well as all the science she's done on Uranus. Well, public outreach also includes talking to your fellow scientists and letting them know what the heck is going on.
Right.
And Heidi certainly led on that in a very generous and a very illuminating fashion. So it's great she's coming on in a bit. So if you probe her a little bit about Shoemaker Levy 9, she can tell you a bit about that as well.
Excellent.
She's a star. She's a star.
Oh yeah. If you're able to, it's totally okay to hang out with us in the panel and converse and ask questions yourself as well. And I don't know, we all probably secretly hope for more planetary impacts to come.
Just not on this one.
Oh yeah, not on Earth. Yeah. Yeah, I think we're pretty safe here on that score for a while, possibly in fact thanks to Jupiter actually. But you know, a lot of people say Jupiter is saving us from asteroids and everything like that. It is, I'm sure, but it probably also is bringing some of them in as well. And I'm not sure what the balance is exactly, and you know, what's the net good that Jupiter is doing. But yeah, I think what do we have here? We have a question for Steve in the Q&A here. So interstellar H3+ was detected April 29th, 1996 at Euclid towards the infrared stars AFGL 2136 and W33A, two bright young stellar objects that are deeply embedded in the natal dense clouds. I thought that was a question before I read it out.
I think,
so,
I mean,
more of a
it
comment.
leads to an interesting part where we've obviously been talking a lot about HT plus the planetary, but obviously, I mean, I've been reading up on the book I frequently go back to, which is the HT plus conference that happened back in 2019, which unfortunately was just before I came into my PhD, but that was talking about HT plus as the molecule, not only looking at it in our solar system, but also outside of our solar system. And as our anonymous attendee has let us know, it's fascinating to know that we can find HT plus outside of our solar system. Would you be able to perhaps give us a bit of an insight on that, Steve?
Okay, so I mean, I think from the early 1960s, as people were beginning to understand the chemistry that was going on in space, there was a suggestion that the H3 plus molecule ought to be playing a role in the interstellar medium, gas clouds generally, and so on. So all of the initial searches for H3 plus outside of the laboratory and outside of Earth concentrated on the interstellar medium. And it was as I said, it was a surprise that it was found in Jupiter before it was found in the interstellar medium. And if you want to read about this, Takashi Oka has written some lovely articles about, I think particularly one in 1992 about this. But eventually, Oka and Tom Jabal, they were able to detect H3 plus in the interstellar medium. And they've gone on with other co-workers and so on to make use of it, really to probe what's going on in dense molecular clouds, diffuse molecular clouds, the galactic center, all of these very challenging environments. And it's really an incredibly sensitive probe of physical and chemical conditions in various environments in our galaxy. So you're going to bring Tom in, is that the idea?
Yes,
I'm here.
with us as well.
Hello.
I was going to say thank you very much for that, Steve. We appreciate the insight onto everything that's happened. Well, James, I don't want to step over you a little on this one, but I know in the schedule we're looking at possibly going back to yours again. Thank you very much, Steve, for for all of your insight. It has been very cool going through the history of HC Plus as we know it.
So I'm going to leave you for a bit, but I may come back again a bit later on, if that's okay. It's just
great, Steve. Thank you.
We've got to do our lunch.
No worries. Have a lovely lunch.
Take care, everybody.
Yeah.
Cheers, Steve.
Bye-bye.
Nice to speak to you. Excellent. Yeah. Let's see.
So at the moment we've got an update from us.
Uranus update.
Uranus update.
That planet.
So just trying to think how to highlight, just so everyone can see. So at the moment I've pulled up Uranus again with the spectra. So our spectra is looking very, very nice. As Steve was saying, our Q1 is looking excellent. It's looking a lot more consistent across the line. Earlier this morning, we were seeing kind of more of an enhancement at the edge. I would say we're now seeing more of a consistency through. So that is perhaps encouraging that we're not actually seeing any aurora at the moment, which is good because it's nice to see that there's nothing happening, because we do expect at some points in these observations to actually not see anything as Uranus rotates around the slit. I think if I bring back up the view, saying before, I really do need to just put a box on this so that I can better demonstrate what I'm meaning, but there are going to be these sections. Again, if you imagine a straight horizontal line on James's wonderful animation that he's made, there are these key moments where we actually don't have either aurora in the slit, and that's where we expect there not to be much of a difference in the light that we're gaining. So perhaps at the moment, that's what we currently have going on, is that we have just the non-exciting part of Uranus. I say non-exciting because I'm sure, as James and Tom can both attest to, at Jupiter and at Saturn, we find very fascinating things that happen outside of the aurora as well. So that isn't to say the same things couldn't happen at Uranus. I know, talking with Tom, we've had a couple of discussions about possibly there even being ring rain at Uranus. If there is at Saturn, why couldn't there be at Uranus? So and that would have its own 80 plus emissions from the surface. So again, that's something that we're excited to see if could be found, if by IRTF, perhaps even by James Webb. So that's fascinating in its own way, but distracting, slight tangent on the whole thing. So let me just bring back up again. So yes, we have the spectra. I don't know. I think we are just about seeing. Again, I need to.
Yeah, I can get that third line over for sure. It is on the edge there.
Yeah, we're seeing a third line come in, which is again excellent. The more lines that we have, the better restrictions we have when it comes to trying to find our temperature. We basically have more values that we can put in to compare against one another to minimize the error in our attempts of finding out what the temperature is, essentially, as well as the column density. So for me, who's going to be using this data, seeing a third line is phenomenal. Yeah, it's just peeking in at the moment, just making our way towards it. It's just on the very, very edge, just here. I'll see if I can circle around it with my mouse. So just in the very top corner. Apologies on that. It's difficult to put all the lines in at the same point. So that's really exciting to see. Again, our view at Uranus. So I'll see if I can change to a more close-up view of Uranus. We have the star that is just making its way into the slit at the moment. I know we had a question from YouTube with John, who was discussing about, obviously, what the impacts are going to be if the star interacts with the slit. How is that going to cause trouble? I think, as Tom mentioned, the star will only be in the slit for and it will be in there for an amount of time, but it will be in comparison to the whole 8 hours of observations that we're doing. It's not going to be there as much. So when we do, let's say, 60 to 90 minutes set of data, which is usually what we need to have a considerable signal to noise ratio for Uranus, the intensity of that star will actually be dimmed out by the noise that was originally before the star and after the star, so it won't be interacting as much. But it's something that we definitely will note in the obs log, if not for my own benefit, because I'll probably start seeing something else coming in the spectra and start freaking out because Uranus shouldn't have something else also coming to say hi. So it's just be a note for myself as well. Otherwise, we still have Miranda. I believe that's the very faint point that we're seeing just in the very top of Uranus, Ariel and Umbriel just off in the distance on the left-hand side. Other than that, the observing team is still in very high hopes. I haven't managed to touch base with them for, I think, about an hour or so, but I see that they are happily chattering away to each other. We will see if we can have a couple of people come say hi, but again, we appreciate that a lot of our focus does need to be on making sure that the telescope doesn't go out of work and still focuses on Uranus. So as many people we can have on there is as best as possible.
Excellent. Thank you. So basically, there's the Uranus cam there showing you kind of a false color view of Uranus and with a bunch of moons. We can't see the rings very. Oh, Tom mentioned earlier we could just about faintly see a halo that is the rings, right?
Yeah. So if you carefully select your ranges enough, you can start to pull out what you might believe are the rings. I think I believe that the halo around the planet. Let's see if I can pull it in. So you can see here, a little bit fuzzy.
Yeah.
You get the color stretch right.
Yeah.
You can definitely see a haze. And it does go in and out, but at times when you get a particularly good frame, you can see a fringing edge to the ring. So that actually one of the bands in the rings around. Here is somewhere on the edge of the planet. Actually, the planet's probably closer in than this, and then it's swamping the instrument with light. But when it's a particularly crisp image, this yellow circle gets smaller, and we get a much clearer view of the halo that surrounds the planet, which is the rings. So we see it basically all the way around.
It'd be really nice to get some lovely auroral temperatures. Looks like you've got really clear skies up there, judging by the data, and you have multiple lines there on the left in the spectrocam. So the more lines you have, the better your temperature estimate will be.
Exactly.
When we started the night, the telescope operator warned us that there were some clouds around. We haven't seen any evidence of that, so we've been very lucky. It seems to have cleared out for the second half of the night. Looking at the webcams, there is definitely cirrus down on the horizon. So as we drop down towards the end of the observations, we might start hitting some of that cloud, but it shouldn't impinge on our ability to do work. And looking at another camera, there's a wonderful set of ray tracing. There is something very, very bright coming up, and I imagine it must be the moon. Because it's not the sun. We know it's not the sun. So anything that's bright enough to cause all of those fringes must be the moon, I think.
Okay.
Thank you.
Excellent.
That's all we've got to report from over here. We'll hand back to you, James.
Thank you very much. And we have a very special guest from very far away from you guys, but not from me. And that is Professor Elizabeth Tasker of the Japanese Space Agency, JAXA, a place that I also work. Let's see. There we go. Hello, Elizabeth. How are you doing? What's the weather like over there?
It's. I think the first thing I would say is it's a lot less sunny than it appears to be outside your window, even though you're effectively down the road from me.
Yes, I have a very large office as well.
Bigger than any other apartment in the Tokyo region.
That's right. Yeah. Excellent. So if you don't mind, I'll give you your formal introduction. Professor Elizabeth Tasker is a researcher and science communicator at the Japan Aerospace Exploration Agency's Institute for Space and Astronautical Science. And her research looks at the formation of planets and stars and diversity of planets outside of our solar system. She writes the Institute's research blog Cosmos, and is also a writer for NASA's Nexus Many Worlds column on solar system and exoplanet discoveries. A popular science book, The Planet Factory, which I happen to have a copy of here. I revealed that this is a fake office. Yes, looks at the weird and bizarre worlds that we've discovered and how they might have formed, and whether any of them could be called home. And in Elizabeth's free time, as she notes rather extensively during the pandemic, she rescues cats. And if you follow Elizabeth on Twitter at @girlandcat, then you'll see lots of lovely cats, moggies. And so an excellent service. I wish we could have cats in our house, actually, but they're not letting us. They allow us to have a baby, but not cat. So thank you, Elizabeth. It's nice to see you. Long time no see in real life.
Yeah, definitely. Yeah, so I have had a small problem, and that is last Thursday I gave another talk, and my microphone found it so exciting it actually lost its head entirely. So if you see me using two hands to describe my talk, which I sometimes do, and then the sound drops, it's because I've let go of the microphone and it's fallen to the floor. Sorry about that.
No problem. No problem.
Yeah, so it's and I made some slides which get slightly sparse near the end, but I figured we'll just switch to discussion, so it won't really matter.
Yeah.
Can I share my sleeve?
Absolutely.
Share my screen.
I think, is it letting you? Or?
No, it is not letting me. Is it I can raise my hand?
Okay, I will.
Oh wait, I can. Yes, sorry.
Oh, okay.
Sorry. Did it? Let's try that. Share. Does that work?
Excellent. The problem with Uranus. Oh, I said it the wrong way. Excellent.
So,
thank you.
When James invited me to come and speak here, he was like, look, you do exoplanets. Why don't you tell us about exo-Uranuses? And I'm like, that's really difficult. We basically only know of a handful that might even be remotely like an ice giant. And so we were sort of thinking about how to link this in. And then I realized the fact it is in fact really difficult to see ice giant like exoplanets was quite interesting. So I thought I'd talk about why we tend not to say exo-Uranus. So really the problem is, what's the problem with more Uranus? And is it more Uranuses or more Urani? I was wondering that too.
It's a problematic name. Yeah, sorry to interrupt.
Yes, it's exactly. It is indeed a problematic name. So yeah, first of all, like, what even is an exoplanet? I just thought I'd remind you that we're about to go outside the solar system. So when we say exoplanet or extrasolar planet, extra here just means outside, and solar means the sun. So extrasolar planet means any planet that does not orbit the sun. And in the early 1990s, we didn't really know any of these at all. But since then, we have discovered over 4,500. And I actually put exactly how many we discovered in my presenter notes, but Zoom is not letting me see them, which is rather sad. It also means I don't know which slide is coming up. So this is going to be a surprise for me and you. Right, so if we've discovered so many exoplanets, it might be quite reasonable to say, well, can you tell us about ice giants around other stars? So, can we have some more Uranuses? And, the outrage is very similar to Oliver Twist. More, you want more? It's really very difficult for 3 reasons. The first problem is that Uranuses don't scream loud enough, and I'll talk about that in some depth. So it's actually really hard to find their whisper around other stars. Second reason is Uranus is frankly in the wrong place. And the third reason is it's possible that exo-Uranuses are even in a wronger place than our Uranus. So the first problem actually comes from my own research. I'm going to give you an example of something I was struggling with recently. So when we discover exoplanets, there are multiple different techniques, but there are 2 really big ones that have discovered over 95% of the planets that we know around other stars. The first of these is known as the radial velocity technique, and it accounts for roughly 20% of the planets we found. So the idea here is that we generally think of a planet orbiting a star, which of course is perfectly correct. But we normally picture it as the planet moving and the star being stationary. But in reality, while the star has a much stronger gravity than the planet also has gravity that pulls on the star. So the star itself also makes a very small orbit that's really a lot more like a wobble than what I've drawn here. So in reality, both the star and the planet orbit around their center of mass. Now, this is typically really, really close to the star's center of mass, because the center of mass is really the balance point where the star's gravitational pull and the planet's gravitational pull cancel out. So if you want a seesaw, imagine where that pivot point is. But because the star is so much heavier than the planet, that pivot point is super close to the star's center. So the planet makes this huge sweeping orbit and the star gives a little bit of a wobble, but it is a detectable wobble. And if the planet is more massive, that wobble on the star is larger because the pivot point moves further towards the planet. So what you end up with is a value of the planet's mass, but more accurately, it is actually the planet's minimum mass. Now, why minimum? It is because we can't see all the wobble. If you are looking at an edge-on orbit, so from Earth, we're looking exactly edge-on to that orbit, then actually it's no problem. All that star's motion is directly towards the Earth, and we see the whole shebang. So in that case, the measured mass and the true mass are identical, no problem. But if the orbit is tilted, and we do not know in most circumstances if that orbit is tilted, then actually only part of that star's motion is towards the Earth and the rest is undetectable for us. So therefore, because we only see a little bit of the wobble, we underestimate how hard the planet is pulling on that star. So in that case, our measured mass is less than the true mass. So when we just have a radial velocity measurement, we only know a lower estimate for the mass. So we know it's got to be at least enough to account for the wobble we see, but is that the whole wobble? We don't know. So that is the first technique. The second technique, which accounts for a whopping 75% of the planets we know, is the transit technique. And most of the planet hunting you will have heard of is from the transit technique. It's a technique used by the Kepler Space Telescope and TESS follow-up. So in this case, the planet is crossing the star's surface from our view on Earth. And this actually causes a small dip in the starlight that I have greatly exaggerated in this plot. So if we see the planet passing in front of the star, we see a very small drop in the starlight as the planet's bulk obscures that star's brightness. So in this case, we don't get a mass measurement, we get a radius measurement, because the bigger the planet is, the more light it obscures and the bigger the dip we see. So where does that leave us? Well, if you found planets through the transit technique, then you're going to get a radius. And if you found planets through the radial velocity technique, you're going to get a minimum mass. And the problem is that we could really do with both, because if you have mass and radius, you can get an average density, which is your first characterization of what the planet might actually be like. Like, is it gaseous? Like Saturn and Jupiter, or is it like sort of gaseous, but maybe kind of icy like Neptune and Uranus? Is it rocky like the Earth or Mars? Is it, maybe icy like Europa, or is it some hybrid world that we don't really have in our solar system? And the first clue to that would be a density measurement, but hey, it's really hard to get mass and radius. So what can we do? Oh yes, we're coming to what can we do shortly. So what you end up with is if you go and look at all the exoplanets we discovered, and you can easily do this. We have lots of databases online, and my favorite is the NASA Exoplanet Archive, and the URL is there. You'll actually see tons of different planet properties, which makes it look like we know loads about these exoplanets. But if you go and look at any one in detail, what you find is actually a lot of this table is empty. And that is typically because we've discovered it through one technique and it's only revealed part of the properties. So part of this solution, of course, is bigger and better telescopes. Yay. And that will definitely help as we improve our instrumentation, but it won't actually solve everything. So one of the problems we have here is that, for example, if you want a radius and you want a transit observation for that, but the orbit is tilted so that we don't even see a transit, then you're never going to get a transit measurement, no matter how big a telescope you build. If the orbit is tilted, so we do not see that planet crossing in front of the star, then you just never see a transit. And unfortunately for an Earth analog, by which I mean an Earth-sized planet on our orbit around the sun, the chances of spotting a transit is only less than 0.5%. It gets more and more difficult the further the way you move from the star, which gives you your first hint at the problems we have with Uranus and Neptune around other stars. And even for the radial velocity technique, it can also be very difficult. For example, if the star is noisy, for instance, it has a lot of stellar flares, then it's very hard to pick out the signature of the planet from all the other kind of activity that's going on the star surface. So bigger telescopes are only half the answer, and this is where my work comes in. So one of the projects I did recently was to look at ways of making good guesses of the properties we're missing. And to do this, I used a neural network. So what we did with a neural network is effectively we do a very complex imputation. So imagine these are all the planets we've discovered. And we have various properties that we know about them: radius, mass, number of planets in the system, how much starlight they receive, what the mass of that star is. And we say to the neural network, find patterns, find links. So for example, if you have a bigger mass, you probably have a bigger radius. And for reasons I'll actually touch on later, if you're further from the star, there's a fair chance you'll have a bigger radius, with some exceptions. And you say to the neural network, yes, I've given you a whole bunch of properties, but I think you're up to the challenge of finding the connection between each of these properties. And then you can say, okay, I've got a planet, but I've only been able to measure, say, the radius, say it's a transit. and I don't have any kind of mass measurement. But you say to the network, I'm going to give you the radius, I'm going to give you how much starlight it receives, I'm going to give you the orbital period and tell you how many planets are in the system. And the network will say, well, based on all the links I found between the current number of planets that we know, this is my guess for what the mass is. So it's really a clever guesstimate, an educated guess of those missing properties, and it could help us fill in the measurements that we just can't make. So how did we do? Well, here is the imputed mass from the network on the y-axis and the true observed mass. So what we did is we gave the network planets that we secretly do know the mass to, but we pretended we didn't. And we said, go and find that mass. And the closer they are to this dotted line, the better we did. And this is what they look like. So not fabulous, but, you know, a strong guess with some very noted exceptions. So for example, what on earth is going on here? I mean, that is just like the network has got it utterly, utterly wrong. So why? So what I did is I went through some of these bad cases and asked, why does the network so completely fail in these options? So what we're looking for, what would be a good result is if we said to the network, what's the mass? And it comes up with a probability distribution. So this is what it thinks the mass should be. This is its guess. And you can see there's a very strong peak to this graph. So that means the network is pretty certain what it thinks the mass should be. What we don't want is a graph that looks like this. This suggests the network is equally certain about a huge range in mass. It really doesn't have a preference. It frankly does not have a clue. And you guessed it, this is exactly what the network produced for this particular exoplanet. It was an almost flat spectrum. It really said, you know, your guess is as good as mine. I've got no idea what the mass of this planet is. So when we looked in a bit more detail at this, what we discovered was the planet's mass was 21 times the mass of Jupiter. Its radius was about Jupiter, and its period was 20 years. Now, this raises two flags. For a start, anything that massive and dense probably isn't really a planet. It's probably what we call a brown dwarf, which is an almost star. So really, maybe that was a bit unfair to give the network in the first place when you have started to have an internal structure that's becoming a lot more star-like than planet-like. But the other point was, a period of 20 years, there's really very little data here. If you look at all our exoplanets, they favor planets that are closer to their star. They're much, much easier to find by both the transit technique and the radial velocity technique. So that means there's a strong bias to finding planets that are close to their star and not at a period of 20 years. And in fact, this star/planet was not found by either the transit technique or the radial velocity technique. It was discovered by a technique known as gravitational microlensing. And we don't have many planets found this way, but the few that we have on long orbits are often found with this method. So for example, this is the actual data I gave the network, and you can see that overwhelmingly, most of the orbits are incredibly short. And the first red line is the line of 20 years where this exoplanet was discovered. And the second red line is actually where Uranus's orbit would be. So basically, we've got no data out there. So the network was like, you're asking me to impute from a whole load of planets that have orbits of, you know, a matter of days. And you want me to guess about the properties of a planet with an orbit of 20 years? Yeah, no, not happening. So that really told me how little we know about outer planetary systems. We just don't have that data yet. Oh, sorry, let's get rid of that. So I had a look actually at the Exoplanet Archive, and I said, give me all the planets you've got with an orbit longer than about 30,000 days, which is borderline what Uranus has. It's about 82 years, I think, out there. And as you can see, that list is not long. So out of the 4,500 planets we've discovered, we only have about a dozen. And the other notable thing is how they've been discovered. If you squint at that list, you'll see there's no transits whatsoever. So that's 75% of the planets we discovered, but notably, none are at these kind of orbits. There's 2 with radial velocity, and the rest have actually been discovered through direct imaging. Now, direct imaging is awesome. It's when you actually see the planet yourself, as opposed to looking at its impact on a star. So this is one of the systems in that list where there's actually this amazing movie where we start to see the planets move around the star. But this technique is super difficult because the star normally drowns out any reflected light or light the planet is emitting itself. So most of the planets we can discover through this technique tend to be very far from the star. Okay, that's good. But they also tend to be young, hot Jupiters. So planets like Jupiter that are very young are still hot from their early stages of formation. So they're easier to spot through direct imaging. To spot a mature system like our solar system and to spot ice giants such as Uranus and Neptune is still probably beyond the limits of our current technology, though it is getting there. So to find an exo-Uranus, or at least to find many exo-Uranuses, we're really going to have to wait a bit for the technology to reach the stage where we can really start to see these outer parts of these planetary systems. So currently we might get lucky. We might spot one, maybe not through imaging yet, but we might spot it through gravitational microlensing. But it's super difficult. They're really hard events to detect. And at the moment, we haven't got many examples. So that's the answer to the first one. So my second reason of why it's actually hard to find a Uranus clone is actually Uranus is probably in the wrong place. So what do you mean by that? Well, this is a diagram I drew, obviously not an actual image, but it represents the first stages of planet formation. So this occurs when stars are really young. They're surrounded by these dusty disks of gas. And we've actually have seen these through instruments like ALMA. And in these dusty disks of gas, we have microscopic grains that collide and stick and eventually build up to form a planet. Now, if you are forming close to your star, it will not surprise any of you to know you are going to be rather hot. And what that means is that the grains out of which you're forming tend to be mainly silicates. However, as you move away from the star, you end up in a much colder region of the disk where water starts to freeze into ice, and that gives you a boost in building material. So larger planets can form past the ice line, and that explains planets like Jupiter, Saturn, and potentially Uranus and Neptune. However, hang on, let me just check where I'm going with this. Oh, yes. So, however, where are my notes for this? What is my however? It seems fine. What's the problem? Oh, yes. So this process of building up a planet where you collide and stick and build steadily larger and larger objects is quicker if you are forming close to the star because your orbit's shorter. So you basically have more time, more opportunities to collide with material along your orbit and build up a bigger body. So even though past the ice line, you have a bit of a boost in material, by the time you get out to distances where Uranus and Neptune are, there's started to be less material again because the disk is petering out. And moreover, the orbit is so incredibly long that it takes a massive amount of time to actually start to build up large planets. So much time that we don't really think it's possible for Uranus and Neptune to have formed in their current positions. It's more likely that Neptune formed at a position that's about 15 AU, where 1 AU is the average distance between the Earth and the Sun. Whereas currently, I believe, because I can't see my notes, I think it's about 30 AU. So about half its current distance. But if that's true, why do they sit so far out now if they had to have formed much closer? And actually for that, exoplanets can help us again. So in 1995, the first exoplanet around a star like our sun was discovered. And this was actually the the result of this was the Nobel Prize in Physics in 2019. This actually wasn't the first exoplanet to be discovered, but it was the first one that was around a star vaguely similar to our own sun. But it was weird. So this is 51 Pegasi b. And 51 Pegasi b is roughly Jupiter mass. Okay, you might think we've got a Jupiter, they've got a Jupiter. Where's your problem? Well, the orbit of 51 Pegasi b is just 4 days. It's only 5% of the Earth-Sun distance. So for comparison, Mercury is at 88 days. It's 40% of the Earth-Sun distance. So this is really, really close, much, much closer than Mercury is. But it's a huge planet like Jupiter. And this makes no sense because, as I briefly mentioned, you need to get past the ice line to get this boost in building materials where you can start to put together a seriously large planet. So how on earth do you end up in a system where you've got these huge gas giants closer than Mercury where actually there should be relatively little building material for planets. And the answer to this turns out to be something called migration. Oops, let me come back. So as we are colliding and sticking to get larger and larger planets, we reach the size of Mars. Now, Mars is not an impressive planet. It's only got about 10% of the mass of Earth. It's pretty squiffy. But at that stage, it has enough mass to start pulling very hard on the surrounding gas and dust. And the results of this are a little bit like being in a race. So let's imagine that you are Mario, and there's Princess Peach, and then there's, I think, Yoshi on the inner track. And you are all moving around trying to win this race. But for some terrible reason, someone has tied you together with a rope. So a little later on, Yoshi's overtaken you. He's on a quicker track and he's moving at a faster velocity, whereas Princess Peach is lagging behind. And as a result, because you are tied together, you feel a tug from both Princess Peach and Yoshi. And this is actually very similar to what happens to a planet when it reaches the size of Mars. The inner gas is pulling one way and the outer gas is pulling the other. And these forces do not exactly balance. The net result is actually typically, though not always, but typically an inward pull towards the star. So what this means is that you could start forming your planet beyond the ice line, where there's plenty of building material and you can build up a decent size. And then you migrate inwards. So you take advantage of all that outer building material, but then you slowly shift inwards, or sometimes even rapidly shift inwards. And you end up on a much closer orbit and become what we call a hot Jupiter, because it's Jupiter-sized, but hot. Astronomers are really imaginative with names. So interestingly, this explains a few things about our solar system. One of the things it explains is why Mars is pathetic. So as I mentioned, Mars is on the small side, but actually we would expect it to be larger, because you'll notice that as you go outwards from Mercury, Venus, and Earth, you get steadily larger planets. And we actually expect Mars to be slightly larger than Earth, but it isn't. And the reason for that is probably Jupiter. And Jupiter and Saturn are probably also the reason why Uranus and Neptune sit so far out. So here's what we're going to do. Here's our young Jupiter, and it is sitting in a sea of dust and gas and small rocks we're going to call planetesimals. And it's going through what I call the Pac-Man phase. That is, it's colliding with material on its orbit to get larger and larger and larger. But as it reaches the size of Mars and grows beyond that, it's going to start migrating inwards. So it moves in towards the sun, munching up material as it goes and gets larger and larger. But as it's doing that, before it becomes a hot Jupiter, Saturn appears in the scene. And Saturn's also a really hefty planet. And it starts doing exactly the same. It's munching up material and it migrates inwards. But now Jupiter's going to start to feel Saturn's pull, in addition to the pull of the surrounding gas and dust. And if you add up all these forces, you turn around. And you can actually pull back towards the outer solar system again. And this theory is known as the grand tack, for that sailing maneuver where you turn around. And in that case, the planets move back outwards again. And this has a few consequences that explain our solar system quite nicely. The first is because Jupiter has moved into the inner solar system and back out, it's eaten up a lot of the building material that would have gone to form Mars. So Mercury, Venus, and the Earth are largely unaffected because they form a little bit later. But when Mars tries to form, it's not got much building material left because Jupiter ate it all. The second consequence is as they moved back outwards again, their orbits are thought to have become quite elliptical. And as that happens, as they bent from a circle onto an ellipse, they started to disturb the orbits of Uranus and Neptune. And during that whole process, which is called the Nice model, Uranus and Neptune get thrown outwards and they end up on a much more distant orbit to what they formed in. So it might all be due to migration. So that's my second thing about why it might be hard to find a Uranus, because actually the reason ours are so far out might be the consequence of our whole solar system architecture. So if we find another exoplanet system, but it doesn't have a Jupiter and Saturn with exactly the right masses that are able to do this grand tack formation, then you won't get a Uranus and Neptune so far away from the star. They'll be much closer. So we don't know this for sure. What we need to see is other planetary systems and see if they have similar planets to ours, and if therefore they have a similar configuration or not. So my third reason of why we might not find an exo-Uranus is actually we might have found exo-Uranuses, but they might be in an even different place. So in our own solar system, we have broadly two classes of planets. And excuse me, I am going to roll Uranus and Neptune and Jupiter and Saturn together and just call them gas planets. But we have the gas giants, those 4 planets, and we have the rocky worlds, but we don't have anything in between. But the same is not true of exoplanets. We found actually the most popular kind of exoplanet we've so far discovered has sizes in between that of Uranus and that of the Earth. So what are they? Are we looking at a massive supersized Earth that's rocky? Or are we looking at a teeny tiny Neptune or Uranus that has maybe migrated inwards because perhaps there wasn't a Jupiter and Saturn to block its path? And if they migrate inwards, then they would obviously receive more sunlight or starlight as they get closer to the star. And that might have caused part of their atmosphere to evaporate away. And the result of this might be some kind of hybrid planet where you have a core very similar to what we'd find on Uranus or Neptune, but less atmosphere because it's been stripped. Or alternatively, there could be something entirely different. And indeed, for a few of these, we have measured the density, and we found it to be too dense for a gas world, but too light for a rocky world. So they might be something like water worlds, where we have like 50% water, whereas the Earth, even though we think of it as very watery, by mass, it's only like less than 0.01%. So these might be really alien. So they are my 3 reasons for why we might not have an exo-Uranus. They don't scream loudly enough because their orbits are so long and so distant, it's very hard to see them. They are probably in the wrong place. Our Uranus perhaps isn't even where it should have formed. And the only reason it's there is because of Jupiter and Saturn. So you need a really good solar system analog, if that's true, to get a Uranus and Neptune. And thirdly, actually, we might be forming them all over the place, but they might typically move in to become this strange sort of mini Neptune super Earth class of planets. Thank you. That's my talk. James, come back.
Hello. Thank you very much for your talk. And thank you for making special slides and making it very Uranus focused. I think it's very good to have an exoplanet person and exoplanet perspective on the stuff we do here. And for people not in the know, I guess exoplanet scientists and planetary scientists, the overlap in many departments across the world is it's unusual. It's like you could come from a looking at stars background and go into exoplanets, or maybe you can go from looking at planets and go into exoplanets. But usually in departments, they tend to be separate for some reason. But I think good efforts have been made now as we're getting more zoomed in views of exoplanets.
It is actually, I mean, you're absolutely right, James, that it's actually become quite a big issue, because until fairly recently, we were focused on detecting exoplanets, just finding them. I mean, it's an incredibly new field. So in the early 1990s, which at least to me seems very recent, we only knew of the 8 planets, and if you really like Pluto, 9 planets in our solar system, and we had to base all our theories on there. But now we know of 4,500, and we're moving to a new era of exoplanet discovery where we're going from detection to characterization. Like, what are these worlds really like? What are their surfaces like? Are they mini Neptunes or are they super Earths? Could any of them support life? Do any of them support life? And this means suddenly you need to unite the astrophysics with the planetary science, because until then, you've really been looking for shadows that cross that planetary surface. And for that, astrophysicists are very well equipped. But to actually characterize the planet, you've suddenly got to understand planet geology and to understand what that top atmosphere might be telling us about the planet interior, its chemistry, its physics, its geophysics, its biology. And as an astrophysicist, I can tell you I have probably never sat courses in that. And so suddenly we need to go and start talking to our planetary scientists and say, hey, how do planets work? And on their side, they've got to say, excuse me, what data do you have? I mean, you've been showing these beautiful pictures of Uranus, and, you know, for an exoplanet perspective, I can give you, when we're really lucky, one pixel. You'd be good with that. And we have to be able to deduce from that how the planet's working. So this slightly awkward meeting of the minds has just sort of really started to take place, and it's really difficult.
This in itself is a collaboration of a kind, because I don't think you've met Tom Stallard, Emma Thomas here. Maybe when the pandemic's over, they can come over to JAXA and give nice talks and so on, and maybe we can go back to the UK, top up on some essentials.
Crazy idea that, James.
If there's any
back to the UK. What are you talking about? Crossing borders. What is this? I can't even remember what it's like to cross our international border anymore.
It's been a couple of years now over here. Yeah.
But so you are actually, sorry, you are broadcasting almost from my home. My parents actually live in Leicester.
Perfect. There we go. So regarding the number of planets, we've watched it go from 0 in 1992, I guess, well, from 1 in 1992, and then to 4,500. I think I've been quoting 4,500 for quite some time now. That was a big surge recently from the Kepler mission. But I was wondering how you expected kind of the next, like, how do you expect the curve of new discoveries of exoplanets to go up in the next 10 years or something like that?
So actually the peak recently has probably been with TESS. So Kepler and TESS had slightly different goals. They are both transit. They didn't look for this dip in starlight, but the stars they're looking at are different. So Kepler was trying to do a survey. It just picked one patch of the sky and stared at it and was like, give me everything that's there. So you ended up with a relatively wide range of planets and orbits, whereas TESS is specifically looking at the whole sky, but picking out stars that are bright enough that you can do follow-up, potentially preparing for this characterization. So if most of the stars in the Kepler field are too far away for us really to be able to get more information, what we need is local bright stars that are good enough that we're starting to get some starlight filtering through the atmosphere and being able to resolve that. And that's going to be our first clue as to really what's going on with the planet itself. So that recent pick has been TESS. Now, what's going to happen from there onwards? We are moving more to characterization, so taking planets we already know about and trying to find out more of them. But that said, we still have a lot of upcoming satellites that will be looking for detection still. So obviously TESS is still going on. We've got European Space Agency's Plato mission that will be another survey one to try and find out what is out there. But then some of the others we've got going up are going to be focusing on taking planets that have been discovered, but then trying to find out more of them. So I'm going to pronounce this wrongly, Cheops. It's the European Space Agency's mission where they're taking planets which have radial velocity measurements. They've already been discovered and trying very hard to find a transit for them and measuring the transit very, very precisely to get some really good density data on that. And then, of course, JWST, which is really soon to launch. I'm actually slightly terrified. I feel that I keep waiting for the next delay and there doesn't seem to be one. I don't quite know how to handle this anymore. But one of its big tasks as well is going to be to try and look at exoplanet atmospheres. Now, obviously, JWST is a general observatory. There's other people who want to use it, like, in fact, you guys mentioned you might want to look at some solar system. I don't really understand. But for some reason, it isn't 100% exoplanets. Who knows why? But one that will be is European Space Agency's Ariel mission, which will launch, I think, at the end of the 2020s. And that's going to try and do a survey of nothing really like Uranus in terms of orbit, but probably sort of gaseous planets that are close to the star. And it's going to try and find out, what's in their atmospheres. And that will be really interesting because if they formed much further out, their atmospheric composition would be expected to be quite different compared to if they formed where they're now orbiting. So that will be able to tell us something about how common migration is, which is something I'm personally super curious about. Like, it seems to be a major sculpture of planetary systems, but does that mean that all the planets we found with Earth-like orbits are secretly Uranuses that have shifted in and lost half their atmosphere? That would be quite a different sort of world. So I think it's important that we find that out.
As you pointed out in your book, The Planet Patsy. Available at all good
I didn't
bookstores.
pay him, guys, I promise.
Yeah. Anyway, you mentioned you have a chapter saying that the chapter title is "We Are Not Normal," and there's many interpretations of that, I think. But yeah, that highlights. As you point out in the talk as well, it's, at least of the data we have, the most common thing we have seen is planets in between Earth and Uranus, and there's a funny kind of divides there where you say super Earth, or you say mini Neptune, or mostly it's mini Neptune, right? But no one says mini Uranus for undisclosed
I don't know
reasons.
why.
Yeah,
I'm assuming because
we all
it's got
know
a
why.
side.
You know why. You know why.
Well,
It's got a bit
there's
of
that
ring to
reason.
it.
And I would also say the fact it's rotating on its side is just, it's
True.
trying to be different. We can't use it
Yeah.
for anything typical.
That's right. Yeah. So I mean, it's fascinating to think of. Is it possible for life to exist on these super rocky Earths? I mean, when I'm saying that, I mean definitely very ridiculously large versions of Earth that are still rocky. I'm picturing the people there as being very good at lifting things because of the high gravity.
Absolutely. Well, I think the higher gravity is one of the interesting questions. There's a lot of things, because we have at the moment only really got size and we haven't got characterization. It's really anyone's guess what the surfaces of these planets are like. But if we start to say, okay, let's assume we've measured the density, which is not impossible, we might have done it, and let's assume the density is consistent with a rocky-like planet. Could you then have life? And the gravity itself is quite interesting. Some people have done some investigations of what that might do. For example, if you have a higher gravity, you might sort of flatten the topology. So you might have less mountains. Now, one of the consequences of that is it's quite easy to accidentally get a water world. So just because you have a rocky planet, even if you have it at an Earth-like orbit with similar temperatures, there's no guarantee it's actually got water. Because indeed, exactly how we got our water turns out to be a bit of an open question. But let's assume that it has, and it's got it through a similar mechanism. If you flatten all the mountains, you end up quite easily being able to spread the ocean and cover all the land. And that has an interesting consequence for the thought of life. So, for example, the Earth, we often talk about the Earth being in the so-called habitable zone. And how we define the habitable zone normally is where we think is the range of orbits we think the Earth could remain a fairly temperate temperature on the surface and therefore support liquid water. So the way we can do that when the sunlight changes between these orbits is by something called our carbon silicate cycle. So this is the geological cycle that can adjust the amount of carbon dioxide in our air. And if we put more carbon dioxide in the air, we get warmer. If you extract more, you get cooler. And so you end up with a range of orbits where you're going to be A-OK for those oceans. But if you cover all the land with water, the carbon silicate cycle breaks down because a key part is the reaction of rainwater with rock. Now, if you cover it just a shallow amount, you might get away with it. You might all be fine. It's not going to be quite as good because the water sort of buffers that temperature, so it responds more slowly. Like seawater changes temperature more slowly than the air, so you can swim late in the autumn. But in the August, the atmosphere temperature is the hottest, but the sea temperature could be cooler. Well, that kind of delay would happen as well if you had a shallow water world. So your thermostat would be a bit cranky, basically. It would sort of be out of sync slightly with the atmosphere temperature, but it's possible. If you make the ocean too deep, then you start to have some problems. So for example, Ganymede, which is one of the Jupiter moons, is thought to have a subsurface ocean, but it's also thought to have built up deep sea ices. And in that case, if you end up with deep sea ices, then you seal off the ground completely from the water. And then you can't react to any change in temperature because the ground just doesn't know about it. It's covered with a thick layer of ice. And if you change the temperature on the outside, well, it doesn't know. So at that point, your carbon silicate cycle fails. Now, if it fails, it means you have to be in exactly the right orbit for liquid water. Because if you're too hot and too cold, you can't adjust. And the problem with that is the sun's luminosity hasn't been constant over the planet's lifetime. So it's actually impossible to stay in the so-called habitable zone for a long period in that situation. So if you had, a super Earth with a very flat topology and you ended up with a water world, your best scenario is that it's sort of okay, but not quite as good. And your worst scenario is the carbon silicate cycle breaks down and you might not be able to control your temperature. But of course, there's more unknowns here. For example, people have produced theories that suggest, okay, the carbon silicate cycle is trash, we have to forget about it. But you could have a different cycle. And there's been papers by Kite and Ramirez, which have looked at ways in which a similar kind of carbon dioxide controlling cycle could come from a very deep ocean. So it's not necessarily curtains, but it starts to look a bit tricky if you have a very flat topology, maybe.
Fascinating answer. Yeah, it makes me think of Waterworld, the movie, and everything like that. But obviously a different situation. But well, I was wondering if Tom had anything to add because Tom has got a heavy geology background too. So
yeah, well, I stare upon that gap between astrophysics and planetary science from the other end and see as many mysteries across the gap. So it is quite difficult, isn't it? I'm fascinated by these super Earth, sub Neptune worlds and how similar or different they might be from either Earth or somewhere like Neptune. And it's so hard to tell at the moment. I mean, as you say, there's no real measurements that we have that really confine it at all. It is somewhat alluring that they have basically almost identical densities to what we see at Uranus and Neptune. So there is a part of me as the planetary scientist that sort of hopes that means that they are very reminiscent worlds. And you also have to caution this idea that they ice giants are made of ice, and so maybe these worlds are rock with hydrogen envelopes, and so they can't be at all alike, because we really still don't understand Uranus and Neptune either. And there's some wonderful new papers coming out suggesting that maybe ice giants is a terrible name for these planets, and maybe Uranus is just a rock world with a hydrogen envelope. So I mean, as always, this is the theme of the weekend. We should have a space mission back to Uranus and Neptune to better constrain and understand them and see whether they fall within the same bracketing or not.
It's indeed exoplanet mission. A spacecraft to an
absolutely.
It's a career building one.
That would be even more distant in terms of, I'm already looking at missions that will arrive when I retire. So
yeah. But maybe that's the way to go, James. We propose an exoplanet mission and everyone's like, well, how long will that take? And you say, well, if you were to point Voyager 1, which is our fastest moving spacecraft, at Proxima Centauri b, which is our nearest exoplanet, it would take just 75,000 years. And everyone will be like, oh my goodness, that's really quite a long time. And you'll be like, oh, okay, if you insist, we'll go to Uranus instead. And it will seem a lot more reasonable after the 75,000 year suggestion. And maybe people will go for it.
We have an anonymous question. For radial velocity detection, would you have to wait for the 84 year of an exo Uranus at a similar distance to ours in order to detect it, or will a fraction of an orbit, say half an orbit, do?
So given they've got a couple of radial velocity detections and we've only been looking for exoplanets successfully for about 30 years, it must be true you can do it on a fraction of an orbit. I'm not an observer, so I've never really had to handle the data, but I don't see how that couldn't be true. I think the question is, how confident can you be on a fraction of an orbit that you actually have a planet? And that will depend on a lot of things. It will depend on how noisy the star is. That's a really big thing with radial velocity. If the star is very active, like it's got a lot of flares, or if it's an older star, they tend to get kind of cantankerous as they get older and their atmosphere has a lot of pulsations, and they can all look like a fake planet. So we've had a lot of cases where we've discovered exoplanets and we've got excited about them. And then someone's pointed out something suspicious, like how odd its period seems to be an exact multiple of the star's, rotation. And that's almost, it's really a smoking gun for the fact you've got a false positive and there's something like a star spot or something that's causing a similar signature to be periodically appear, but it's actually got nothing to do at all with a planet. And an interesting story, of course, is you can go the other direction. And our first exoplanet was discovered in the early 1990s, but it should have been discovered in 1988. So in 1988, there was actually a radial velocity wobble around a star called Gamma Zephyr. And the authors even published this, and they said, oh, there's a wobble here. It could be due to a hidden third body. This could be a planet. But they hesitated, and they hesitated for a couple of reasons. For a start, the star was part of a binary system. And very notably, our sun is not in a binary system. So there was some doubt about whether you could even have a planet in a binary system. And secondly, they thought, actually incorrectly, but they did believe at the time that Gamma Zephyr was an old star, which had a lot of pulsations in its atmosphere, which would produce these kind of false signatures. So they published a paper saying, yes, we detect this sort of radial velocity signature, but we don't think it's a planet. And when they published that, they missed discovering the first exoplanet, because it actually was one, but it wasn't confirmed, I think, until 2000 and maybe 2. So
Right.
it missed the boat for that. Yeah.
They
So we
missed
can go the other
Nobel-
way as well. Yes, exactly.
Yeah.
They missed the Nobel Prize.
Nobel Prize for that. Yeah, I mean, I think that's a good point. Like sometimes in our own results, we publish things that are pretty good, close to like 98% correct maybe, and or maybe 90% or 80% correct, and you just got to get it out there, and so people can discuss it in the journals and stuff, especially with observations too. But maybe one more question, and then we can go to we'll have a look at Uranus, and maybe you can take a look at Uranus and see. Maybe get some of your thoughts, Elizabeth, on what it's like to see something that's more than a pixel in size in the screen. But if Jupiter migrated in and scooped up poor Mars silicate grains, does that mean that Jupiter should have a silicate iron core that now the Juno gravitational measurement instrument calls for Jupiter as a diffuse core, a sharp difference from the ball of rock and ice that it was predicted to possess?
So in order to start migrating, Jupiter already has to be a fairly solid core. So no one knows exactly what Jupiter core is like. So bear in mind that you should not take my word as law, as this is final. We've decided this. My feeling on this subject is that Jupiter will still resemble most strongly the material reasonably close to its orbit, because it will have had to have built up a reasonable size before it starts that migration. And then in terms of diffuse, it sort of depends on the gravitational environment inside the planet. So that isn't as dependent on or at least it's not purely dependent on the material. So I don't think that is evidence enough that it definitely migrated inwards. If we could really get its composition, then maybe we would find clues there. But I think at the moment we don't have enough to really say. But it is true that if we were able to look at some of these planets that were much closer to the star and found they had a very icy composition, I think you could do it the other way around, and then you could argue, no, you guys have definitely moved in. And indeed, if we find that these sort of in-between planets have an in-between density, which we have seen for some of them, if we could prove that was water, that would strongly suggest they have formed out near the gas giants, where, as we know from, Enceladus and Europa and Ganymede and Callisto, there's a lot of water and ice there. So that would definitely suggest that they were migrating inwards.
Excellent. Thank you very much. Thank you for your talk and for taking the questions. And I hope that you'll hang out and we can draw you back, but obviously no pressure. And so I'll pass it over to the pro observer, Emma Thomas, and maybe we can see some Uranus with some moons around it and so on.
There we go. So hopefully that's now being seen. I'm going to unpin my camera just to make things a little bit easier to see.
Okay.
Okay, so I haven't had a good chat. I've had a quick text chat with our lovely observers at the moment, Nahid and Riyang, are currently taking on the torch of observing. We're coming along to 3 o'clock in the afternoon here in the UK. So that means you've probably been observing for, what, 6 hours now? We're getting along to 6 hours. Of observations at Uranus. Similar to before, we still have our 3 key lines that we're seeing at Uranus. So we have our Q1, Q3 and Q3-1. What I mean by that is essentially the H2 plus, that's the molecule that Steve Miller was talking about earlier, basically will light up at specific wavelengths, basically saying, hello, I'm here, I'm doing things. And that's where we can kind of get a lot of our information about Uranus. So as I said, I'm excited at the fact that we've actually got, we've got not only 2 lines, we've got 3 lines. That really helps when it comes to the data analysis side of things. In terms of what we're seeing at the moment, I think we're currently on what we call a B frame. What I mean by that is there's basically 2 positions on the slit we will pick for Uranus to be. The reason we do this, or the technique that it's called as nodding, is essentially to mitigate the effect of Earth's atmosphere. The way that we can do that is basically by having Uranus in a position and then Uranus not in the position and just Earth's atmosphere. You can actually mitigate the Earth atmosphere when Uranus is there by minusing when Uranus isn't there to get rid of that effect. At the moment, we're hopefully going to be shifting probably back to an A frame very soon. So we'll see it dart back and forth again. I believe we still have Miranda being very, very faint up at the very top. I think this is Miranda up here. We then have Ariel and Umbriel still following along in very similar positions as we saw them yesterday. So it's, again, great to confirm that we still have them about. I think just on the very edge here is the star that we've been having a lot of discussion with today, interacting with the slit and also being part of our investigation. We think possibly a double star. So that one's fascinating to see that we also have interstellar neighbors coming to say hi. Outside of that, we haven't seen too much variation with the spectra. So at the moment, we're still seeing kind of fairly consistent line, I would say, through. So again, I'm probably going to round off on the same way as last time, which is that I think we are looking at the boring part of Uranus. Again, I will always quote on boring part because yes, the aurora is really fascinating and it's great to know and there's so much information. But as we've seen at Jupiter and at Saturn, a lot of the fascinating phenomena that we've seen, such as the ring rain at Saturn, we've only been able to detect how those phenomena by observing lower down in the planet's latitude or closer to the equator, essentially. So same here at Uranus, if we're able to see quieter periods, that may give us an indication of actually what's going on at Uranus, and that maybe, as I've discussed with Tom before, we could perhaps even be able to see ring rain at Uranus, maybe with IRTF, maybe even with the James Webb Space Telescope. So these are fascinating times, but at the moment, whilst we do our observations, we think we're probably on a fairly quiet period with Uranus. So fingers crossed, later today we may see something, but if that's not the case, then that looks like tomorrow will be when we possibly see either aurora or perhaps more of the southern aurora, with a vague idea of where we possibly are, but again, we'll need to investigate the data a bit further on that one. Outside of that, I'm just trying to think of anything else. The clouds are fairly good. We are now at, I'm just trying to think time-wise, I would say 3:55 in the morning in Hawaii. I believe that's correct. Possibly 2:55. I may be slightly off by an hour. Actually, I think either way, it's early in the morning, if I can say that much, in Hawaii. So we now have at least another 2 1 hours of observations. Let's say myself right. Another 2 hours of observations at Uranus. We're going to hope that we can keep looking at the planet, but as Tom did mention earlier, we do have possible clouds close to the horizon. So that will mean that our guider will start struggling to see Uranus by the end of the day, but hopefully we will get as much data as we possibly can.
Excellent. Thank you very much. That's awesome. let's see. Heidi will be on in about an hour. I think I must have misdone the times here a little bit, gotten confused with Eastern time, but that's okay.
Nice.
Yeah, so yeah, Q&A. We can do some Q&A with whoever's on board, and we were going to do that in the last hour. We'll just switch it around. I shot Heidi an email in case she wants to join earlier. It's up to her, I'm sure. Over there, it's a little bit earlier. But yeah, let's see. So I have some general kind of questions, but there was a question earlier from, let's get people pinned up. But yeah, so it was about LIGO from Gwen. Let's see. Question, which was originally, I think, for Heidi Hamill, but this is exoplanets. So I'm sure Heidi could answer any question as well. But have there been any exciting discoveries on exoplanets by use of gravitational waves, such as using LIGO? I'll let you take that if you're available, Elizabeth.
Oh, hey, yes.
Hi.
No is the answer to that question. So at the moment, in theory, you're completely right. I mean, a gravitational wave is created by any accelerating object, and that will include a planet going around a star. But in practice, we've only, like I was saying, exoplanet field is new. Well, gravitational wave field, I mean, that is like really new. So at the moment, we're only sensitive enough to discover really strong wave producing objects, which largely means something very, very massive and very, very dense. So we can see things like orbiting black holes. We've seen some orbiting neutron stars, but the density of those objects compared to a planet is almost incomparable. So although in theory those objects will be emitting gravitational waves, we're not close yet to being able to detect them.
Right, that makes a lot of sense. Yeah, you need some pretty, I would say, space bending activities to make that happen. You probably don't want to find a planet that's doing that, but just add some spotlights.
I would question whether it was a planet. We have found some planets going around neutron stars, though. That's actually been the first exoplanets that were ever discovered. So people always remember 51 Peg because, I mean, they had a whole Nobel Prize, and it was, planets going around a sun-like star, which we could all kind of relate to. But the actual first discoveries were a couple of planets orbiting a neutron star. And this was completely bonkers. And it has a rather bizarre story attached to it. So we do not believe that planets could be around neutron stars, because a neutron star is a dead stellar remnant. And it's a dead stellar remnant from a star that's much bigger than our sun. So when such a star dies, it goes off as a supernova, which is like this huge explosion, and anything orbiting that should be, either incinerated or like thrown off and never seen again. So you don't expect a couple of planets. It turned out there were actually 3 neatly orbiting a neutron star. And it turns out the way we believe this happens is that neutron star once had a stellar twin. And so that's not uncommon. Many stars in the galaxy are in binary systems. And if that happens and one becomes a neutron star, then it can start to feed off its twin. And as it starts to feed off and drag material onto it, it forms a disk that looks suspiciously like the kind of disk around a young star. So this becomes a second generation of planets that are rather morbid, really, because they're formed from the shredded remains of what would have been the neutron star's stellar twin. So, right. But we can't detect those through gravitational waves, but I just thought I'd throw in that they were around neutron stars and quite disturbing.
Yeah, thank you. It reminds me of a movie Interstellar. There's a planet very close to the black hole. Not sure why it's there, but that movie has its own quirks, should we say. Yeah.
I actually really liked Interstellar. I know that's controversial, but I really liked it. I mean,
yeah.
For a start, it was something on exoplanets, which I liked. And the black hole science, I think, was done by Kip Thorne. So likely incredibly good. And then one of the things I liked is the ending was completely crazy. I mean, it's absolutely nuts. In order to get home, he had to fall into a black hole, somehow survive, get back out where not even light can get back out. And I felt that really told you exactly how far exoplanets are. I mean, it's going to be really difficult to visit them. To go and come back requires you to fall into a black hole and emerge from it. I felt that was a strong statement. I liked it.
Yeah, I always have an issue with going back in time things, but yeah, it's very rare we get such a spectacular movie actually. So it was very nice to see. One thing I wanted to discuss was that you do your talk was very awesome, and it had lots of cool animations and artwork, and as well as that you do your writing as well. So and also you're getting involved in virtual reality stuff, and basically all around any way of communicating, you'll find a way. So I just wanted to say that was very impressive stuff.
Well, I really enjoy experimenting. I mean, that's part of why you become a scientist, really, isn't it? Is you just want to try new stuff. If there's a new toy on the market, I want to give it a go, whether that's animation or virtual reality virtual reality. I find really exciting. I know we've all been driven online because of the pandemic, and we've all probably found meetings and classrooms less than satisfactory. But in some ways, we had to do it very fast and we weren't prepared. Whereas I feel that there's actually a lot of potential for online activities that could even be better than in person. Because in person, you could never hold a lecture about, say, IO on IO. But in virtual reality, you could totally, do your classroom on astronomy, standing looking at these objects. And that's something that can never be achieved in real life. And yet we can all become astronauts in virtual reality and get a much more immediate feel of what it's like. So I feel the medium has a lot of potential that hasn't really been demonstrated during the pandemic, and I'd like to see more of it. And as you found yourself from your animations that were discussed earlier in the program, they're an amazing way of reaching people. People don't absorb information in the same way. So I think we should put out a variety of information.
Yeah, I totally agree. Obviously, because we like to dabble in the same kind of things there. But it actually reminds me of what Tom was saying yesterday at the end of the discussion about how, there's a lot of kind of artistic stuff that we do. It's not just we're not just buried in numbers here. We actually have a lot of other stuff on offer, like creativity, for example, and we employ that in our jobs, doing the science, but also in the outreach of the science. If Steve was still on, I would ask him about the other. He is. Aha.
I'm still
Hi,
here.
Steve. Excellent. I'll put you on.
I had my lunch.
Oh, I hope you had an enjoyable lunch.
Did indeed, yeah.
Excellent. So Steve, one of the things that struck me is that you said that you led the University College London's the first degree in the world for science communication. So that's pretty huge. Yeah.
Yes. Completely serendipitous. I was in the physics and astronomy department. The undergraduate tutor said, "Hey, Steve, we hear you were a journalist. The Royal Society is getting into things around the public understanding of science, which they did in the mid-1980s. Could you put together a communicating science course for us?" So I did that. And that ran for a couple of years, just as a sort of an undergraduate module, which was optional and had quite a few takers. Some of you may know Kevin Fong. I know.
Yeah.
Kevin,
not personally.
Kevin was one of my students. I always remember him coming to me and saying, "I want to do your course, Professor Miller, but I understand that you've got to understand I'm a straight A student. So can you guarantee that I'll get an A on your course?" And I had to say, well, it depends how hard you work. But he got an A on my course. And then after a couple of years, we said, well, actually, it's about time UCL started offering a bit more in this area. And at the time, we had a very small department on history and philosophy of science, which was literally down to 3 staff members. So the then provost was thinking about closing it. And then he said, well, if we put science communication in there, we can have a bigger department. And we put science communication and science policy. And we ended up in the early 90s putting together a whole degree that included science communication, policy, history, philosophy. We used to call it all the wonderful things you wanted to know about science but were too afraid to ask degree. And we got a lot of takers for that. And that's developed into the Department of Science and Technology Studies at UCL. We've just, well, I'm retired now, but they have just started their own masters in science communication, but it's been part of the mix of the department's offering now since, as I say, I think it's 93 or 94 or something like that. And earlier it was just in the physics and astronomy department. So and sometimes it's been a struggle. You know, these things go in and out of fashion.
Right.
You get pushes from the research councils. Oh, you've got to communicate about this, you've got to communicate about that. So people do, and they say, well, what are our rewards in terms of our careers for doing this? Because we have to put food on the table, and we want to go up the professorial ladder and so on and so forth. And they're not so good, and they're still not so good about rewarding people who put a lot of time in. I see Tom shaking his head there. He knows what I'm talking about. And, they're still not fabulous about doing it. Even though, at least in the UK, since the mid-1980s, the Royal Society has said that scientists must not only learn to communicate with their fellow citizens, they must consider it their duty to do so. Well, if that's the case, a bit more support for doing it. So one of the things that I've been involved with recently is something called RAS 200. So last year, the Royal Astronomical Society was 200 years old. And a few years prior to that, the treasurer came to a council meeting and said, we want you to think big about some big projects. And by mistake, he said, what could you do with £1 million? And I think I was one of the few people to take him seriously. So he said, if you give us £1 million, we will set up this outreach and engagement program. We will have it as a bottom-up program. We will reach out to groups that don't normally get involved with our sciences. And we will partner with them. And so since 2015, we've been partnering with groups like the Prince's Trust, who deal with young people who have had the most incredibly tough starts to their lives, all kinds of things, being thrown out of home, being on drugs, being exploited one way or the other. We've partnered with groups that provide care holidays for people who are full-time carers and never get a break. Otherwise, we've partnered with the Space Centre in Leicester, producing a great planetarium show based on Holt's Planet Suite. We are partnering now with Girl Guiding. We're partnering with groups in various parts of the UK where science communication is less, I won't say less advanced, but needs more resourcing. So that's something that I think is really important, that when we're talking about science communication, public engagement, we need to think about audiences who are not necessarily immediately going to come into a something badged science, but working with groups who deal with what used to be called hard to reach audiences. I don't know what the correct term is now. That can be a way of going forward. So, you know, all of these things from small beginnings in the physics department at UCL through to working with huge groups of people. And this is something that the Royal Astronomical Society is still very, very keen to be doing.
Right. Yeah, I was going to ask actually, really everyone what your take is on, you know, so as we all do a lot of science communication as part of our jobs, and often in our own time as well, on top of that. And I was kind of curious how you all thought the trend was going. I always find that it's kind of like basically, you know, as time goes on, there should be more and more, you know, we should be more open and transparent about what we're doing and how we do it, and, you know, mistakes we make. This is a great example, actually. If I was going to put the Uranus back up, actually, so I can see it. Yeah, so
I'm so sorry.
Oh no, I was wondering actually, is there any other way of showing a scientific experiment like the way that we can do it with this? I was thinking, you know, there isn't really like a live in the laboratory or a live in the field in geology or something like that. This seems like a kind of a unique thing that we can do. So I think kind of we're very lucky to be able to have that opportunity. So I'm glad that this whole event is running, and long may many more events happen like it.
So when I was teaching courses, I used as an example for students Michael Faraday's Chemical History of a Candle, which was a series of lectures that he gave at the Royal Institution in 1853, and then again sometime in the 1860s. So you can do chemical experiments, and I worked with a colleague, Professor Frank James, who was jointly at the Royal Institution and UCL, and we used to create some of Faraday's lecture as a Christmas lecture, because the Royal Institution do these amazing Christmas lectures, which are incredibly experimental. But Faraday's Chemical History of a Candle is, in my view, that is the archetype of how really to engage audiences with all kinds of things. And he explains how, just by understanding how a candle works, that you get all the way through to Newton's laws of gravitation. So he explains that if you tip a candle, the wax comes out, and the cup that is made by the wick gets lopsided. And he goes, you know, because the same universal laws that hold stars and planets together are working on this simple example of the candle. So he's talking about gravity, and just brilliant, some of the stuff that he does. And there've been, I don't know how many fantastic exemplars using all kinds of sciences. And Tom will know about, you know, what you can do with geology. And we were talking about Mauna Kea with volcanology and so on and so forth, and how absolutely fascinating these can be. But you've also got to allow for people to come in and say, yes, but you guys just can't have it all your own way. We've got some things to say about this. We're funding you, you know, we want to know a bit more about this, that, and the other. And we've got some questions we want answering too.
Indeed. I was going to say to Elizabeth, actually, about the observations. Is this what you expected? So sorry to change the subject a little bit, just to focus on Uranus here. But I wondered if this is what you expected to see, or, you know, look at all these pixels compared to your exoplanets.
I know, right? It's like it's honestly quite a lot bigger than I expected. It tells you that I've done really zero observing, but I'm genuinely amazed by the fact that you can even see a hint of the rings and you can see the moons. It's just amazing.
It's good. Well, I hope the observations are going well over there. And actually, Tom, for those that don't know, Tom is my PhD supervisor from 2010 to 2014 in the University of Leicester. And Professor Steve Miller is Tom's former supervisor. So it's and Emma Thomas is Tom's current student. So we're all part of kind of a PhD family here. Looking at I was wondering if I remember, Tom, you've done live observing from Mauna Kea itself. That's my first exposure to this whole idea of live observing, like right from the actual, to schools, right? I think it was a school in Canada at the time.
I've done it to universities, and I've done it a couple of times to schools too. It's always difficult. It's a great opportunity to share when you're actually at the mountain, at the summit. And it's wonderful to be able to do that, but tricky, challenging. Emma's done an amazing job this week in sorting out and organizing all of this, and it's always hard to share these things. I think the honesty, trying to be intellectually honest, trying to show when things goes wrong, is really important. I was thinking on what Steve was saying. I think there's an awful lot of science communication in terms of results, but there's so little in terms of process. And I always think back on that. One of my favorite television shows from the past was Time Team. And I think Time Team is really the only television show that's ever attempted to capture the lightning bottle of science. It's obviously, as a non-archaeologist, I'm sure that they trick you in many ways to think that it's more real science than it really is. But, the idea that they would, over a period of 3 days, film an active investigation and follow that investigation, show the decision-making that was made during that process, it was always fascinating to me. And I wish there were more ways that we could reveal that. Obviously, that's not really true for us, because we're not like archaeologists who sit and dig things up and change our opinions about where we should dig as we continue to dig through the data here. We're just burning our way into the ionosphere of Uranus to some degree, and every so often something will happen and will dramatically change what we're doing, or we'll have to adapt to the fact that things have gone wrong. But for us, it's those months afterwards that we're digging through the data that process happens. I just wish there were more ways to investigate that. Another show that is really good for that in a different way is Mythbusters, which again sort of tries to capture the spirit of investigation, but there's very few, and it's really surprising. And I think it's just because we were talking about this yesterday, people see science as being this ivory tower of geniuses working on some magical thing, and it's all about the results. Look at these amazing black holes we've found, look at the amazing planets we've found around other stars, look at these wonderful images we have of Uranus. And it really it does a disservice to the creativity of the people who work on these things. And it's as much a dance as it is a painting. You want to see the results, but you do also, I want to share the idea that this is not magic. We're working creatively to try and put and frame what we're doing to get to the point where we can understand what we've seen. And I don't know if we do a very good job of that here, but no one else seems to be doing it. And so maybe astronomy is one of those opportunities to try and share those processes in action. And planetary astronomy, especially, just because things are changing all the time, you can see adaptations. We over a period of hours that you'll be able to see changes, which gives us such a lucky view. Most astronomy is looking at objects that are so distant that it's very hard to tell differences on short time scales. So the hope is that helps, I think, with communicating the gift that is science, I guess.
We've also done more recently a few things with planetary missions, which have been live too, with similar risks. I mean, it's a bit different. My astronomy friends once told me it was showcase planetary science with missions, because unlike a telescope where you have a sort of much longer period, a planetary mission will have events which happen over a very short period. So they said it's, you guys get it easy because you have your Hollywood moments. But since NASA, I think NASA were the first people to do that with the landing of, was it maybe Curiosity on Mars, where they did that live? And then ESA followed it with Rosetta and Philae. And then we followed it with Hayabusa 2, doing a mixture of things. We had some actual live events where we were talking on YouTube during the really big operations to actually collect a sample from the asteroid surface, but also doing things like for the more minor operations, we would do a continuous Twitter stream where we would update at sensible intervals. So at first kind of slowly and then near whatever we were doing much quicker, where the spacecraft might be descending low over the asteroid, and we would do live uplink of the images too. So I think there has been a push, like people are starting to say, okay, you've got this result, but we want to be there in the front seat. And there's been a bit more of a push to try and show them, there's no reason why you can't be here. Just please understand that we can't promise this will work.
Yeah, and I think some really excellent examples from the past. If only we were technologically in the place to do that for the Shoemaker-Levy 9 impact, because we weren't around at that time with technology that could allow that. But certainly I had a hint of that from the Deep Impact mission when I was actually able to go out. And again, inside of the rooms, you get an absolutely amazing feel for all of the different astronomers across the whole globe, as well as JPL streaming back information and being able to watch the impact in real time from UKERT and see it happen before JPL could see it happen was a phenomenal experience, and lost just to our memories because there were no ways of actually communicating that outwards at the time, really. So I think that again, sharing these things, and it's being open and opening yourself up to the potential for failure that is the real risk, right? You have to feel assured that no one's going to point and laugh at you because it's gone horribly wrong, and that's quite a dangerous thing to put yourself up to the risk of.
James, I'm afraid you're muted. I don't know if you've got a mute button on your
Oh,
mic.
yeah. I just gave the best speech. No. So we have a question that came in from Gwen about Uranus. It says, much of Uranus that has been spoken about has been investigative or exploratory. Are there any hypotheses that you'd like to disprove? Yeah, anything you want to prove wrong, or in general, do you prove things wrong? Yeah.
The magnetic field of Uranus is amazing, as you know, but what is fascinating to me is a comparison between Neptune and Uranus. And if you look at the magnetic field models, Neptune seems a lot more weird than Uranus. Uranus is weird and Neptune's crazy as anything. It's got 4 magnetic poles. But I think a lot of that comes out from the fact that we flew past Neptune very, very close to the surface of the planet, whereas we were at least 4 radii away from Uranus. And as anyone who's studied magnetic fields will know, they fade, the high orders fade away really quickly. So we don't really know how weird and wacky Uranus is at all. And what we do know from really close by observations of Jupiter is that Jupiter's pretty wacky too. It's got some really weird loops and magnetic strangeness in it. So it's a bit of a nuanced argument, but is Uranus as wacky as we think, or is it even crazier? Is the thing I want to know.
For that matter, do you have any, or does anybody have any anything they want to disprove in the other giant planets, Jupiter, Saturn, Neptune, in this field? Probably, I guess in general, do we really go around trying to disprove? I mean, that's not really, you don't really set out to try and disprove an individual person like it's some kind of I really want to, I don't like this person, I'm going to try it. No, we don't do that. But we do also like to I guess we do also like to decide between theories, really. I mean, whenever somebody is saying one thing, there's always an opposing theory or many other theories. And what we try and do with observations is to try and, reveal which one was correct. And probably 9 times out of 10, there isn't really, there's never a good answer. It's not like, oh, well done, you were right about this. It's usually some kind of mixture of all of them, plus 2 or 3 other phenomenon that was not expected at all. So yeah, in general, we're not really vindictive people. Well, most of us aren't. Yeah, I would say.
Well, I think the big question for pretty much all of the giant planets is still, why are the upper atmospheres so hot? And I'm, okay, I've seen explanations saying, well, you've got energy coming up from below in the form of gravity waves, maybe. I've seen explanations that say, well, you've got some heating just below the upper atmosphere as a result of electric currents, and maybe. We know there's a huge amount of heating for both Jupiter and Saturn going on in the upper atmosphere around the poles, but we don't seem to be able to get our models to transfer that energy from the poles towards the equator, where we still measure very hot temperatures. So I think, and this is something that we've known about since the Voyager days. We've known that these upper atmospheres are hot. What are we talking about? We're talking about 50 years, aren't we? And I don't...
48.
40 some years, yeah. And I still don't think we've got good explanations. And that is worrying, because it's a fairly, temperature is a fairly basic property. And if we don't understand the temperatures of planets in our own solar system, heaven help us when it comes to extrasolar planets, because there's all kinds of weird things going on there. And it just seems to me that we've got to try and sort out some of these questions quickly. Maybe James Webb.
Yeah, I think James Webb will really help, won't it?
Sufficiently accurate observations that we can distinguish between, say, gravity waves, between planet-wide electrical heating, between transfer of heating from the poles towards the equator. I don't know.
I think that, one thing that we can hope may help with this is actually these observations and the observations surrounding them, and especially James Webb, because everything that we know about heat transference and the balance of energies in gas giants are based around super bright heated aurora at the poles, and then flows of energy from the pole to the equator or from the equator to the pole. And here we have potentially lots of heating at the equator because the aurora tipped over so much. And the poles themselves don't have any aurora or anything interesting on them. So if we're able to go back and look at the temperatures of the poles of these, of both Jupiter, of both Uranus and Neptune, maybe that will resolve out, because we know these huge temperature changes we've talked about already at Uranus, where it's gone from 700 Kelvin down to more like 450 now. So if we could explain that about Uranus, or we could look at differences and see whether the pole, not the magnetic, but the rotational pole is colder or hotter, that might give us a really alternative view of what's going on. But you have to be really careful, because these are slower spinning worlds and they are much less able to draw energy out. So it might be that we talk about how all of the gas giants have superheated atmospheres at the equator. It might be that ice giants are pretty boring, and the aurora make the equators hot, and so it's not really a mystery at all. And it doesn't necessarily help us answer the much bigger mystery of a big giant whopping planet like Jupiter having superheated equators. That's the problem with these things. You think you found a solution, and it just proves to be another interesting aspect that adds to the complexity of the universe ultimately.
So
That's right.
I'm going to sign off now from this. Thanks very much for organising it, James and Emma and Lucinda, who I guess is still hanging around somewhere in the background, and catch up with you all in the not too distant future. Actually, maybe even physically catch up with you all in the not too distant future.
That would be a joy, wouldn't it?
Would be. Okay.
Thank you very much, Steve.
Bye-bye,
Thank you so much,
everybody.
Steve.
Bye-bye.
Thank you.
Great.
Bye.
It's great to see you. Excellent. Yeah. Lucinda just said, thank you. yeah. That's right. Just had to read that there. So do we have any questions for exoplanets and Uranus and just all planets in
I
general?
was going to perhaps ask one what's more exoplanet was, as a slight deviation from what you're doing. This might be a very basic and I say basic question in the sense of like, there may be a very simple answer. It may end up being so basic that it ends up with many answers kind of question. But I know when I've been looking at exoplanet, especially because at the moment I'm writing a paper with Uranus and there's a lot of comparison with, if we know this at Uranus, perhaps this may be useful for more exoplanet understanding. But when looking at exoplanets, I realized that there are lots of types of exoplanets and each one kind of has its own subdivisions. So you have obviously sub-Neptunes, we have hot Jupiters. I believe that's also another term used. So I was going to ask you, what makes an exoplanet, and then from exoplanets, how many categories do we have with exoplanets?
Right.
Yeah, I said I may have hit on a landmine. If I have, just let me know.
And some of this is going to be partially opinion based. I think that's my slight hesitation. So exoplanet one is easy. An exoplanet simply means not around our sun. So exo is extra, and then solar is the sun. So any planet that doesn't orbit our sun is an exoplanet. So typically they're orbiting other stars, but we also have things that we call rogue planets or orphan worlds, which don't have a star at all. And it's possible they may have formed as like a very small object on its own in a kind of star-like fashion, but it's more likely they were ejected from a solar system. So in fact, if you try and build a model of our solar system, one of the more successful models actually starts off with 5 gaseous planets and one is booted. So it is possible that, bullies like Jupiter and Saturn regularly throw out planets. So that's the first one. Exo simply means not our solar system. In terms of classes, as I understand it, the only reason we have a class is when we have a bunch of objects that we believe are similar. So in my talk, I talked about how we were using neural networks to try and impute missing properties. But another way we sort of experimented, but not currently with a lot of success, was whether you could ask the neural network, if you were going to group the exoplanets, how would you group them together? And would that be the same to how we group them? So typically the groups that are talked about are hot Jupiters. That's fairly well defined. That is a Jupiter mass planet or close that is on a very short orbit. So it is literally a hot Jupiter. It's very descriptive. So those we believe are the products of migration. So they start off forming roughly where our Jupiter is, but they're able to travel inwards during the very early stages of a planetary system where the gas disk is still around and it provides a drag, exchange of angular momentum more scientifically, but basically a drag on the planet. And it ends up on a very short orbit. So and we found those guys first because they're large and they're on short orbits. So they are the all-time easiest exoplanets to detect. I mean, they are the screaming babies of the exoplanet world because they produce a relatively large signature and they produce it all the time because they go around every, few days to a week. The other groups we typically talk about are things like super Earths and mini Neptunes, and there's a gray area of which is a super Earth and which is a mini Neptune. If you can measure the density, then you can tell, and you would call something with a rocky density a super Earth and something with a more Neptune or Uranus-like density a mini Neptune. But often we don't know. So we can only go by rule of thumb. And roughly speaking, for the planets that we have measured density for, all of which are very close to the star, because as I mentioned, they're the easiest ones to get good measurements for, we found that if you are more than roughly 1.5, so 1.5 times the Earth radius, you typically seem to have a lower density. So it suggests that around that area, you're able to acquire a thicker atmosphere. But that data is not based on a lot of planets because it's actually quite hard to get a density measurement. You have to have both mass and radius, which is tricky. It often demands a dual detection. So for those planets, we're basing it on, they're all orbiting very close to the star. So whether that 1.5 will hold as you move further out, I would say was quite questionable, especially if you argue that below that, it's easier to lose your atmosphere, the sun can strip it away. But if you're further from the sun's going to have a harder time at stripping that atmosphere. So you might find, and indeed I would expect, that threshold of 1.5 to change as you moved away from the star. And then we talk about Earth analogues or Earth-like planets, and that's got, guys, there's no definition for that. It's what anyone feels like writing. Because at the moment, we only can measure size or mass, we don't really know whether any planet is Earth-like. We're normally basing it on radius. And may I just point out, we have 2 Earth-sized planets in our solar system, the Earth and Venus, and their surface conditions are not similar. So I really want to tell anyone, every time you're reading a media article or even sometimes a research paper, and you hear the term Earth-like exoplanet, just remember you can replace it with Venus-like exoplanets and be just as accurate. It is true, of course, that Venus is not in the so-called habitable zone, but the edges of that are defined by the Earth's ability to control its temperature. So if you moved Venus into the Earth's orbit, would it be habitable? We don't understand really how Venus evolved to become Venus-y. So the answer might very well be no. For instance, it doesn't have plate tectonics, it doesn't have a magnetic field. There's a lot of things about Venus that don't seem to be just heat. So therefore, the habitable zone is not a very helpful concept for distinguishing between Earth and Venus. So in that sense, Earth-like, I would always replace it with Venus-like before making any assumptions. If you still feel the same way about the article, great, you've understood it well. If you feel completely differently about it, probably we don't know that much yet. We will do one day.
Awesome. Well, thank you very much.
I always find this really interesting because, people talk about gas giants and ice giants and terrestrial planets in our solar system, but it depends on your boundaries. Really, every single planet in the solar system is so fundamentally different from the other planets that they all fall into their own unique categories. And ironically, we're in a position really that you can apply better categorization to exoplanets than you can to planets in our solar system. We don't really know much about what those categories mean, but we do know that there are hundreds of planets that have very similar masses at very similar distances from the star. So those probably are somewhat similar. And our experience from planetary science is that they won't be. They'll be vastly different from each other in wonderful and unique ways, but they're certainly more similar to each other than any of the planets in our solar system. So the term terrestrial planet just means it's made of rock, but it's not made of rock. Earth is mostly iron. Mercury's got even more iron in it than the Earth. Mars has very little iron in it. The compositional differences in terms of bulk, especially if you sort of categorizing planets, is vastly different. If you think about what the surface is, well, Earth has a massive liquid surface. Venus has a massive gaseous surface, and Mercury has no gas on it at all. It's almost impossible to kind of come up with categorizations that don't just start being sort of meaningless, because we can see now Ceres is happily rotating away with a rocky surface. That's not considered to be a planet within our categorization scheme, but it's more like Mercury than it is like Earth. And so, where do these boundaries lie? So it's especially important when you come up with something like Earth-like. It is supremely frustrating as a planetary scientist when someone declares that their newly discovered planet is Earth-like when, well, hold on, it's twice the mass of Earth. Who knows what vast differences that plays out in terms of whether you can get plate tectonics. So there's some things we understand about Venus and Earth, and one of the big differences, although we don't know whether it's the dog chasing the tail or the tail chasing the dog, we know that plate tectonics is supremely important for Earth's cycle of carbon, and that Venus doesn't have that process, and maybe the Venus ended because it got too hot, or maybe Venus lost its water because it never had that plate tectonics. You know, that I've seen wonderful models that showcase how larger planets than the Earth would have supremely active plate tectonics, and I've seen other models that have shown that larger planets than the Earth close down and stop plate tectonics, and it's all within the realm of theory. So I think, yeah, as we say, never trust a paper that says we've discovered an Earth-like planet, unless you see a picture and it looks just like Earth. I think if it's got a liquid ocean and then there's small beings on it that communicate with radio technology, it's probably pretty Earth-like. But other than that, don't trust them.
Yeah, absolutely. I hate the term Earth-like. I have a huge vendetta against it, and I've decided that's the hill I'm going to die on, is to eradicate that phrase.
Yeah, I think you've made a friend for life there, Tom. It's you practically have it on a T-shirt, I think. I just have to send a message to Heidi, who's ready to join, but having some difficulties with Zoom. So I'm sending all of the links that I can.
Okay.
Let's see if those work.
I'm seeing a question in our box from George saying, I'm really interested in the theory of migration of gaseous planets. In our solar system, is there a possibility of a second migration? So for the migration I've talked about so far, it requires the protoplanetary disk, that disk of dust and gas, to still be around, because it's coming from that interaction between the planet and the gas. And we know those don't last very long, because actually we've observed when they're there and when they're not. So you've only got about 10 million years. And in fact, one of the big challenges of planet formation is to form Jupiter, Saturn, Uranus, and Neptune fast enough that they still have time to accrete their atmospheres from the surrounding gas, because you have to form this huge planet in quite a short period of time. Now, once that's gone, you cannot have gas-driven migration, but you can have other forms of migration. Now, one of those happens also relatively quickly, and that is planetesimal-driven migration. So when the gas is gone, you're still expected to be left with a sea of rocks that have not yet become planets. And you can bump and collide with those, and they're really a little bit of a jolt if you're a planet, but there's loads of those rocks. So they can also cause migration both in and out. But eventually, they are largely either absorbed into planets, ejected out the solar system, or they end up in one of our reservoirs, so the asteroid belt, the Kuiper belt, or the Oort cloud, which is like another band of rocks really, really far out. So eventually that also stops, because there's just not enough rocks around the planets to cause migration. So after that, there's still a possibility, especially if you're part of a binary star system. So binary stars can also cause the orbit of a planet to change in some cases. And we do see evidence of that. Sometimes we find planets that seem to orbit in the opposite direction. So not just on their side, but literally like the star is spinning one way and they are orbiting around the other. And when we see that, that doesn't make any sense at all, because if they have to form out of this gas disk, that gas disk is always orbiting in the same direction as a star. So to be effectively flipped on your head, you need an outside lever, and that outside lever is the second star. So that can also happen with migration. But for the sake of our solar system, the gas disk is gone, the planetesimals have gone, and we don't have a twin star. So we should be fairly stable.
I'll just follow up on that. I've seen some really interesting papers about this. Obviously, we're 5 billion years in, so there's got to be an expectation of some level of stability, but it's somewhat worrying that that level of stability isn't 100%. So people have taken the current orbits of all of the planets within the solar system and attempted to model what happens to them in the future. And generally speaking, everything is fine. But in maybe 3 out of 1,000 models, Mercury starts getting into a resonance with Uranus and sometimes falls into the sun and sometimes flies off into space. So we may not end up with a Mercury around our star by the end of the solar system, which is somewhat humbling, I think.
It's a good job we've got a mission going there now, Tom. Otherwise, it might be too late.
All right, excellent. Thank you very much for these questions and answers. It's been really nice to have a chat. And I think we can go to Uranus just to top up, see how Uranus is doing, see if it's still on its side.
I mean, as far as I can tell, I can confirm it's still rotated by a good 98 degrees or so.
It's a problem of our time, right?
Exactly.
It's the biggest mystery.
Exactly. So so we've actually had a bit of an interesting time. We had to stop observing for a little bit, and that was because we needed to put the shutter in place as we're now approaching towards daylight in Hawaii, along with there being, I think there may still be cirrus or cloud close towards that of the horizon. So we have to take countermeasures to try and ensure that we can still keep observing at Uranus. So we stopped observing for a little bit, and that is perhaps a good explanation as to why our image of the spectra, our lines are not as well defined as they were, unfortunately. The reason for that is essentially we've had to stop Cartman and restart it back up. That's our spectrograph. And what happens there is that all the data we had before, it's not like it's gone. I should stress on that in case anyone's worried. We haven't suddenly deleted it. All the data we had before was essentially adding on top of each other, on top of each other, on top of each other, which is enhancing the signal that we could see. But because Cartman has been restarted, all of that data that we had before that was adding up together, it has basically been, I don't want to say deleted, because that, again, I'm worried that someone may take that as we've just got rid of the data, we don't like it. No, we've that data is saved, but that's no longer what's being shown on DE. We're now starting on a new fresh frame, and that will be continued to be added up for the next hour and a bit that we have. So please don't worry, we haven't got rid of the data, but it means that we're looking at very similar lines that we saw at the beginning of the day when we were first adding up our data then. So as I said, our lines will be reappearing very shortly. So unfortunately, I can't give much of an insight if we are seeing anything on the edges, because again, if I take my mouse over towards it, we can just about see that the Q1 line is making its way through, but it is incredibly hard to see if there may be any asymmetries on either end of the line or even in the middle. So unfortunately, my update on that side is I can't confirm if we've managed to see back to Aurora coming into frame at the moment, but hopefully, as the signal keeps building up, we'll be able to see possibly something coming in, or maybe nothing at all. But as I said, it's the fascinating thing of this is that we don't quite know where the Aurora could be. It could be coming to say hi. It could have left us already. We'll find out.
Thank you very much for the update. Yeah, Uranus, the Aurora of Uranus, always elusive. Which side is it on? And then I've described Uranus as basically the magnetic field is like a bar magnet in a washing machine. I don't know how fair that is. Oh, how convenient. You're about to show. You're really good at this. Yeah. Yeah, it's like machine learning or something. I mean, you heard me say it, and it's back there. It is fantastic. Yeah, so that that's something that's very hard to represent in a figure in a paper, which is why I like the animation. This is quite an old animation, I think, from maybe 2003 from JPL. It was on. Someone asked me on Twitter the other day where I got this from, because they have a VHS tape which has this in it. Wow. They were wondering where I got it from, and I found it. It's in the middle of a big video on YouTube somewhere. Yeah, lovely gem of a graphic there. Exactly. I'm a big fan.
I often use it a lot in my presentations, because it's a great representation to show kind of how weirdly kilted it is, but also how the magnetic fields lines just keep extending and extending and extending out into space, which we ourselves can't actually see with our naked eyeballs. The best way to describe it. So it's fascinating to see just like how expansive it can be.
Right, exactly. Okay, so we have a distinguished guest coming up, Dr. Heidi Hamel, and I will just put you on the screen there by adding a spotlight. There we go, and I'll remove Uranus a little bit. Let's see. There we go. I think we have all four of us here, and hope you're well. Thank you very much for joining us.
Thank you. It's a pleasure to be here and talk about one of my most favorite planets, Uranus.
Yeah. I must admit, I'm a little bit starstruck. by your presence here. I don't think we've actually met at a conference. I probably would have remembered. But I will introduce everyone to Dr. Heidi Hamel, who received her undergraduate degree from MIT and PhD from the University of Hawaii. She's currently the Vice President for Science at Aurora, that's AURA, a consortium that operates large astronomical observatories, including the Hubble Space Telescope, that telescope you might have heard of, and the Gemini Observatory, and many more. Dr. Hamel primarily studies outer planets. She served on the imaging team for the Voyager 2 Neptune encounter and has studied Uranus and Neptune extensively with Hubble and Keck and other facilities. She's an interdisciplinary scientist for NASA's James Webb Space Telescope, plans to use her guaranteed observing time to study a diverse array of solar system targets, including the outer planets. She has been recognized for both her science work and her work in public outreach, which we're all a fan of here, including the Sagan Medal, the Carl Sagan Medal, and the San Francisco's Exploratorium's Public Understanding of Science Award. And in 2020, she received the American Astronomical Society's Mussorgsky Award for outstanding service to planetary science and exploration. And in particular, a really awesome honor is that you have an asteroid named after you. Previously, 1981 EC20 has been renamed to 3530 Hamel in your honor. And just before we dive in, I'm curious if, how that works. And do you have an idea where that is in the sky? If it was nighttime and you told someone, you could go, it's over there.
Well, the way asteroids are named is it's by the discoverer of the asteroid. That's an honor that they get to hold. And after the Shoemaker-Levy 9 impacts in 1994, which I played a big role in, a colleague named several asteroids after those of us who were deeply involved in that. And I did that all in Baltimore, Maryland, where the Space Telescope Science Institute was, because I was using Hubble. But afterwards, we came back to MIT, which is where we're working, and they had put little tinfoil stars on all of our office doors with our asteroid name underneath them. And it was really very sweet and very fun. And as to where it is, it's a main belt asteroid. There's nothing unusual. It does not have any unusual eccentricities or inclinations, sort of like me, kind of a boring person. I'm just doing its thing. And I don't know where it is today, but I could look it up probably in the JPL Horizons database and find out. Maybe that would be a fun thing to do sometime. I just don't know where it is right now.
I will endeavor to find it and make an animation and show.
Thank you.
Or I'll just draw a circle and pretend that I found it. Yeah. But yeah, thank you very much. So if you have some slides you'd like to present, I can share you could share the screen. I think I can.
Yeah, I thought I'd talk about something you mentioned, which is the James Webb Space Telescope. Before I do, I know that Emma, you were mentioning lines. Has someone already talked about what spectral lines are and things like that? Because I have some of that in my talk, but if you've already done it a million times, I'll skip over that.
I think we've discussed it lightly in terms of the idea that like a spectrograph acts like a prism almost, with white light just becoming a rainbow, but an in-depth one would be great. I don't think we've touched too much on that.
It's not going to be in depth, of course, because this is kind of a fun talk. But I just wanted to make sure it was okay I didn't want to bore anybody.
If not, I think if we've had anything this morning, I think we may have had a little bit this morning, but it would be great to have a refresher for this afternoon here in the UK.
Okay, and if there are any people who are joining that hadn't seen it before, because I know there's people are coming going in all the time. So let me try to share my screen. Let's see, where is that here? Where is that option in Zoom? I found it, the big green arrow. Yes, and PowerPoint and share. And then I will start the viewing part. If I can find it here. Okay, how does that look to you guys? Does it look good, like a PowerPoint should look?
Perfect. Thank you.
Okay.
Yeah, that's great.
So what I'm going to share with you today, very, very brief, I hope, is some information about the James Webb Space Telescope and where it is, what we're going to do with it. And I'm going to actually keep it super short so that there's a lot of time for questions that people may have. So Webb is complete. It is built. It is done. This is a picture of the Webb all folded up in its launch configuration at the clean room in Northrop Grumman Space Park in California just about 2 weeks ago. And that's sort of the last time it was in this configuration. It was then, and the reason it's folded up like this, of course, is it has to fit into the rocket fairing. Can y'all see my cursor if I move it? Someone.
Yeah, I could see it.
Okay,
Yes,
great.
I can see it too.
Yeah, so this is an Ariane 5 rocket on which it will launch. And here it is a cartoon showing you the telescope folded up inside the rocket fairing. It's such a big telescope that there is no rocket that we have that can launch it open. So it's all folded up and it's going to have to unfold. And we'll show a video of that later. Here is where the sort of the final steps of what we were doing a few weeks ago. Here is, again, James Webb Space Telescope all folded up. And what's going to happen, what did happen, is it was moved onto this device called the rollover fixture. It connected here, and then this thing rotated sideways, so the telescope was long ways, and then got put into a shipping container. And that's what this structure is off to the side. Once it was in the shipping container, it was carefully rolled out and through the streets of Los Angeles and put onto a boat. A ship. I've been instructed by NASA that this is a ship, not a boat. And this is not the actual vessel, but it looks very, very much like this. It's on a sister ship that looks like this. It's in the hold. Some of us were worried it was going to be like on one of those cargo ships with all the cargo containers and stuff. It's got its own private transport. And this is a map showing you the path that it's going overseas. We kind of joke, I posted on Twitter recently, yesterday or the day before, that we're on our way to L2 right now. But the first leg of the journey is over the Earth's oceans. Going through the Panama Canal. And yes, I do know that this cartoon, which I did not make, is incorrect. The Panama Canal is actually over here near the M and the A. So blame whoever made this, it wasn't me. And on its way to the spaceport at French Guiana. People ask, why are we launching from French Guiana, not from Kennedy? And the answer is we're launching on an Ariane rocket, and Arianespace uses the spaceport at French Guiana. And so that's why we're going to be launching there. And the most important news is we have a launch date. After years, more than 20 years, for those of us working on this project, we have a launch date, December 18th, 2021. So we are 69 days from launch, and it's amazing for me to be that close to launch after 20 long years working on this project. So now, why do we need Webb? People ask me this, and this gets a little bit to what Emma was talking about. We talk about light a lot, but astronomers don't recognize just visible light. Isaac Newton put the prism in the little hole, spread light out into its rainbow of colors. But in fact, that rainbow doesn't end at the rainbow colors of visible light. It extends out beyond the red, and it extends beyond the blue. And we have words for all of these kinds of light, and I'm sure that all the listeners have heard them. Words like radio and microwave that we use in our microwave ovens. You're using light to heat your food. Ultraviolet, X-rays, gamma rays. But infrared, just a little bit longer than the red wavelengths of light we can see, is what interests us for James Webb Space Telescope, and I'll tell you why. But overall, the universe emits light at all the wavelengths of light, not just visible wavelength, not just what our eyes can see. And thus, we do want telescopes that cover that full electromagnetic spectrum, all the way from the shortest gamma rays to the longest radio waves and beyond. And so James Webb is sort of sits in the middle here at the infrared wavelengths. But we have a problem. Why do we need to put James Webb Space Telescope in space? Why couldn't we just build it right here on the ground? It would be a lot easier, a lot cheaper. And the answer is our Earth's atmosphere is the killer. It absorbs light. It does not absorb visible light. That goes all the way through to the ground, which is why we have big telescopes on mountaintops like Mauna Kea, where Emma is right now at the NASA IRTF. And radio wavelengths make it to the ground. Now you're going to say, well, wait a minute, she's at the NASA infrared telescope facility. Doesn't that mean infrared light does make it to the ground? And the answer is, yeah, some of it does. The shorter wavelengths of infrared light make it to the ground, but the longer wavelengths of infrared light, what we sometimes call mid-infrared, that doesn't really make it to the ground. You know, there are some telescopes that have some capability at mid-infrared, but the other problem we have with mid-infrared light on the ground is that, here's something you need to know, mid-infrared light is heat. And telescopes are warm, and the Earth is warm, and the ground is warm, and the atmosphere is warm, and the telescope is warm. And that warmth, it swamps the infrared light from the distant universe. And so to have a really cold telescope that is really sensitive to this mid-infrared light, it has to be up in outer space. It's the only place to put it where it's cold enough that we can actually detect that warmth from the universe. Okay. So here's another thing about light, and this is what we were alluding to earlier. It isn't just about taking pictures at different colors of light. The key word is spectroscopy. Spectroscopy is crucial to the astronomer's toolkit for us to explore the universe. It's what Emma's doing right now. She's not doing, she's got some imaging, but really what she wants is the spectroscopy. And so what is spectroscopy? Well, when we look at the rainbow of light, and remember, it doesn't just end at red or indigo, it goes on. Some materials out there in outer space absorb light in a characteristic pattern. It has to do with quantum physics, has to do with electron shells, but you know, certain pressures and temperatures, these molecules absorb light, they take it away, it's gone. At other kinds of pressures and temperatures and conditions, materials can emit light. And that adds light to the spectrum in a characteristic pattern. And these characteristic patterns are what allow us to figure out what things are made of out there in the universe, even though we can't travel in a spaceship there. And in the olden days, when I was young, back in the olden days, we didn't have color printers. So we couldn't print rainbows that looked like this. So we had a shorthand, which we call spectra, where we would draw a line, and where light was missing, we would make it go down, and where light was added, we would make it go up. And so these spectra are representations of the added light or the missing light that tells us what's happening out there in the universe. And so NASA doesn't like us to show these. NASA calls these the squiggly line plots, and NASA won't really allow us to release them. So for example, here's an example of this. Here's the beautiful Eta Carina Nebula imaged by Hubble. It's beautiful. The picture tells you a lot about what's happening, and there's some details on there. But for us scientists, what we care about is the spectra. And so, you know, when you spread the light out into the spectrum and you look for those added lines or missing lines, here's an example of what NASA allows us to print. And here it is. You can see the helium lines, the nickel lines, the iron lines. You can see shapes to the lines, and that tells us about, you know, rotation, and it tells us about motion. The strength of the line tells us about composition, and the positions tell us the chemistry. What you would see in a paper about the Eta Carina star would be something like that. And so you'll see a lot of these squiggly lines in any scientific presentation, but I hope you now understand what those squiggly lines are. They are information about certain molecules or atoms out there in the universe. And for us astronomers, spectrum is science. This is what we do. And we're going to be taking tons of amazing spectroscopy of everything in the universe with James Webb Space Telescope, including the planet Uranus. And that's where the real science happens. I don't want to say that's where the magic happens. That's where the science happens, is spectroscopy. and here's my last bit of science, really, before I jump into James Webb. When you look at a nearby star, you can see a pattern of lines that looks something like this. We've named them after the Greek letters, and it doesn't matter what molecule it is, it's in almost all stars. My point about this is that when you look at a nearby galaxy, you can see the same pattern, but if you look carefully, you see it shifted to the red. And if you look at a distant galaxy, it's shifted more to the red. And if you look at an extremely distant galaxy, it's shifted really far into the red. In fact, those characteristic lines we want to use to study stars and galaxies are shifted into the mid-infrared. Hence, to truly study the earliest galaxies that ever formed in the universe, we need a telescope that is optimized for detecting mid-infrared light, and it has to be able to see the faintest galaxies in the universe, the most distant, the earliest ever formed, and that's why we've built James Webb Space Telescope. So how does it differ from Hubble? Let me show you a little video. Well, there's 4 reasons that I want you to remember. It's bigger than Hubble. The mirror is bigger. It sees redder than Hubble. It is colder than Hubble, and it is further than Hubble. So bigger than Hubble. Here's what I mean by that. Here's a cartoon showing you to scale the Hubble Space Telescope and James Webb. Overall, they're about the same size, right, compared to the person standing there. But the mirror, that's the aperture, that's the piece of the telescope that collects light. It's much, much larger for James Webb Space Telescope. Hubble's mirror is 2.4 meters across. Webb, its effective diameter is about 6.5 meters, and it's the area, so it's pi r squared, so it's far more sensitive than Hubble. And so it's a lot bigger than Hubble, and that's what we need. Redder. Here's a picture of a guy in visible light holding up a garbage bag, and all you see in the garbage bag is the reflected light off of outside of the garbage bag. But if you had an infrared camera, you could see right through the garbage bag, and you could see his arm underneath there. And I'm sure many of you have seen this with infrared cameras. You understand that you can get infrared pictures and you see things that look different than they do in visible light because you're seeing the heat. And this is true in space as well. Here's a constellation that many of you may be familiar with, the Orion constellation. And you may know, of course, that there's this lovely nebula, the Orion Nebula, here in this sword that's hanging from the belt of Orion. But this is a visible wavelength picture. With infrared pictures, this is what the Orion Nebula looks like. And you could actually see through all the dust into the bright glowing regions of the Orion Nebula. And with Webb, of course, we'll be able to get super high resolution images of those in the windows that we can see through here. So Webb sees redder than Hubble. So both we can peer through the dust in the universe and we can see the warmth from the most distant galaxies. Webb is colder than Hubble. And we do that by using a shade. And here's a picture of a shade on the beach. And if you were at the beach and it was hot, you'd get cooler by getting into the shade. We have sun shields on Webb that do the same thing. All those pink things that you see, those are our sun shields. And they will always be between the telescope and the sun, the earth, and the moon, all right? They will always be pointing away from that. And so we will keep this telescope in the shade to keep it cold. And how cold is cold, you may be asking. Let me try to put it in human terms. We're gonna be operating all of our instruments below 50 Kelvin, all right? And you're like, well, I don't think in Kelvin. Okay, well, maybe centigrade, minus 223 degrees. So when I say cold, I mean minus 200, more than minus 200 degrees centigrade. For any American listeners, in Fahrenheit, that's minus 370 degrees Fahrenheit. So negative hundreds of degrees. How do we get it that cold? Well, I'll use an analogy that you might be familiar with. If you use sunscreen, you're familiar with sun protection factors of 10 or 50 or even 100. Because of the construction of our sun shield, our sun protection factor, solar protection factor is 1 million with the James Webb Space Telescope. And so the temperature on one side and the temperature on the other side drops by 300 degrees because of our 5-layer sun shield. So it's pretty cool. And it's further, this is the last point I wanted to make. We will not be in low Earth orbit like Hubble. We're going to be out at the L2 point. So if you drew a line from the sun to the Earth and then kept going for 1.5 million kilometers, that's where the L2 point is. We're not going to be sitting at L2. We'll be in a tiny orbit around L2. How do we get there? I already showed you this picture, the Ariane rocket, and it's folded up. And here's a video that shows you unfolding. And this process is going really quickly here. This process actually takes weeks to do. It's as highly sped up in this picture here. What's happening now, you already saw our solar panels unfold and you saw our radio beam unfold. And now we're slowly deploying the sun shield, pulling it out on one side and then pulling it out on the other side. This is going to happen, we believe, if all goes well. See how we're now spreading the sun shields apart? By Christmas, if we launch on the 18th, then we will have a deployed telescope here, the sun shields by Christmas. And after we deploy the sun shield, then the telescope wings themselves will unfold. The secondary, watch for it. It's going to unfold soon. A little trim tab for angular momentum. Here comes the secondary, and there go the wings. And now we have a completed telescope. This whole process of unfolding and getting to L2 is going to be at about a month long. So what are we going to explore? Science. We have 4 science themes with this, and I'm not going to go through them in great detail, but I'm happy to answer questions if I can. I already mentioned that one of the key drivers of building Webb was to see the very first galaxies that have formed in our universe. That's the goal. That's the driver. When we started this, it was called a first light machine. And so this is going to be one of the crucial scientific outputs of this. Just like Hubble was designed to measure the size of the universe, this telescope is designed to see the first galaxies, maybe even the first stars, although that might be really hard. So I'm not going to promise that, but first galaxies, yes. And then because it is so powerful, we will be not only able to see those first galaxies, but of course, galaxies all the way through the evolution of our solar system up until today. And so we will watch the assembly of galaxies over space and time. And that's another key theme for this telescope. Thirdly, as I mentioned, we can peer through dust, so we can look into stellar cocoons where stars are being born and actually see some of the processes by which that is happening. And also protoplanetary systems, watch how they are forming within places like the Orion Nebula. And then fourth, planetary systems and the origins of life. Just before I joined, we were talking about looking at planets around other stars, trying to look at the chemistry of the atmospheres of planets around other stars. We will be doing that with James Webb Space Telescope. It wasn't designed to look for the chemistry of the atmospheres of planets around other stars because they hadn't been discovered when we started this telescope decades ago. But because it is such a powerful machine, it will clean up, particularly on the large giant planets and ice giant sized planets like Uranus, our friend, topic of this whole series. And it will be able to characterize their atmospheres. And we will also be able to look at objects throughout our solar system, which is what my program on the James Webb Space Telescope is designed to do. And so I'm not going to go into detail because I want to keep this short, but I will just share with you that if we look at this cartoon of our solar system and ask, where is James Webb? It's here between the Earth and Mars. And remember I said its sun shields will always be between the telescope, and the sun shields will always be protecting us from the Earth, the moon, and the sun. And what that means, of course, is that we can't look at anything interior to that. So we will not be looking at Mercury, nor Venus, nor the moon, nor Earth, nor some of our near-Earth asteroids in certain locations. Everything else is fair game. And in fact, here's a synthesis of our solar system. Each one of those little lines shows you the instrumentation and spectroscopy and cameras that we plan to use to study all of the objects in our solar system. Mars, near Earth asteroids in the right configuration and the asteroid belt. Jupiter and its moons. Saturn, its moons and rings. Uranus, yay, Uranus. Neptune, Pluto, and many of its companions in the Kuiper belt, including comets as well. So all of this is part of cycle 1 observations for James Webb Space Telescope. A lot of it is part of my program, and that is the ice giant part of it, which is why I actually joined James Webb Space Telescope. The ice giant part of this is being led by Lee Fletcher, and I know that Tom is, I hope, involved, and other people are involved there at Leicester, folks who are running this Uranus program. I know Lee has already talked a lot about Uranus, and so I'm not going to dwell on it, but this is some of the spectra that has been modeled by Lee and other folks there. The kind of data that we hope to get with Webb for Uranus. And I wanted to show you this picture. This is one of our Keck pictures of Uranus and its rings. And the colored rectangles you see are the fields of view of the integral field unit of the imaging system on the MIRI camera. And they are beautifully tuned to the planet Uranus. And I joke with them all the time. I'm like, yeah, I know you really made this to look at galaxies, but I think you really made it to look at Uranus because it's perfect for Uranus imaging and spectroscopy. And so there will be great Uranus data coming from James Webb. I'm really excited about that. Also, sometimes we don't know what's going to happen in the solar system. Rare, unusual things happen. What if we get the comet of the century while Webb is up there operating? We're ready. Program 1253 is ready to observe that comet. What if another interstellar object comes by, like Oumuamua or Comet Borisov? We're ready for that. We have a program 2337 is ready to go if we have one of these, and I think we will. And what if there's another impact on Jupiter? They happen all the time. One happened, 3 weeks ago? There was another impact on Jupiter observed by amateur astronomers. If that happens, we're ready. Program 1424 is ready to go on Jupiter. So we're ready for whatever is going to happen. And I just want to kind of end my little spiel about our science in that I'm telling you all the science that we're planning to do. We've been planning for more than 20 years for this science, and we still need Webb. There's no other telescope on the ground or in space that can touch what I'm talking about. But that said, what we learned from Hubble is that when you look at the top 10 scientific discoveries from Hubble, only 5 of them were originally planned. And so I'm showing you what I'm planning here and what our teams are planning. But in fact, we don't really know what we're going to learn. And we don't know what we're going to find when we're talking about the assembly of galaxies. We don't know what mysteries we're going to uncover when we're looking at the birth of stars and planetary systems. And there may be mysteries in the solar system that we just haven't even thought of yet. And that is the power of a great observatory like James Webb Space Telescope. We don't know for sure what we're going to learn, but I can tell you that sometime 10 or 15 years from now, we're going to look back on what we've done and we're going to say, that was amazing. This is amazing what we have learned. And so again, we have a launch date, we're ready to go. I do want to encourage you to be patient. You have to wait for the science. After we launch, I already told you, it takes us a month to get to L2. And then there's 3 months of telescope alignment of all the segments to make sure they're all working properly together and checking out the whole telescope system. And then after that, there's 2 months of checkouts of the cameras and the spectrographs. And only then will we be able to start doing the science that I've been talking about. So launch in December. Science starts in July 2022. I am just so excited about it, and particularly about the Uranus observations that I've been waiting for 20 years. And I'm really looking forward to it. And so with that, I'm going to turn off my screen and start answering questions and chatting.
Thank you so much for giving that talk. Let's see my screen. There we go. Hello. Thank you very much. That's great. I was actually going to ask you straight away, because you have a lot of the history in observing Shoemaker-Levy 9 impacting Jupiter as well, and also the dark spot on Neptune as well. I was wondering if you have any specific goals in mind for follow-up observations of your own research from the 90s and beyond.
Yeah, great question. What I'll share with you is that I am now a vice president for science at a major research organization. And I made a career shift about 10 years ago, where I committed my life, instead of being an observational astronomer, to enabling new facilities for the next generation of scientists. And so I don't do observational astronomy anymore. I have turned over all of my time. When I made that shift 10 years ago, I gave my Hubble programs to the next generation of young scientists. I said, here, it's your job to do follow-up observations of great dark spots, not only on Neptune, but even the one we saw on the planet Uranus back in 2006 or 2005. And it's your job to be ready to do follow-up observations of impacts on Jupiter. My Hubble, I had several programs that were active, and I turned them over to other people. Also with James Webb Space Telescope, I am an interdisciplinary scientist for that. And with that came over 100 hours of guaranteed time. I have given all of that time away. It has all gone to other people, including Lee Fletcher there and folks there at Leicester to do the ice giant work. I've given it all away, and I'm not doing it anymore. So, but that's okay. We need to have people like me who are astronomers in these positions so that we can be advocates. In the United States, we're advocates to our stakeholders in Congress and NASA and the National Science Foundation. My job now is not so much to do this science anymore, but to make sure that Emma has an amazing, huge new space telescope to use. Not only Webb, but whatever our decadal survey says here in the United States, we're all on tenterhooks waiting for it to come out. Hopefully it'll say we want to build a whole new giant space telescope to do ultraviolet imaging that just can't do with Hubble. Hubble's not big enough. We want to build the next generation space telescope. Like that's my job now. So
right.
Yeah.
That's amazing. Amazing. That's very generous. And when you said you were handing it over, I was thinking it would be like a control panel of some kind, so that they could operate the telescope like a Hubble. But so we have a question came in. Will Webb look for Oort cloud objects?
Ooh, good question. Yeah. No, we haven't developed a program for that. I think that they're going to be too cold and they're too far. So I don't think so. We will be looking at things between the Kuiper Belt and the Oort cloud. Sedna is one of our targets, and that's a really distant object. People often ask me, are you going to look for Planet 9? Or whatever that one they call it. I lose track of what it's called nowadays. Mm-hmm. The one that Mike Brown and Batagian and other people are hypothesizing is out there. And my answer is, we won't look for it. We're not a survey telescope, we're a pencil beam. But if a survey telescope like the soon to be operational Rubin Observatory down in Chile, if it finds this object through its surveys or other surveys, find it. We will for sure look at it with James Webb Space Telescope, but we're not going to be the ones to find it. We'll be the ones to characterize it. But I think Oort cloud objects are probably beyond even the reach of Webb right now. That might be something for that next generation of amazing, huge space telescopes.
Amazing, yeah. I have another question. So knock on wood, you probably already know what I'm going to say about Webb. Knock on wood, it won't happen. But if for some reason Webb flops, now that we have learned all the hard lessons building it, could we, or are there plans to build a replacement? And you probably don't want to talk about that, but maybe you have plans.
Well, first of all, let's talk about what we've done to ensure that Webb doesn't flop, okay? We have tested all the components of this telescope from 6 ways to Sunday. We have put it in chambers that simulate the cold and vacuum of space. We have put it on things that shake it. We have put it on things that thermal cycle it. We have tested the deployments with offloading so that they're in the pressures that would be simulated by outer space. We have done everything we can to test and prepare it. And people may have heard stories about it along the way. It's like, oh, did you hear about all the nuts and bolts that fell off James Webb Space Telescope? I'm like, yes, that's why we shook it to discover if there's some problem with that. And we fixed it. And did you hear that when they were deploying the sun shields in the test, the cables got hung up on the little, the little pulley? Well, yes, that's why we tested it. And so we fixed that problem. And so we have, like I said, done all the testing that we can think of as humans, scientists and engineers, of the structures and the equipment and everything so that it won't fail. We also have backup plans. We've learned our lessons. Space is hard. It's rocket science. It's hard to do. Let me give you an example of things. You remember the Galileo spacecraft that went into orbit around Jupiter? Do you remember its primary antenna didn't open? All right. So when we talk about things deploying in space, it's rocket science. It's hard, it's scary. But for example, if we start to try to deploy things and they don't work, what do you do? What do you do when something doesn't work? Like when you can't get a drawer open, you try and try again. Okay, so you cycle through your commands. If you get really exasperated, you might kick the cabinet to try to get the drawer to open. So we have analogous, not kicking, but we have like, you can shimmy the spacecraft to try to loosen things up. You can even, twirl it a little bit to try to loosen things up. You can rock. If it's a pulley thing, you rock back and forth. So, we have all these tricks, and I'm making them sound a little flip. Believe me, these are like extremely well characterized motions and maneuvers. It's not that you just like kick the spacecraft, right? It's very well controlled, and you track the telemetry every moment that you're doing these things. But we're ready for all of this, and we've had other instances where things haven't fully opened, and you do workarounds. So if the side panels don't come out, we still have the center panel, right? And if the sun shields don't fully deploy, they're still going to work pretty well. The secondary has to deploy. If we don't have secondary deployment, we have no light to the instrument. So to me, people ask me, what are you most worried about? I'm like, it's secondary. That's the most scary thing we gotta have. And it's got to be in the right orbit. The rockets have to do their thing.
Will you go and see the launch?
We got to get through launch too, right? But Ariane is a really successful rocket, and people have been paying very close attention, especially to the recent Ariane 5 launches, and making sure that any anomalies we're accounting for and planning for. So what can I say? We have done everything that we can to ensure that this will work. What if it doesn't work? I don't think we're going to build another Webb. I think that we will look to the future, and we'll look on to like the next thing. It took us a long time to build Webb, and we've learned a lot, but we don't have a second one sitting in a room somewhere that we can do. I mean, we can talk about Hubble and talk about, we can talk about Nancy Grace Roman and how that came to be, but we don't really have another Webb sitting around anywhere.
So someone actually did mention the Hubble mirror. Oh no.
Well, remember, Hubble was a monolithic mirror, and it was the wrong shape. But to be fair to the optical engineers who actually know these guys, because they used to live like right by the plant where the Hubble was built, those guys made a perfectly wrong shaped mirror. It was wrong, but it was perfectly wrong. And that allowed us to build corrective optics for Hubble, which is now working at the peak of its game. Webb is built differently. Webb is segmented mirrors, and they all have actuators behind them. And so we can change the shape of these mirrors and manipulate them in real time. We couldn't do that with Hubble. And so, that lesson was learned.
Excellent. Thank you. Yeah, maybe not dwell on all the negatives too long. The science is going to be fantastic, and really looking forward to hearing or seeing the obviously the images, but the spectra is what we're all, that's going to reveal a lot. And we've waited a long time for it. And I think you've been involved for now more than 20 years. And I briefly saw your exchange the other day with Mark from ESA. I think it's Mark, yeah. Talking about how you've been in panels for this working group meetings for 20 odd years now. And it must be amazing to see that it'll be up by Christmas, the usual hilarious phrase that we say for things that, but will you see the launch? You go to the launch or?
No, I'm not going to the launch. I don't rate high enough to be there. The French Guiana Spaceport is relatively small compared to spaceports like Kennedy. And so only like the high level dignitaries from NASA and ESA, maybe a few of the really key people who were the key engineers, key scientists. I'm a lowly interdisciplinary scientist. I don't rate that. I will likely be at the Space Telescope Science Institute in Baltimore, Maryland. That's probably where I'll be. And I'm working right now with the Planetary Society. This is a worldwide advocacy group for space exploration led by Bill Nye, the science guy. And I'm working with them to be sort of an on-the-ground spokesperson for the launch for the Planetary Society. So if you're looking for a live stream to watch, that isn't NASA or ESA, and you want to hear, Bill and I talking about what's going on, and that's what I'll probably be doing for the launch, working with them.
That'd be awesome. Yeah, I might book some days off around that time to guarantee that I'm totally free and share it widely and everything. That sounds great. We have a question that came in from Elizabeth Tasker, who actually just spoke via YouTube. Given the length of time it takes to design a very novel and new instrument such as James Webb, how do you design it so that it can handle scientific questions that have not yet been asked? For example, I think, in brackets, about 25% of James Webb is allocated for exoplanet atmospheres. But when James Webb was being designed, did we even know any exoplanets, or let alone methods of exo-atmospheric detection?
Yeah, first, astronomers, not me, because I was too young, they started talking about Webb, what would become the James Webb Space Telescope, even before Hubble was launched. All right. And I think the way we handle this, Elizabeth, is we try to make our future telescopes to be so powerful that whatever questions we have now, by the time that telescope is built 10 or 20 or 30 years down the line, those scientific questions are still relevant, and we haven't surpassed the capabilities with any other facility. I mean, I think that's kind of was a message I was trying to get across with James Webb. Yeah, we didn't I think we knew about the pulsar planets back when we were starting to build the next generation space telescope, which became James Webb. We knew about the pulsar planets, but we didn't have, we hadn't launched Kepler. we hadn't launched TESS. We didn't know we knew that we suspected planets were out there, but we didn't have a stable of 4,000 planets to pick from as actual targets. But we were building a telescope with enough capability that once we did find these planets and, oh, hey, presto, we can actually do spectroscopy of their atmospheres. We can actually do that science. So I and my colleagues who are looking forward to the next generation of space telescopes, we don't want to make a little baby step. We want to make a quantum step forward. We want to build something like, like a LUVOIR. If you've read about the LUVOIR mission study, I personally wrote a paper for the Decadal Survey advocating for something kind of between the LUVOIR concept and the HABEX concept. And I called it the Carl Sagan Observatory because I'm that kind of person. And
Right.
And his wife Anne graciously allowed me to use that name. She was a co-author on my white paper to the Decadal Survey. We talked about we need to build something that big and that difficult and challenging because, Elizabeth, that's going to be the tool to characterize those planets that you don't want to call Earth-like. I was listening to that. I call them Earth-like because to me, that's kind of a holy grail. I want to find an Earth-sized planet at the right orbit from a sun-like star to be able to have liquid water and be able to do the spectroscopy of its atmosphere and find out if there is liquid water there and carbon dioxide and maybe industrial pollutants that would be clues that there was actual life on that world. So I personally am going to continue to use Earth-like in that context because that's what I want. I want to know, is there life out there? We can't answer that question with Webb, I don't think. We'll make strides towards it, but I don't think we can answer it. But maybe that next telescope, the one we're designing, the 15-meter deployable UV optical Keck Observatory in outer space, maybe that is the one that might answer that question.
I have a question, actually. So the building of James Webb obviously took a long time. Do you expect that to always be the case for big telescopes, or is it something unique about this about James Webb?
All our big missions take this long. People forget. They forget how long it took to build the Hubble Space Telescope. The story of Hubble is the story of Webb. There are history books you can read about the development of Hubble, and you just substitute Hubble with the word Webb, and the story is the same. These are technologically challenging. They have no precedent. Little unclear. Well, Hubble had a little bit of precedent because we think on the dark side, what we call the dark side of the U.S. government, we think that maybe they had Hubble-like telescopes, but they weren't using them to look out, and so the sensitivities and the stringency of the requirements were not as precise as you need for the astronomical use. So it isn't simply a matter of taking a downward looking telescope and pointing it up and saying, oh, it works. It doesn't. One could imagine that maybe some of those other agencies that we're not talking about maybe are exploring segmented telescopes in space. But even if they are, they're not doing it with the sensitivity required to detect the first galaxies that ever formed in the universe. So astronomers push this technology beyond what is available to us, and that's hard. It just takes a long time. You're using new techniques, you're using new testing procedures, and so it does take a long time. I think if we get the go-ahead for a very large UV optical segmented space telescope with the next Decadal Survey, it's not going to be done in 5 years, people. We just don't know how to do it yet. We've never done it before. We're going to have to figure it out. We're going to have to figure out how to do it. We're going to have to figure out how to test it. It's just going to be challenging. So it's going to take a long time. You know, part of the story with Webb, if you look at some of the congressional reviews that have been done, there's a report called the ICRP, the Kasani report. It really talks about, it wasn't so much technology that limited, it was also the management and how the funding was provided over the years. I know I served on some of these oversight panels in the early years. Webb didn't have the money it needed in the early years to cover things that were unexpected and going wrong. And so those things all had to be pushed forward, and that increases the cost. If you start, and also, well, let's just be brutally honest here. I'll be brutally honest. I'm looking right into the camera here. This idea that when they said the original cost of this next generation space telescope was going to be like $500 million, we all knew that was nonsense, right? We all knew that that was just not true. But that was the Dan Golden, better, cheaper, faster. Everything had to be cheaper. And so to get this thing started, there's like, oh, well, it's not going to be that expensive. We learned all our, you know, it was just not true. And we knew it. A lot of us are saying, try to be more honest about these things. And there was just a recent report that just came out about large NASA missions. And one of the things they said is, you got to be honest about how much these things cost. And so I'll be honest with you, if we want to build a super large, giant Keck observatory in space, it is not going to cost $500 million. It's going to be closer to $10 billion or maybe $15 billion. We did learn a lot of lessons from Webb, for sure, on how to build these things, how to do deployments and all that. But also prices inflate over 20 years. And you ask, how much did Hubble cost? $3 billion. Well, if you inflate that 30 years into the future, it costs close to $10 billion. So we're in scope here, and we're trying to be honest about the costs. And sorry, I lost track of the thread.
Yeah.
But the point is that these telescopes take a long time because we just have never built them before, and they cost a lot of money. And let's just be honest about that. But the scientific return on these large facilities is revolutionary for the field of astronomy, all fields of astronomy. I hope you got that from my presentation. Although this machine was built for the first light in the universe, we're going to revolutionize all fields of astronomy with it, including solar system science, including the study of Uranus.
And it's not like that cost is in a single year as well. It's spread out, and no one is throwing the money away. It's going to salaries, science.
Yeah, it's people.
A lot of people think it's like, oh, we're burning the money.
No, it's
people, right?
It's
exactly.
people. Most of it is people paying for scientists, engineers, miners who mined the beryllium, steel workers who crafted the steel structures that we use to test it. I mean, it has huge ripple effects all across, you know, the economy of the United States, and for James Webb, Europe as well, and Canada. You know, our fine guidance system and our nearest instrument are from the Canadian Space Agency. So it's a multinational endeavor to build one of these large facilities. And I believe that if the United States decides to lead on a next generation large telescope, we will be doing it in partnership with our international colleagues. We have to. We have to. I mean, it's just the right thing to do.
Absolutely.
One of the great frustrations for me when I'm, looking at the reports about the next generation and what's coming is that you talk about how far in the future they will be, in the 2040s, and I'm writing reports trying to argue the case for space missions to Uranus, and you realize that's your competitor. As a space mission going to Uranus, you have to show that you can do better than this future space mission where we'll have potentially a 15-meter telescope.
Yeah, it's not an either or thing.
It is not. No, absolutely.
Not. I mean, there are things that we cannot do with a large space telescope. We can't really measure the magnetic field. I mean, we're trying to measure the aurora, and from that we hope to, infer the structure of the magnetic field. But the actual detailed moments of gravitational moments, we can't dipole moments. We can't do that with even the largest space telescope. We can't send a probe into the atmosphere with a large space telescope. We can't measure the noble gases. We can't learn about the detailed chemistry. They are complementary, and I don't want anybody to think that these telescopes, supplant a mission, an in situ mission. They always work together. And so, Tom, that I will be advocating just as hard for an ice giant mission as I will be for a space telescope, because it's not either or. You can't do some of this planetary exploration work with telescopes, although I'm an astronomer and have used telescopes for most of my career. It's got to be both. We're gonna advocate for both.
Absolutely. There's things that you can't do with James Webb unless you're at the planet. You can't, what does the night side of Uranus look like? No space telescope at Earth will ever know that. And
it's especially important for Uranus, right? Because as we have been finding, what happens on the daylit side is not what's happening on the side at night. That's what we've learned over all these decades of watching it, that when it was in its sideways configuration to us here, Uranus, help me. When we were at Ring Crossing in 2007, what we saw with the sunlight illuminating both hemispheres of Uranus is all sorts of cloud activity that simply was not there when we were in the face-on configuration for the Voyager flyby. And so there are changes that happen on this planet that we won't be able to see with telescopes because we just can't do it. We need the missions. We need the planetary missions.
I concur. Definitely want the missions there. There's so many reasons. There's so many reasons, but just please, somebody send the mission, please.
Absolutely. I like to think of it as kind of a greater than the sum of their parts thing as well. We proposed a lot of these observations to support missions over the years. We probably wouldn't have got the time on for a lot of our discoveries, actually, but we wouldn't have made the discoveries if it wasn't for having a combined space mission plus ground-based or space-based observations. Like we saw the rings of Saturn are raining material into the planet, and then just a few years later, Cassini flew through and felt all of these charged particles coming from the rings and going into the planet directly. So it all adds up, and there's plenty of other studies where the Aurora observed from Earth-based platforms, whilst spacecraft are going around and measuring the particles that are coming through and landing on the planet. So you look at the planet, see, oh, look what's happening here. What's causing that? Well, we can tell because we can see those particles flying past the spacecraft. I see that you have Uranus.
I was going to ask
the
about
star
that.
of the show, or the
Uranus,
not star of the
that's
show.
Uranus on the slit there.
So this is yesterday's Uranus.
When I look at this, Emma, though, it looks to me like I'm seeing the pole brighter than the rest. Am I seeing that correctly, or is that just a weird artifact of the camera?
So, okay, this is where Tom may need to jump in a little bit, but if my correct thinking, so we have the sun side, or we have the southern pole that is facing us at the moment in this picture, with the northern pole basically tucked behind. I'll see if I can bring up James's wonderful picture. So yeah, so at the moment, the Uranus that we have in our film is slightly flipped, I think. So it's the other way around from what we're seeing in this animation, but the slit is kind of horizontally along. So my knowledge is that we have the day glow from the sun, which is what's massively lighting up on one side of Uranus rather than the other, with the halo, as Tom was saying earlier, the halo illuminating around Uranus itself being the rings.
I'm perennially frustrated by Heidi's amazing images. And we worked together a little while ago where we were doing some observations of Uranus from the Very Large Telescope in Chile, where we were actually using adaptive optics. And you expressed surprise about how low resolution our adaptive optics images were. And I actually inquired into it, and we're focused on the spectra, and so always there's trade-offs there. And here especially, it's mostly just the seeing of the Earth's atmosphere is fading everything out, unfortunately.
Yeah, with Keck, of course, where we get most of our most spectacular Uranus images, we spent decades, maybe 15 years, seems like decades when it's 15 years, tuning the adaptive optics system of the Keck Observatory to track on the extended disk of Neptune and also Uranus themselves. We don't use point source. And And we tweak the adaptive optics parameters in certain ways. So we have special settings that really allow us to work at the diffraction limit of the 10-meter telescope. And, people are like, why don't you just, 8-meter instead of 10? 8 and 10 sounds the same. When you're working at the diffraction limit, what you gain by going from 8 meters to 10 meters is really makes the difference in trying to understand the details of the atmosphere. There's a new image circulating on Twitter from the Keck telescope I've taken of Neptune just a couple of weeks ago.
Yeah, it's amazing.
Yeah, isn't that beautiful? I got a heads up from the chief scientist. He sent it to me like the day it was taken. It's like, look at our Neptune image. I'm like, wow, that's great. You can see the pole. And what I like about Neptune is it looks like it actually has a cloud like at the South Pole, like where the rotational axis comes out of the planet. There's a cloud right at that point, like it's poking the planet. I just think that's really very cool. We wrote a paper about it because one year we were looking at it and it split into a double, and the pole is double, and then it went back again. So it's kind of cool. Uranus, much harder. Uranus, without a whole lot of post-processing, it's hard. There's, you can see some stuff, and even with the Hubble at visible wavelengths, when Uranus was near its ring plane crossing, there was a lot more cloud activity, and we saw the great dark spot for like one set of observations. There was a great dark spot on Uranus, and that was really very cool. But then it disappeared like by the next time we looked, and we've never seen it again. Unlike Neptunes that come and go a lot. So.
Actually, I would like to ask you about the Great Dark Spot and what is a nice simple explanation for what is causing the Great Dark Spot on Neptune on that subject.
Yeah, well, you'd really need Tim Dowling or Ray LeBeau here to explain it, because it has to do with the vorticity of the planet's atmosphere, blah, 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 blah. The way my simplistic brain envisions these dark spots, mostly based on the Voyager Great Dark Spot, the one that we had the best images of, to me, they look like holes. They are gaps in the clouds where you can see to deeper layers, which are darker. And it isn't so much that they're the giant storms like you have on Jupiter. I think they were kind of a different beast than that. But I have to admit, I am not a dynamicist, and my brain just short circuits when I have to talk about potential vorticity. And so I can't really give you solid explanations. I will share that they are much less stable than the large features that we've seen on Jupiter or even Saturn. Our long database, 30 years of database of Hubble observations have demonstrated that. The Great Dark Spot itself, the Voyager Great Dark Spot, like the greatest Great Dark Spot, it was gone 5 years later when I first used Hubble to look at Neptune. And that was a huge surprise. We just really, it was hugely surprising to first find a great dark spot on Neptune, because we had never seen such a thing, because we never had visible wavelengths that were high enough resolution back in the 1980s to be able to see a dark spot. All of our high resolution images were at near infrared wavelengths. At that wavelength, the methane in Neptune's atmosphere is strongly absorbing. And so you were only seeing high altitude clouds that were up above the bulk of the methane absorption layer. And the Great Dark Spot is deeper, all right? So all we could see in the 1980s were these bright companion clouds that were up above the Great Dark Spot. And we confirmed that. I confirmed that because one of the saddest moments of my life. You know, I worked at JPL as a mission scientist for the Voyager Neptune mission. I went there in '88. I just finished fresh out of my PhD, right? Just like the ink was still wet. Went to JPL, worked on all the approach phases of Voyager Neptune, discovered the Great Dark Spot, discovered the Scooter Spot, discovered all these other atmospheric features. But the head of the imaging team came to me in sort of mid 1989, and he said, Heidi, we need ground-based imaging of Neptune as ground truth for the Voyager observations. We need to understand what those things we've been seeing from the ground are in the context of Voyager. And I said, yes, you're right, we do. He said, you are the world's expert in imaging Neptune. I'm like, oh no. And so I spent the Voyager Neptune flyby on the summit of Mauna Kea, right? The next telescope over from where Emma has been doing observing, the 88-inch 2.2 meter telescope, imaging Neptune every night, working hours and hours at the telescope, getting, and this was like almost pre-internet, it's so old, getting fax messages from Andy Ingersoll from JPL. Heidi, this is what we're seeing, these Voyager images. You need to look at this time and this time. And I'm like, okay, you know. Yeah. So I missed the whole Voyager flyby. I wasn't there for the flyby, but I was there for everything leading up to 5 days for the flyby. So in a sense, and this is how I try to frame my life story and deal with that huge disappointment. Shoemaker Levy 9 was payback. It was karmic payback for missing the Voyager, which was sort of I had expected to be the focus of the pinnacle of my career, you know, and then I missed the whole thing. We did all the science still, of course, but I missed the party. I missed Chuck Berry playing at JPL. I missed it all.
Oh, really?
Because I was observing on Mauna Kea for the whole week, 9 days straight. So anyway, sorry, I'm getting maudlin.
All in the service of science. Yeah, that's awesome though. I mean, that's a really cool story. I mean, it's almost like romantic sounding, being on the top of Mauna Kea. And I know how it is though, the altitude and everything like that. But it's stellar observations, I would say. Amazing. Did you have what were the results of your observations up there? Did you see kind of like a dimming of, I mean, I guess it's not really well resolved, Neptune from...
Well, it was actually really very worthwhile. What we could see, remember this is 1989, all right, Keck hadn't been built yet. All we could do, and we didn't have adaptive optics yet. So I had to play a lot of tricks with the telescope and the dome to minimize the seeing. And what I learned in the course of my PhD thesis there at Hawaii is that most of the seeing was dome seeing, all right? And the actual natural seeing of Mauna Kea is fantastic. It was, 0.2 arc seconds, 0.3 arc seconds. That's the natural seeing up there on Mauna Kea. But the dome, the heating in the dome, people's body heat, computers, just residual heat from the daytime warming up things, that contributed to all sorts of turbulence in the dome, in the atmosphere, and that was screwing up people's observations. So what I could see a disk for Neptune, and I could see bright features on the disk, and I could see they call them we call them blobs. There's a big round blob with a big white blob on it. But over a period of hours, you could see the blob move from one side of the planet to the other. That was this feature rotating. And what we discovered with our simultaneous ground-based image, my simultaneous ground-based images, and the Voyager images that were taken, that arrived at Earth 4 hours later because of light travel time from Neptune, the great dark spot had bright companion features. And what we were seeing was the companion cloud in the mid-infrared. And so that's what we were seeing. And what was really interesting is that in previous years, people had tried to do Neptune imaging and they had bright features on the planet, but they were at different latitudes than the bright feature that I was tracking. And they got different rotation periods. And that was actually important for the Voyager Neptune mission because we were trying to plan observational sequences using these old rotation periods. And I had this showdown with Brad Smith and Rich Terrell at one point where they're like, your periods are wrong. And I'm like, no, my periods are right. And I was just a grad student, but my PhD advisor arranged a backroom meeting at one of the Division for Planetary Sciences meeting where it was the dark room, I remember. And it was Brad Smith, the head of the Voyager imaging team, and his number 2, Rich Terrell, and me and my thesis advisor behind me. And I laid out all my observations on the table and I showed what I was right. And they agreed that I was right, that what their rotation periods and their features corresponded to a different latitude and different, something else. And so it gave us a clue that that great dark spot must have been at a different latitude with a different rotation period. And in fact, now, with 30 years of Hubble observations, what we have found is that Neptune's great dark spots do come and go, and they're at different latitudes, and their companion clouds are at different latitudes and have different rotation periods. So it all made sense retrospectively, but it was having the absolute simultaneous Voyager ground-based images that allowed us to be sure of this interpretation. So scientifically useful.
Yeah, that's fantastic. I understand that the observations are essentially over now.
Yes.
Let's see.
Apologies. I don't have much to show that they've stopped, apart from that we have a login screen, but obviously for security, I can't show the login screen itself. So
the sun sets, it always has to.
So I think at the moment it's just daybreak in Hawaii at the moment. I think it's 2-3 minutes past 6 is daybreak for Hawaii. So unfortunately, because of that, that's starting to blot out Uranus. We can't continue the rest of our observations. But in theory, we've taken about 146 degrees of rotation of Uranus, so that's another good more than a third of Uranus's surface. So fingers crossed we can knit that together with what we saw on Friday, and hopefully with tomorrow's observations get the best image that we've had across the whole planet for Uranus in the infrared.
That's wonderful. Thank you for doing these observations. It makes my heart sing to see young people picking up and observing Uranus and adding to our body of knowledge for this amazing planet.
Of course. I mean, I think with the Ice Giants conference that Lee had back, the beginning of last year, when we could see people in person, it was nice to see there was such a large mixture of just different generations, I suppose, of scientists, and it's daunting to feel like it, but I think it's been clearly stated all the way through this, the generation that's going to be making these missions and trying to plan to go towards Uranus and Neptune, unfortunately will not be the same generation that will be taking the results and the data and will be going through those results. So I mean, I guess this is my own message to the audience as well. If there's anyone that is intrigued or interested and thinks, actually, I might want to delve in that, honestly, I would say go for it. See what you want. I mean, we'd love to have more people involved. The more people we have more involved, the bigger the message can become of, we need to go to the ice giants, please.
Yeah. I just want to share, like, when Voyager was launched, I was still in high school and had no idea that I would be, interested in a career in astronomy, and let alone ice giants. And it just takes so long to build and so long to get to these missions that they are exactly as you said, Emma, they are multi-generational. And same with Hubble. I got to use Hubble when I was a young postdoc, and I had absolutely nothing to do with building it, but it was there for me and for the science that we needed. And, that realization for me is what makes me not sad about the fact that I'm probably not going to be there when we do get to Uranus, because the people who built Hubble, they may not have been there to see Shoemaker-Levy 9 or see our amazing Neptune images or all the other amazing Hubble things. You don't do it for you. You get to a point where you just realize, for me, it was like, I'm not this James Webb, this next generation space telescope. I'm looking forward. I'm like, yeah, I'm probably not going to do this for me. I'm doing it for everybody else. And when you realize that, and you have to think that way when you're an ice giant person, even the science takes decades to figure out, to do a year on Uranus, 84 years, none of us are going to have a scientific career 84 years long. So we're relying on the people who were doing the observations the decades before. So, when we get back to the next solstice, people will be looking back at Voyager. And when we get to the next equinox, people are going to be looking back at all the work that we did in the 2007 era, and we won't be there, for it, but they will the publications and the science that we've laid out there hopefully will be giving the base for the understanding of these very long period planets. It's even harder for Neptune, right? 165 years. So, we've only seen a month on Neptune, let alone a year. So yeah, you have to shift your perspective when you're an ice giant person.
To borrow a phrase from Isaac Newton and then flip it a bit, it's like standing on the shoulders of giants with a telescope. So if I've seen further, it's by standing on the shoulders of giants with a telescope. Yeah, and you're right. Yeah, as you go further out to the solar system, the generational gaps, they do seem to expand bigger and bigger. That's kind of interesting. I myself have just Jupiter and Saturn mostly, but I'm increasingly becoming enamored by the icy giants.
We'll get you there, James.
Yeah, thank you. Yeah, I would like to come on board for this thing. Yeah, I'm becoming a big fan of a mission there, and it'll be awesome to see what James Webb does to revolutionize, well, the entire universe practically, but our little corner as well. Be very useful. I'm aware that you've already given lots of time, Dr. Hamill, for us today. We're very grateful for it. I'm actually not sure what happens exactly at the close of the sessions, but maybe Emma, you'll know.
Well, I guess just a rounding off comment, which is, again, thank you so much, Dr. Heidi Howell, for your time today. It has been an amazing pleasure having you on for today. We obviously want to thank everyone that has come along and supported us today and been watching. Remember at the beginning of today's discussions, we said, and we still mean, that everyone that came in today, you can count yourself as an observer. You have been observing Uranus alongside us. And please know that we are putting these on to really be able to show the kind of science that's going on and get everyone at least involved, and perhaps this might inspire a couple of people for, again, a topic that we've been mentioning for the next generation. Of course, want to thank Lucinda, who unfortunately isn't with us at the moment, maybe in chat, obviously for putting this all together, as well as the rest of the HD Plus team. They've had Nahid and Riyang in the background, who are PhD students alongside myself with Dr. Tom Stallard, who have been diligently all the way through this producing the spectra and the images that you've been seeing throughout today. So I wanted to say a lovely thanks to them, as well as Bernie, who has been our TO for the last 2 days. Unfortunately, Bernie is not going to be our TO tomorrow. I believe we have a new TO, so that's new telescope operator. So I look forward to a new fresh face that I'll be able to discuss a little bit with. But otherwise, I hope that everyone is excited for our third day of the weird and wonderful world of Uranus for tomorrow, where we'll be starting at 9 o'clock British summertime. I don't know exactly where that is across the whole globe. There's many different time zones, but I do know it starts at 10 o'clock in the evening in Hawaii, as that's where our observations are taking place.
Excellent. I just want to say thank you very much, Emma, for all the hard work you're putting into this. It's been, it's inspirational, actually, the amount of the work, and I'm learning a lot by watching you do this. And I think it's really awesome to be able to link the public with actual science observations. Pretty rare, I'd say. We discussed it earlier, but it's pretty rare, and it's a big undertaking. And the weekend too. So, so well done.
Awesome. Well, thank you very much, everyone. Thank you very much. I think it would be about a good point now, so we'll start looking at wrapping up. Again, thank you so much, everyone. Thank you very much for the Royal Astronomical Society. Thank you very much, Dr. Heidi Hamill. Thank you very much, Dr. James O'Donoghue, and Dr. Tom Stallard. And I guess thank you to me as well for being here. Sorry. I hope you all have a lovely evening, afternoon, morning, or day, wherever you are, and we look forward to seeing you tomorrow. Take care, everyone.
Bye-bye.
Bye.